Well, it's not going it out. Okay. I'm waiting for it to come up here. All right. There we go. Okay. Good morning, everyone. Uh, we're excited to be here at the inaugural start of CoSMiC, the first student-run space mining competition hosted by the Cardinal Space Mining Club at Iowa State University. We're located here in the Student Innovation Center on the campus of Iowa State University. We have our arena, our lunar simulation chamber that teams will be competing in, erected here in the outdoor storage room at the Student Innovation Center, and all of the teams are located in the lunar pits, which is located in the atrium of Howe Hall. This event is open to the public, so if you are local here in the Ames area, we invite you to come out today and see the event. Come mingle and talk with the students here and the teams. We have 12 teams, Iowa State among them, from across the nation. We have teams from California, from North Dakota, from also Illinois, and we have New Mexico, Virginia, Arkansas, and Minnesota. So we're very excited to have them here. Oh, and I also have to include Ohio. So come out if you can, see what we have going here, and get as excited as we are about space mining and these student hand-on activities. My name is Jim Heisey. I am the faculty advisor for Cardinal Space Mining Club at Iowa State University. I'm a professor in the Department of Mechanical Engineering, but most of all, I'm an engineer, and I love working with my students and the club here on doing all sorts of engineering things. I get to teach senior design capstone, and we do all our projects with industry, so we do a wide array of different types of engineering. And for the club, it's all about space mining, all about robotics, autonomous operation of robots, a little bit about artificial intelligence, but mainly it's about preparing bases on the moon and Mars for future space exploration. And the main material that we work with is called regolith. And what is regolith? Well, it is a soil that is free of any organics, and I've got some samples here. This big jar here is from NASA itself, and it's material they call BP1, and it's aggregate of basalt mining tailings. It was found by Gene Cernan, the last astronaut to walk on the moon. He was out walking around in Arizona on an ancient lava flow, and he found this material. He said, gee, this feels just like walking on the moon. And so NASA said, well, hey, it's really expensive to get actual lunar material to test to it. We got to find something that's more readily available. Well, they found it right here on Earth. And this is what this looks like. It's a very gray, it looks a lot like Portland cement or coal fly ash, but it is mainly made out of basalt. It's very fine. It has a particle size of 0.05 millimeters on up to about 4 millimeters in diameter, basing on the particulate. When compacted, it does not want to move. In fact, standing on it when it's compacted feels like you're standing on a concrete floor. But if you shake the stuff up, get it very loose, like I'm doing here, and now stand on it, and you can see how much taller it is. It's like stepping in the mud, and it'll pull your shoe off when you try to step out of it. We have our own regolith test chamber here at Iowa State. It's called the Lunar Test Chamber, located in the basement of the Student Innovation Center. And we have our own regolith that's very similar to that, and that's what this material is in this jar. As you can see, it looks just like the NASA stuff. It floats just like it. We call it ISU-1. And what our regolith is made out of is 5 parts Portland cement, 3 parts coal fly ash, and 1 part fine sand. And it has all the same physical properties as the NASA BP1, but it is more carbon-based as opposed to silica-based, if you're looking at it from a chemical standpoint. Nonetheless, that's to be compared against soil, which we have here. We got some good old Iowa soil, and sand. A lot of teams will go test in sand, but sand is not the same as the regolith, because it's like a whole bunch of little ball bearings, and you sink in it, it flows very easily. The regolith does not like to move unless vibrated. If you vibrate it, it goes everywhere, because it's very light, and in an Earth atmosphere, it will flow. You've heard the term, I'm sure, pyroclastic flow with volcanic eruptions. Well, we get to see that here whenever we're shoveling it, because we'll throw a scoopful of a regolith and it hits the ground, and rather than just landing like most soil does, it actually float along the ground for significant ways, and which works great with leveling out the arena, because all we got to do is toss it and it levels itself out. But nonetheless, it's a very tricky material to work with. It's very abrasive because of its fine particle size. It gets in everywhere. It will jam up gears. It will wear stuff out very quickly. And this is the challenge that we have to work with mining on the moon or mining on Mars. Mars material is a little bit different because it does have an atmosphere. It does have moisture. And so as a result, that material is a little more closer to Earth soil. The NASA exploration of Mars has been pretty eye-opening, because we're finding Mars is very much like the Earth in many ways. It just doesn't have enough of an atmosphere. The moon, however, has no atmosphere, but what it does have is a lot of charged particles. Because there's no atmosphere, it's bombarded by the solar winds, and it charges a lot of the surface material on the moon. And after the flyby of Pluto that NASA did a few years back, and they noticed that Pluto had an atmosphere, they came back and looked at their lunar reconnaissance orbiter and noticed that it looked like the moon had an atmosphere too. But they did some more research and found out it was actually suspended regolith that had taken on a negative charge and was floating above the surface of the moon by about 1 kilometer, and it made it look like the moon had an atmosphere. But nonetheless, interesting things too about the moon. When Neil Armstrong and Buzz Aldrin did their first moonwalk, they noticed when they came in from their walk on the moon that the regolith smelled like hot burning electronics, because it had so much positive charged particles in the material and negative charged particles that had very much a burnt smell to it. Subsequent explorations of the moon found that this material was very clingy, would cling to their suits heavily. The astronauts also developed some coughing issues with getting the material in their lungs because it floated so much, but they did recover from that. But we have to take the same precautions here when we work in our lunar test arena. Our students have to wear personal protection equipment, N95 or 99 mask. They're fully suited up in a Tyvek suit, wearing latex gloves and rubber boots as they're working in a lunar arena. So it's kind of like suiting up for space exploration. But they do enjoy it mostly. The suits get very hot, and we do a lot of testing in arena, and we do invite schools to come and use our test chamber as well for testing their robots. So we're looking forward to competition runs today. They should be coming up shortly. I'll be here today as your host. I'll get to interview some of the teams that you'll get to meet. I'll go through the team names right now. First on the registration roster is Sonoma State University, SSU Lunabotics. And then we have Youngstown State University, the Penguin Moon Miners from Youngstown, Ohio. Then we have the University of North Dakota Lunabotics team, followed by the San Diego State University team called Team Creed. We have North Dakota State University, the Bison Robotics. We also have the University of Illinois at Urbana, and they are the Illinois Robotics in Space. We have Northeastern University. They're called NU Lunabotics. We have the University of Minnesota. We have Iowa State University, the Cardinal Space Mining Club. We have New Mexico Institute of Mining and Technology, and they're the Miner 49ers. We also have Virginia Tech, that's the Polytechnic Institute and State University, and they are Virginia Tech Astro Robotics. And lastly, we have the University of Arkansas, and their team name is Razorbots. So we're looking forward to today's runs, and we should have them up later this morning as we get everything prepared to go. So again, if you're just joining us, I'm Jim Heisey. I'm faculty advisor to Cardinal Space Mining Club, and I will be your host throughout the day for this competition, and looking forward to sharing with you all the wonderful work that these student teams have done. Thank you. Okay, we got the first team going on, so I've got my mic on. Okay. Good morning, everyone. We got our first team loading up in the competition arena. This is the Cardinal Space Mining Club from Iowa State University. They are the host team for this competition. They will not be competing in this competition, but they will be running demonstration runs so that they can collect data on their robot, make a comparison to the other competitors. We're excited about this competition. This is an inaugural event here at Iowa State University, and it is hosted by the students of the Cardinal Space Mining Club at Iowa State University. So it is the first in the nation of its kind being a student-run competition. We do have our corporate hosts, which you see there at the bottom of our screen going through. You want to give special thanks to Caterpillar and Danfoss and CoSMiC. They do a lot with LiDARs. If you've never heard of the company before, they're very big in LiDAR equipment internationally. We also have Mechdyne, Collins Aerospace, Iowa State Space Grant or Consortium, and the College of Engineering that have supported us in setting up this space mining competition here at the campus of Iowa State University. So the Cardinal Space Mining team is getting the robot set up in our arena. What you see there is a simulated lunar environment. The material in there is crushed lime rock. It has a particulate size very similar to that of the surface of the moon. It has very similar densities, and so the digging forces required to run in that material is very similar to running on the moon. NASA uses this material as a safe alternative to their standard material, which is called BP1 after Black Point, Arizona, where they get their material from. Their material that they use has similar densities to lunar material that Neil and Buzz had brought back from the moon and the subsequent Apollo missions, 11 through 17. And we get the opportunity every year to go down to the Kennedy Space Center and compete with other universities in one of their space mining arenas that they have set up at the Space Education Center at the Kennedy Space Center Visitors Complex. They have a lunar simulation environment in there. We've built ourselves a temporary shelter here, you can see as well, erected by the students. What it consists of is about 22 tons of crushed lime rock. It's about a foot deep. The structure itself is made out of 2x6s, 2x4 and plywood. It has a tarp base in it and plastic put on the walls as a dust barrier. They have a HEPA filtration system set up on it with dual fans to create a negative pressure system to keep all the dust inside the arena. So with the workers now stepping out of the arena, I might ask the guys to go ahead and take that rake out of there too, so that's not sitting in there while the robot's running. They should have the robot running here shortly, and you'll get a chance to see what's going on and what space mining looks like. The particular robot here that you're seeing is called Lance 1. It weighs about 57 kilograms and is capable of mining a significant amount of material. And last year in the NASA competition, we collected close to 200 kilograms of material and got that deposited in a berm area. What our pit worker is doing here right now is he's working the collection area, making sure it's all smooth so that we have an initial point with which to measure from, because in order to grade these, the teams are going to be building a berm, and we're using a laser LiDAR unit from CoSMiC that will measure the volume of material that they drop. And he's now marking out the drop zone that the teams, where they need to build their berm into. And this is where they'll drop their material, and then we'll evaluate that for each team, and the team that gets the greatest amount of material collected. How long is the run, guys? 30 minutes, 30-minute runs. Which doesn't sound like all that much, but when you're designing robots, they're running off of batteries, and the amount of battery power that you have to carry for one of these robots to do its work for a half hour can get quite significant. A lot of these teams use a lithium polymer battery. It's a plastic-based battery system that's very common in the RC hobby realm and robotics realm. They're fairly lightweight and can carry a fair amount of power. You can pull a fair amount of current out of them as well. But if you pull too much or discharge them too far, they will catch on fire. And because the lithium polymer battery has its own oxygen source, they're very hard to put out. So for safety, around the arena, we do have a bucket of sand that we can use to douse or contain the fire for the battery, and we also carry those in the Luna pits where the teams are set up, so that we have any issues there, we're prepared for putting out any battery fires. But over the course of the competition, over the years that I've been involved with the Lunabotics Mining Challenge since 2010. We really haven't had any battery fires. So the teams that get involved with this are very professional in what they do. The students are very safety conscious. As you can see here, our team workers wearing their PPE equipment for working in this material. And the teams that are working in the pit areas or where the robots are set up are also making sure that they're wearing their safety glasses and being safe with their tools that they're working with. We're very safety first minded here at Iowa State University and with the competition. A little bit about the competition itself. It was originated with NASA and Caterpillar. Eric Reiner's at Caterpillar, who is their vice president in charge of autonomy and mining equipment. Got very interested in creating a competition with NASA to look at, well, how can we train students to do autonomous operating robotic systems, because that's what Caterpillar does with their great big mining trucks. But knowing too that the future in space will involve mining. It will involve setting up bases on the moon and Mars. If we go beyond that to the asteroid belt, then we'll have to create systems that will be capable of collecting resources out in space. Interesting thing, the most valuable resource out in space that anyone could collect is not gold, it's not platinum, it's not the most abundantly traded commodity on the surface of the Earth, which happens to be aggregate. It's actually water. Water is the most critical resource that can be collected in space, because with water, you can separate that to get hydrogen and oxygen, which you can use as rocket fuel. You can also use it for oxygen for the astronauts to breathe, and water to hydrate and keep the astronauts alive and grow plants in space. And these are the key things that they're doing at the International Space Station. The big issue with mining these materials in space is it takes a lot of rocket fuel to get off of the surface of the Earth into orbit, and even more rocket fuel to get onto the moon. So for every kilogram that we would want to put into low Earth orbit, it's going to take 2,000 kilograms of rocket fuel. To get to high Earth orbit, it's going to take another 5 kilograms of rocket fuel for that 1 kilogram of water. And if we want to go to the moon from high Earth orbit, it's going to take another 2 kilograms of rocket fuel. So by the time you calculate that all together, you're looking at a significant amount of rocket fuel just to get that 1 kilogram of water to the moon. So it gets quite expensive, and that's why the Saturn rocket itself was so big. So the big challenge here is, how do we save on rocket fuel? How do we save on resource costs? And one way to do that is design lightweight robots that can go to the moon and collect this material, or go to Mars and collect the material. They have found water in the moon. They have found water on Mars. And so how would they collect it? Well, they wouldn't send an astronaut out with a shovel and tell them go dig it up. They'll send a robot out and it'll go do it. And this robot sitting here is an example of what one might look like mining on the moon or Mars. A little bit about this particular robot. It has a bucket ladder system for collection that you see on the left side there in your picture. The arms that are sticking up there carry a camera and a LiDAR unit for tracking obstacles. Then the box is the hopper or the bin that holds the regolith that the bucket ladder picks up. And in the bottom of that bin is the a belt conveyor for unloading the material into that red area, which is actually a lightweight nylon material. And the reason we have that back there is twofold. It contains the dust that gets generated whenever you're dumping regolith. That dust will go everywhere into the air and all over. And we can see now the robot's moving. But as I mentioned earlier, when you dump regolith on the ground, this material, it likes to flow. And we don't want it to flow. We want it to pile up in a berm. So we set this tent up, as we call it in the back of the robot, so that the regolith has a constrained space that it's being deposited into, and it cannot be allowed to flow. And that will then give us the bigger pile. Last year at the competition, NASA thought this particular robot looked like a beloved Sesame Street character, so they nicknamed Lance 1 Snuffleupagus. And we proudly wear that nickname for this robot. He's very good at what he does. And give you a comparison too, here we have about a 57 kilogram robot that in an hour's time could collect 4 to 5 times its own weight in material. And it's doing so on a power usage less than what your hairdryer would use. It's about 600 watts average power usage on this robot. A typical hairdryer with its heat coil is about 1500 watts. So it's a very efficient digging machine. And to give you an idea how much weight is that, well, that is enough to fill a half-ton pickup truck in about an hour's time, which I think a lot of us would be very hard-pressed to do that with a shovel on our own. So, okay, so they got the bucket ladder. They're testing the operation there. They'll get some things adjusted and get the robot ready to roll. They're checking maneuverability on this. And the objective here is they got to go through an obstacle area and avoid the rocks, which, okay, going to have to do a little driver training for the team. They're just checking, probably checking out to make sure that they're not going to be too easy to get over. So here we go, and we're heading into the obstacle area and mining area. Okay. And they're getting themselves orientated to what they want to do. One of the things they can do here for building the berm is, you can see we got 2 rocks sitting there in the arena. Those rocks could be easily used for building a berm. They make a good foundation for, now he's backing over the rock. I hope he's mindful of that, but that's okay. Okay, so now he's setting his bucket ladder down, and he's digging up material, and that's being deposited into the hopper. This robot is designed to dig generally at about 4 inches depth, though he's digging a little shallow right now, just an initial run, just probably getting a sense for what the arena's doing. He'll make several passes, digging up material, maybe going a little deeper each time, or shuffling to the side to pick up fresh material on a track. Looks like he's going to make an adjustment on his run here. Yep. And dig up material. The reason why we're interested in building what's called a berm, which is just a ring of raised material, is that when a rocket lands on the moon, that material is very loose, and with no atmosphere, it will pick up the velocity of the rocket blast, which can be a significant fast, 1,000, maybe 1,500 miles an hour. But with no atmosphere, no drag, that material can be projected for miles along the surface. And at that speed, with a particulate size, can cause significant damage to any habitats or buildings that would be erected close by. So in order to not have to travel a significant ways from the launch pad to your operations base, if they would set up a landing pad that has a high berm around the entire landing pad, well, that deflects the rocket blast up and eliminates the velocity of the material going along the surface of the earth, and then makes it safe to have buildings close to the landing pad. And so that's the objective here with this competition, is to create a berm area that would be located around the rocket landing pad. The interesting thing about this too, NASA's doing a lot of research on how they can take the lunar material. Like I said, it is basalt, and it's very much a glass-like material. If they heat it up significantly, they can form that into glass rods that have a significant amount of strength, and that can be used like a reinforcement rod, like they use for building roads. They can also take the lunar regolith, because it is somewhat like a low-grade concrete. They can add water to it, and it will solidify, and they can use that, and they've experimented with this out on the Pacific International Space Mining Center out in the main island of Hawaii, and have tested landing pads for rockets out there by doing just that, using reinforcement rods made out of glass basalt, and then making low-grade concrete out of the basalt material, and making rocket pads, and then testing how much that material erodes when a rocket lands. Now it looks like they're getting ready to make their first dump here of material. The hopper will rise up, they'll turn the belt on, and you can see the material dumping out of the back of the robot, and they're going to see how much they have. And they'll pull forward, and there they go. Shaking the material out of there. Looks like he's got a pretty good pile sitting there. If you're wondering why he's kind of driving all over the place, one of the challenges here, there's about a 2.5-second delay between what the mission control person who's driving the robot sees and what's actually happening in the arena. And so sometimes when you move your controls, you go too far, and you have to then make adjustments. And it takes a little time getting adjusted to that time delay. And it's similar to operating things on the moon. The signal delay between what you see happening on the moon and when you see it on Earth is about 10 seconds. A lot can happen in 10 seconds operating a robot. If you're on Mars, depending on where Mars is in relationship to the Earth, that time delay can be anywhere from 45 minutes to 90 minutes, and that's significant. So obviously, operating anything on the moon is going to have to be autonomous. It's going to have artificial intelligence to make a lot of its own decisions. The robots that are operating on Mars right now, Curiosity and Perseverance, they actually use, hold on, this is interesting. Not sure what he was doing there, probably just testing maneuverability out, or something got stuck. All sorts of things can happen in these events, and like a motor failure, a wire coming loose, and all of a sudden your robot doesn't do what you want it to do. I think we're seeing something similar to that here. Oh, maybe we got everything running. we will find out when they get done with this run. I'll ask the team how things went, what sort of things were they experiencing. Given that the thing is going around in a circle, I would venture to guess that the right track has probably got some mechanical issues with it. Could be jammed by a rock. It could have a motor that became unplugged. It could be any number of mechanical things. Nonetheless, he's just continuing to dig some material and get as much data out of the robot as he can. Okay, the track is moving, so there we go. He's going to have to explain that maneuver to me sometime. That is not the most efficient way to go about mining material. Ideally, what you want to do, and this is Caterpillar's philosophy on mining, is you go straight out and you come straight back. You unload your material and you go straight out and get some more and you come straight back. And that's the most efficient way. But these are student drivers. It's interesting to note, if you look at the top of the robot, he's got quite a bit of material sitting there on top of the hopper. So he might be running his bucket ladder a little fast, or that hopper might be completely full. We don't know for certain. We can't tell. We don't have that camera angles to know. He certainly collected plenty of material, and my recommendation is he would go get that unloaded. So, okay, so here he goes. He's heading back to the berm area to unload. Oh, you hit that rock. Make an adjustment. There he goes. Just had to double check his position. Interesting thing, you've noticed there the red material that the, oh yeah, he's got quite a bit of material in there. Yeah, he pulls that out, spreads that around. Yeah, he's getting a pretty good berm built there. Now he's digging up more material. Last year at the NASA competition, this robot did take first place in mining. One of the key strategies it did is it has a push plate between the tracks. They picked the bucket ladder up all the way, and you kind of see that push plate right there behind the bucket ladder. And they pushed 3 rocks of significant size. One of them weighed just as much as the robot did. And so they made sure to have the hopper filled with regolith before they pushed the rock. And then they pushed all 3 rocks into the berm area and were able to make a significantly sized berm. I think they had close to 2 cubic meters of material built up in that berm. So a significant amount of material collected in 30 minutes. So one of the key aspects of this competition is of course the engineering that goes into this, and the method that we use is a strategy called systems engineering. And one of my systems engineers from last year just walked into the building, Gustavo, and did a tremendous job of leading the team through the disciplines that are required. System engineering is about understanding first what is the mission that the robot's going to do, what is it required to do, what are the tasks, can we define those tasks into engineering terms that we can design to, and then from there understand what systems do we have to have on the robot in order to carry out those tasks. From there, then it's coordinating the teams, looking at the various different aspects. With a robot like this, you have mechanical systems, you have structural and electrical systems, you have power system, that is the battery storage. Then you have the sensor systems and navigation. And then, of course, there's driver strategy. You have to plan your mission out and understand what's going to be the steps that you're going to take in order to carry out this mission. And with that all said, then everything comes together, you test it, and if everything works, then you take the robot and put it on its first mission, which in this case would be at the competition, and you operate it and see if it performs to plan. Again, this is an interesting tactic I see them doing. It's not recommended by the professor, but hey, it's their robot. They can run it any way they want. And they're making a pretty nice little crater there. The thing you'll notice, though, too, this robot is operating with tracks as opposed to wheel. A lot of the NASA robots, well, all the NASA robots that are operating on surfaces of planets are operating with wheel systems. The main reason they do that is for reliability reasons. Tracks do have an issue. They take a fair amount of maintenance in order to keep them running well. Though we haven't really had any problems with our tracks. I keep convincing NASA they should try tracks sometime. But the advantage on using a track system is several. The first one is the amount of traction that you get out of a track system for the weight of your vehicle. The second is the low compaction that the track system has when operating over surface. It means you're not going to sink into the material. And when you're operating with something as soft as lunar material, if it's not hard packed, that sinkage rate is really critical in allowing your robot to operate. The other advantage that we find with tracks as well is their resistance to becoming stuck. As long as the robot's not hung up on the belly, and as you can see here, it's climbing right out of that crater it's dug for itself, there's no issue with operating on the surface. One of the NASA judges that we had a few years back made a nice comment about Iowa State's robots. He said that in most cases, the regolith owns the robot operating in the arena, but in the case of our robot, we own the regolith. The track systems have worked very well for us over the years, and this is an excellent example showing why that works so well. Okay, not quite sure what he's got going here. Part of what they're doing, they got about 14 minutes left in their competition run, or in this case, it's a demonstration run. They're probably just monitoring data on the robot, and because they get a lot of information back into mission control. They have to make assessments. Is our hopper full? How are we doing on battery power? What's going to be our next strategy? As he backs through here, they have to make a decision. Do they go back and dump more material into the berm area? As mentioned before, the whole objective is to build a berm for blast deflection of a rocket launch pad, rocket landing pad. If you've been keeping track of any of the NASA or SpaceX launches, SpaceX has their Starship. They hope to take that thing to the moon or Mars. It's going to be a significant challenge to land that rocket, given its height, given its landing legs that it has, to get that landed on the moon. So it's going to take a very well prepared launch or landing pad or landing structure to get that rocket on the surface of the moon. If they use their Falcon rockets, they have a little more leeway, but it's still going to be a significant challenge as compared to the lunar modules that were landed by the Apollo mission that took astronauts to the moon. I know NASA has been doing some work on their new lunar landers with Project Artemis, but given the success of Starship and that they're also weighing the possibility of using commercial systems to go back to the moon for exploration. There's a lot of ifs on the current space program, given certain current budget constraints and that. Putting politics aside, it's really all about getting the biggest bang for our dollar in what we do in space exploration for the sake of gaining science and understanding more about our Earth and the solar system that we live in and our role in this solar system and this universe. So with that, I'll go ahead and let the robot here continue to do its thing, and I'll just let you watch, and we'll see what happens with this run. This is Jim Heisey, faculty advisor for Cardinal Space Mining Club at Iowa State University, and this is CoSMiC, the Collegiate Space Mining Challenge. Okay, I just got word back from the team that we're having an issue with the actuators that raise the hopper up and down that control the height of the bucket ladder, and that is one of the technical issues they're looking at right now in the robot, trying to understand that. And that is typical of some of the things that can go wrong on a space mining competition. You spend hours working on these robots, trying to make them perfect, and then you get them into the arena, and one loose connection or one bad plug, and next thing you know, you've got a system that's not operating ideally. And fortunately, they were able to collect a fair amount of material. They are able to move the robot, but they also have to be somewhat cognizant of what they're doing because they cannot pick up the hopper. That negates their ability to push any rocks into the berm area, so that creates a challenge for them in this run anyway, building a bigger berm. And so that's probably one of the reasons why they were going in a circle, was to reduce possible stress on items. I'm surprised it's done as well as it has, given that that is the technical issue that they're dealing with. This is a very robust robot design. One of the faculty advisors last year came up to me at the NASA competition and told me that our robot was a beast with the way that it operated. It did very well at the competition. There were several other schools that did very well. And we've got 5 of those schools here at this competition, if you include Iowa State University. So we're hoping that this CoSMiC space mining competition gives you some exciting things to see. We're certainly seeing something interesting here with all the material on top of the robot. Normally we have a plastic shield to control dust and control material flow on the robot. Now the team can understand why that shield is there, with all the material that's sitting on top of the robot that's not in the hopper and not in a position that they can get rid of it. So they'll have to clean that off before they take it out of the arena. So those are one of the many mechanical issues that you can run into with the design of a robot. This crushed lime rock that we use, not quite as dusty as the regolith that we normally test with. Our ISU1, as I mentioned before, is a combination of Portland cement, coal fly ash, and sand. It is more of a hazardous material, so when our students are testing the robot in our lunar test chamber that we have here in the Student Innovation Center, they have to wear personal protection equipment, M99 mask or a respirator. They dress up in a full-body Tyvek suit. They wear latex gloves and rubber boots. They tape the gaps closed between the gloves, boots, and the suit so that there's no room for the material to get in, because it can be a skin irritant as well as a breathing hazard to the lungs. So I see they're digging up more material here, and we'll see what they decide to do here with 5 minutes left in the competition run. Again, this robot, its name is Lance 1. It's for a lunar autonomous navigation space excavation system or construction equipment system. And the reason they picked Lance is one of our 2 swans in Lake Laverne is named Lance. We have Lancelot and Guinevere, and or no, Lancelot and Elaine, I'm sorry. And so they've named it after one of the swans, and the logo has a combination of a swan, and you can see a lance in the middle of the logo as well on that. This robot runs on 2 large lithium polymer batteries. It has 4 VEX Falcon 500 brushless motors on it. Each motor is about 400 watts of power at a time. When we're operating the tracks and the bucket conveyor, we're using about 400 watts of power because we're not using the full power out of the motor on the digger, and we're certainly not using the full power out of the motors on the tracks. Then the unload belt conveyor in the bottom of the hoppers also has a motor on it, but that does not run at the same time the other motors run. So that's one of the things we have to manage, is understanding what systems are running when and how much power they're pulling from the batteries, so that we have sufficient energy storage on the robot to run for a full half-hour's time. You'll notice too that it looks like there's some buckets missing on the bucket ladder. Well, that's done on purpose. The reason for that is we have to fit within a confined space on the spacecraft, and one way to take advantage of that is to leave some buckets off of the bucket ladder so that you can put that all the way down to minimize the height of the robot in its stored configuration. And to do that does not hurt the operation of the bucket ladder. Just because it doesn't, missing a few buckets doesn't hurt the drive system at all, and so it's able to tolerate that one little modification in order to save some height on the robot, because height or just volume of the robot itself is a premium. NASA gives us a size restriction that our robots have to be. The size box we have to build to is 0.75 meters by 0.75 meters width and height, and the length of the robot is a maximum of 1.2 meters, and so we have to fit within that. Our weight limit, we can't be over 80 kilograms. NASA penalizes the teams on weight. It's you get 1,000 points for passing tech, and then if your robot weighs 80 kilograms, you'll get penalized 800 points, so you're left with 200 points from there. And then it's up to your scoring, how much you do with autonomy, how much you do with material collection, how well you do with dust mitigation on your robot, and such. So on a typical NASA competition run, this robot would have a lot of clear acrylic sheeting covering the bucket ladder, covering the top of the robot in order to contain all the dust. That would be worth about 150 points to the team for dust-free operation. They'd also have an extra cloth tent over the discharge area. Right now they have that open because this lime rock is not quite as dusty as a regolith. So we don't have to be as careful with our dust mitigation. So it looks like they're going to get in position here and back up and dump some more material. They got a pretty good berm there just with material they've collected and with the technical issues that they've had. So that is good. Fortunately, they don't have to raise the hopper just to dump the material out thanks to the flat belt conveyor, but they could be a whole lot more efficient if they could. So they'll take a look at that. They'll get that fixed on their second demo run. They'll do a better job, I'm sure. They got a pretty nice berm there that they've got set up. It's got pretty good shape to it. With 52 seconds left on their run, they'll probably say, well, this is good enough. We'll stop here and get the robot cleaned off and go figure out what's wrong. I'll interview the team later. We'll come back with more information as to what specifically went wrong with this run and what went right. And this is all part of engineering, all a part of what we do in the Cardinal Space Mining Club. It's highly technical, and it's a wonderful training ground for our engineering students involved with this club. But our club is made up not just of engineering students. Anybody can join the Cardinal Space Mining Club at Iowa State University and be a part of this organization that is helping NASA with space exploration by being a test bed for some of the technologies that they would like to use in doing space mining. But we do have a lot of mechanical, electrical, computer. We have aerospace, civil engineering. We also include education students, because we do a lot in the club. Part of the NASA competition is doing STEM education, doing outreach. So we go out and we go to local schools and we tell them about what we do. We have little activities that we have them do to simulate doing space exploration. We have several different levels of small robots that the club has purchased and that school children can operate and learn about coding, learn about planning a mission, get to experience firsthand driving a little robot that can push sand and push rocks. We set up a simulated little lunar environment and a collapsible swimming pool, something that's about 4 feet square. And so we set up a little lunar environment, and school kids can test their skills at driving a robot and building a berm, just like we build a berm here. And if you're interested in having us come to your school and do a demonstration, you can reach us at our email, which, hey guys, what's our email address? CSMC CSMC_ISU at iastate.edu. And you can make a request of the club to have us come and demonstrate the things that we have and do. And what engineering is all about, what space engineering, space exploration, space mining is, and why we do it. And it really is the next big industry in the future that's going to happen. So I'm going to sign off here for a little bit, check with the team and see what's coming up. Next team to run will be the Illinois Robotics and Space and their team. And we'll try to get one of their people on here and talk with them while their robot is running. This is Jim Heisey, faculty advisor for Cardinal Space Mining, signing off for the next few minutes. I'm going to test it. I'm doing this And we got that on. There we go. Okay, we're back. I have Sebastian
Perez Aburto.
Berto. Yes, thank you. He's our club president for Cardinal Space Mining Club, and he's here to tell us a little bit about how the run went, what challenges we had. So, Sebastian, why don't you tell me what happened there in the CoSMiC arena?
So I haven't had a chance to talk with the team that was in the control room, but it seems that we were not able to move our linear actuators up and down, moving our bucket ladder up and down. So we weren't able to get those deep trenches that we wanted, and we just had to kind of go around in circles to make those big mounds to then be able to dig through, and that was kind of the plan going in there.
Okay, so that I wondered why he was doing the Billy Preston and going around in circles.
Yeah, that was not intended, but good quick thinking by our mission control team to try to get some points on the board.
Excellent.
And, but it seems that our depositing went well, and we do need to look at dust mitigation, because we did get a bunch of that ag lime on top of our robot, which is not ideal.
It appeared you had about half of the load on top of the robot where you couldn't get it off.
Unfortunately.
Yeah. But these are the fun things about doing the space mining and doing these sort of engineering challenges that you guys go through, and how much you get to learn.
Oh yeah, no,
doing this.
It's great. Yeah, no, it's definitely a part of it, and you know, we're all learning here, and it's a fun time.
Excellent. And so when's your next run going to be?
So I believe we're gonna be running tomorrow. I forget what time at this moment, but we're gonna be running tomorrow sometime.
Okay.
And that'll be the last run, and it's gonna be the best of 2 runs. So.
Best of 2 runs is what the competition is set up for.
Yeah.
Okay. Why don't you tell me a little bit about the team?
Yeah, I mean, we're split into between mechanical and controls. We have around 30 members in our team, give or take, and yeah, I mean, we're all I think pretty capable engineers, and just have a lot of experience. This team has a lot of years doing lunabotics competition, and we try to use that to the best of our advantage, looking at a lot of designs from previous years, and trying to take those and improving our robot each year.
Yeah. What sort of majors do we have involved in the club?
Yeah, we got a lot of mechanical. We got computer science, software engineers, and a couple electrical engineers. We also have a few physics majors, interestingly. Okay. But really, we try to we have roles for everybody.
Stay here. I'm gonna talk. Okay.
And yeah.
Yeah, great. Okay. How long has the club been going?
Oh man, I think you could probably answer that better than I. I've only been here 2 years now. It's my second year, and I'm a senior. I'm about to graduate. But how long has it been?
Well, glad you asked. We've been going since 2009. When we started here, when NASA first started their Lunabotics Engineering Challenge. Our original team name was Team Lunacy, because we were crazy about going to the moon, and so that was our name to start out with. We got to competition, and anybody who's ever watched the movie That Thing You Do, the Wonders got announced as the Ornitas, and sure enough, we got to NASA, and they announced us as Team Lunacy. Well, Iowa State wasn't very happy about that, so the next year they asked us to change our name, which we did. We became the ISU Lunabotics Club, and then as years went by, the focus kind of changed from lunabotics to robotic mining, and so we decided to change our name to Cyclone Space Mining Club. Well, that worked out fine until a few years ago, when the athletics decided, you know what, Cyclone is going to be a name we're going to hang on to. So we had to change our name one more time, and now we're the Cardinal Space Mining Club at Iowa State University. But we're very happy to have that name and our logo, which we see, if you look at Sebastian's shirt here.
We got it right over here as well.
Yeah, here, I pull that bucket over here with Cyan and our mascot. And we'll hold that up to the camera. So what you can see here is we have this logo. So we have this gear that's on here. And you see the big red circle here in the center. Well, that's Mars. We got the polar caps of Mars, and then we have this what looks like a swoosh around here. That's an orbiting spacecraft. And then we have the moons and asteroid here, because those are two heavenly bodies that we're going to mine on as well, along with Mars. And it's hard to see here from this camera distance here, but there's a little swoosh on here. It kind of looks like an upside down or kind of like a Nike swoosh. But actually what it is the Starfleet logo from Star Trek, and it's our homage to science fiction and everything that we have on here. So we're really proud of this logo. We wear it on our shirts. We have all sorts of patches, and we take it with us wherever we go.
Yeah.
So we've been in operation since 2009. Been in the NASA competition every year that they had it. We went to 2 competitions at Alabama. We also got invited to Hawaii to the Space Center out there and did an international competition where we actually ran our robot on the same place where they tested Curiosity and where the Apollo astronauts did their preparation training for going to the moon. And it was on the volcano Mauna Kea on the big island of Hawaii, at an altitude of about 10,000 feet. And if you've ever done any physical work at 10,000 feet, I can tell you it takes a lot of effort. The atmosphere at 10,000 feet gets kind of thin, and it can kind of get hard on an old guy like me. But we had a lot of fun. We were very successful there with that. What was fun about that competition, West Virginia was there, Alabama was there, we were there along with 3 other schools. In 40 hours of mining, our robot dug up 1,000 pounds of material.
Impressive.
Very impressive.
Yeah.
40 minutes, our robot dug up 1,000 pounds of material. West Virginia dug up 1,040, beating us by 40 pounds. That's the way this competition goes. Lots of times it gets very close, but had a lot of fun, learned a lot while being out there, and we continue to learn a lot with every year that we've been in the competition since. The reason why we aren't at NASA this year, well, there were some challenges that NASA ran into. They suddenly found out they didn't have enough space for all 50 teams. And so they did a sudden rule change, and we wound up with several teams that normally would be there competing, weren't able to get in. We were one of them. As I mentioned earlier, 5 of the top 6 competing teams from last year at the NASA Lunobotics did not get into the competition. So what did we do about that?
Well, we took the best, put our minds together and figured out that we could probably host our own competition, and that's what we've been doing for the past 2 semesters, really.
Yeah, imagine my shock when I asked them, well, what are you going to do about this? And they said, well, we're going to run our own competition.
It almost gave you a heart attack, probably.
Yeah, you just about did. But I have to say I'm very proud of this team. You've done a tremendous job. My hat's off to all the club members, but especially Jacob Mosier and Timothy Kuhn and Sebastian here, and Anna Overman and several others that really have put their heart and soul into this. And a special thanks to Hannah Albrecht with I can't say conference planning and management at Iowa State, helping us put this whole thing together. We're very excited to be here for this competition.
Of course, thank you to you for supporting us through it as well.
I'm just here making sure you guys are doing what you need to do and being safe. And I'm very happy to say I'm very proud of you guys because you do it very well. You make my job very easy. And I'm very, very thankful to have the opportunity to work with you guys and to see all the amazing things that you do with the skills that we're teaching here at Iowa State University.
Yeah.
So thank you. Okay, how are we looking in the arena? Do we have another team? My understanding that Illinois had some technical problems and we're looking for another team to come in. So who do we have coming up next? Maybe Razorbots? They're in the middle of inspection. Okay. So what you see going on in the arena there, we've got one of the pit workers loosening up the material. It gets pretty compacted. One of the fun things is, I was showing earlier, we got this regolith material here I can hold up. And there's 2 lines on this jar. I know you can't see it very well, but I'm going to put my finger here. This level right here is the material compacted This is the level when the material is loose. If I shake this up really heavily like that and flip it right up, you'll see it's up at this upper line. And if I pound on it a few times like this, usually about 20, but it'll get down. I'm already very close. I'm about right here. And this is typical lunar material, the way it behaves. And in the compacted state, you step on it and you hardly sink into it. It almost feels like you're stepping on concrete. But in that loose state, and robots can loosen that up quite a bit, it's like stepping into dry mud. You'll sink right into it about 4 or 5 inches, and when you go to pull your foot out, it'll pull the shoe right off your foot. It's really amazing. And then because of its fineness and how it builds up static charge, it clings to everything. And we'll have a trail of regolith for hundreds of yards past the robot because of how that material sticks to everything. It clings to the walls in our lunar test chamber. We have regolith 6 feet up on the wall. It refuses to come off.
Yep.
We'll brush it off, but then as we're operating, it floats in the air. It'll collect on the wall and just stay there. And the NASA astronauts, Apollo program, had the same challenges. If you ever get a chance to go to the Kennedy Space Center and look at some of the suits, you will see just how dirty they are from being on the moon and operating. The lunar material is very aggressive, it's very abrasive, and our test material is the same way. It gets into things. We had hardened steel sprockets running our track system a couple years ago, and we had done enough testing in the arena before we went to competition. When we got done with competition and we took a look at our sprockets, and we had just about wore out the teeth on our sprockets. We were shocked as to how much abrasion was occurring because of the lunar material. And this is one of the many engineering challenges that we have here on Earth, just doing a robotic mining. If we were to actually do it on the moon, then we pick up a whole bunch of others, like there's no atmosphere on the moon. We take for granted what the atmosphere on Earth does for us was insulating us from the sunshine, but on the moon, the sun side of the robot will be as hot as 400 degrees Fahrenheit, hot as your oven baking a pizza. And on the shade side of the robot, it will be minus 100 degrees Fahrenheit. So you're looking at a 400 to 500 degree temperature range across the robot. And what's the major issue that you, being an engineering student, that you see with that sort of temperature change across the robot?
Oh, a lot of expansion and contraction in the metals is between those ranges for sure.
And what does that lead to?
Going in and out of spec in tolerances.
I would say a whole lot of stress, right?
Yeah, sure.
Yeah, so we see stress in many forms. We see stress in material, we see stress in the engineers,
Yep.
we see stress in the astronauts operating things, trying to get it all work as the robot is get twisted out of shape by all the temperature changes that it goes through. So some of the fun challenges, if you can call them fun, that we have to go through in doing engineering for space mining. So,
Yeah.
okay. Well, Sebastian, I'll let you go back to team check. Maybe you can report back with me later and
For sure.
find out more what is going on over there.
Yeah, thank you for having me.
Yeah, no, thank you for everything that you do for the club and for Iowa State. And what's your major?
I'm mechanical. I'm a mechanical engineer. Yeah.
Okay.
Yeah.
Excellent. So we do have an excellent mechanical engineering program here, along with an excellent aerospace program. Well, we've got a lot of excellent engineers. We got an excellent college of engineering. We have, I think, 15 different major programs here in engineering at Iowa State. We have one of the largest by enrollment mechanical engineering programs at Iowa State. We have a very highly rated aerospace engineering and agriculture and biosystems engineering program here at ISU. And we just have a lot of fun doing a lot of different things here. Engineering is a great field to be involved with. I have certainly enjoyed it. I've worked in industry. I've been teaching here now 18 years. And out of that, 14 of those working with these guys doing space mining. It's been a lot of fun. I think I have the best job in the world.
Yeah.
because I get to work with guys like you that do just tremendous stuff. So
No, I've only been here 2 years, as I said earlier, but I love it here. It's
yeah.
transferring here from my community college has been
Yeah.
just a great
Which community college was that?
College of DuPage, and they're actually they've been with Lunabotics for a while as well,
Yeah.
and that's actually how I got introduced to Iowa State. Was we reached out, and because Iowa State had a lunar testing chamber, we reached out, we came over, tested our robot, and we took a tour of the campus, and I kind of fell in love. So
Yeah.
that's why I decided to transfer here and finish my degree here.
Yeah, College DuPage is one of our partner schools now here at Iowa State with doing Lunabotics. We reach out to a lot of schools. University of Nebraska and Lincoln also comes here to test their robot. We've had requests from some other schools to come and test their robots as well. We're happy to have anybody come and test in our lunar test chamber if they just want to go ahead and make the trip. It's not a top secret facility. It's just here to be utilized. And I'm very thankful to the College of Engineering that allowed us to build that room in this new $80 million Student Innovation Center. It's been very helpful to us and testing and preparing for doing these sorts of things. And we hope it'll lead to great things as NASA and other companies like SpaceX and Blue Origin, and there's many others. There's at least 15 other companies out there that space and space mining is their focus, like Planetary Resources. What are some of the other companies? Do you have an idea? Some, yeah,
There's a lot.
there's a lot.
There's a lot of them.
We're seeing our students getting hired by these companies too. That's the cool thing about it, and they're getting a chance to do some of this work, and it's exciting. It's exciting to be a part of it. The future is limitless as to what this generation is going to have an opportunity to do. I'm actually kind of jealous that I'm getting more toward the end of my career, but I'll do everything I can to inspire this new generation of engineers to go out and do great things. So, all right.
You've done a great job. Thank you.
Well, it's all up to the work you guys do. So,
Thank you.
all right. Well, thank
right.
you, Sebastian. I'll let you get back with the team and figure out what's going on.
Yep.
And we'll take a break here for a few minutes and let's see what's going on in the arena. And I'll check with a few people and I'll be back in a little bit. This is Jim Heisey, faculty advisor for Cardinal Space Science Club and professor in mechanical engineering. Thank you. Office planning and management. Okay, it's showing the arena yet. Yeah, I wanted the camera on the air. Okay, welcome back. This is Jim Heisey, faculty advisor for Cardinal Space Mining Club. We've got some visitors coming through. Just had a wonderful time talking with them. Just to give you an update, two of our teams, Illinois Robotics and Space and Razorbots, both found they had technical issues. They weren't ready to run just yet. This is typical what we see in competitions. And so we asked some of the other teams if they wanted to move up. They did not. They're still working on their robots. So we're going to have about an hour here where nothing's going to be happening competition-wise, but we may allow a few teams, if they're ready to do some testing, to come in and test. So we're going to be, we'll keep the stream going in the arena so you can see what's going on if we get anybody to testing, but we're going to be off the air as far as doing any announcements. Well, we'll be on and off. I'm going to try to get some people in here to interview and to teach you a little bit more about what we do here and what's all involved with putting together a competition like this. And I'll be back in just a few minutes, hopefully with a few other people to talk to. And maybe we'll get some information from the team too, more technical information about what happened in the run, how it worked. Sebastian did a wonderful job of telling us what was going on. I'm very impressed with their quick thinking that they did on the club and how the robot held up, even though it was not everything was operating as we intended. So I'll be back in just a little bit. This is CoSMiC, the Collegiate Space Mining Challenge at Iowa State University, hosted by the Cardinal Space Mining Club. Thank you. Okay, quick update here. It looks like Razorbot is from the University of Arkansas is in inspection, and they'll be running probably in about the next 10 minutes or so in the arena. So as always, these things change constantly as we're going, and it's no different at NASA as what we're doing there. So we'll be back on as soon as they get ready to run, and we'll continue monitoring the arena so you can see what's going on in there. Thank you. Okay, do you have me going live? Okay, we're back. We have the University of Arkansas Razorbots setting up and getting ready for their run. And it'll be interesting to see. I hope to have one of their team members over here soon to talk with us a little bit about their robot and what's involved with their club and such. For those who are just joining us, I'm Jim Heisey. I'm faculty advisor for Cardinal Space Mining Club and professor of practice in the Department of Mechanical Engineering. I've been involved with the club since 2009. I've gone through many NASA competitions, and so the club decided I should be the person talking to you about what's going on here. Why do we do space mining? What's all involved with this? And so we're seeing the Arkansas Razorbots here setting up their robot, giving an idea for the NASA competition that goes on every year in Florida at the Kennedy Space Center, University of Central Florida. The whole idea behind the competition is to have groups of university students design, build, and test robotic mining systems because it allows NASA to get far more bang out of their dollars with having the students building and coming test and looking at the various technologies. You can see here in the upper left corner, this is the mission control room. I see the Arkansas students are already in there getting ready to drive the robot. We have the 3 students here from the Arkansas team with their walkie-talkie. I see Littlefoot there. They put some names on the back of their uniforms. I'm sure one of them is Bigfoot too. But we have a lot of fun doing this. But at the same time too, it's a lot of very important work, very good training ground for the students, learning about robotics and about planning and about systems engineering and documenting. Oh, he's getting the dust off his glasses. Okay. Yeah. Very good. We love it. We love it. We get a lot of different disciplines working on this: mechanical engineers, electrical and computer engineers, a lot of good enthusiasm. We see the Arkansas team is very enthusiastic about what they're doing, and we love to see that. So in about, let's see, they usually have about 10 minutes for setup. Is that correct, guys? About 10 minutes setup time. And then they'll have 30 minutes of run time to collect their material and deposit it into a berm. And you'll get to see that. The berm location is right there by the door where they brought the robot in from. We have a LiDAR unit installed in the ceiling of this competition arena that the students designed and built. They all CAD'd this up using SolidWorks. Ordered all the material. Cost us about $2,000, maybe $3,000 to build this. We have 22 tons of crushed lime rock in here. It's about a foot deep, a little over a foot deep. And this is a material that behaves very similarly to, as close as we can get, that's easy to work with, to lunar material. The density of this material is about, it's about 1.8 kilograms per liter. So it's 1.8 times heavier than water. You get a 5-gallon bucket of this, and I tell you what, it gets pretty hard to carry. It's that heavy. But the robots will dig this up, and they'll deposit that into a berm. And what is a berm? Well, a berm is a raised area that is built in order to protect any structures that are by the base. So go ahead and have a seat here. And I've got one of the students from Arkansas joining me, and you are?
Ryan Dark.
Ryan Dark. And tell me a little bit about you and your club.
So I'm a junior mechanical engineer.
Yeah, come in a little closer if you could.
I'm a junior right now at the university, majoring in mechanical engineering. Our club is mainly a CP project for our students. This year we had about 25 people on the team.
Okay. When you say CP project, what does that stand for?
So it's a critical design project. It's the project in your senior year that
Okay, so it's like capstone projects.
Yes.
Okay, excellent. Okay,
but we had 25 people total this year. Not all of us are seniors,
Yeah.
but that's just how we improve on what we've done every year.
Yeah.
We don't want the seniors to take everything they've learned and walk out the door. We want them to be able to pass that on.
Yeah, that's a great point. That's one of the biggest challenge about this competition is retaining technical knowledge from
Absolutely.
year to year. Yeah. So does your university have a club affiliated with this as well, or is it done just through senior design?
It's done just through senior design. But like I said, we do encourage underclassmen to join. Like I said,
Yeah.
I'm a junior. This is my second year.
Okay.
We've even had people that want to join as freshmen.
Does the University of Arkansas have student organizations or student clubs on
Yeah.
campus? You should consider. We've been a student organization since 2009.
Okay.
And so that allows us to recruit all sorts of members, not just engineering students, but others.
Sure.
And it allows us to build a fairly good club. I know a number of universities do that, but then a number of them too have just senior design projects. And all of them seem to work out fairly well, get varying degrees of success out of that. So tell me a little bit about your robot that they're setting up there.
So this one's it's kind of weird the way this one came about. We were going to keep our one from last year and just improve upon it.
Yeah.
But then the what if factor came in. Well, what if we did this a little different? Okay, well, we can change this. And then it just snowballed.
Okay.
So now it's a completely new robot based off of the same general kind of concept of a skid loader like we did last year. But this time, the main difference is one arm instead of two.
Okay.
And obviously well, you can't see it right now, but our bucket's a little bit different. It's not a regular scoop type bucket.
Okay. Tell me a little bit about that. Yeah.
So that's actually the team that I was on.
Uh-huh.
I did a lot of the SolidWorks modeling, testing, and everything for this bucket. But we wanted something. Last year we had issues with being able with our actuators to scoop.
Yeah.
So we said, okay, we just had to use that to push, and that didn't work out very well.
Yeah.
So we kind of said, okay, we could do something like a bulldozer blade.
Mm-hmm.
But we still want to be able to pick up any sort of little rocks or anything, be able to move dirt. So we kind of kept a little lip on the bottom. That way we are still able to retain a little bit of material.
Okay. How heavy does a robot weigh?
It is just under 40 kilograms. So
Okay.
right around 70 pounds, I think.
70 pounds? Okay. How many pounds in a kilogram?
I'm not sure off the top of my head.
2.2.
2.2.
Yeah. So if you're 40 kilograms, that would make you
Just over 80.
about 88 pounds.
Mhm.
So it's just to help our audience, for those that aren't used to the metric system and still thinking in the old Queen's English methods of pounds and inches.
Which I am. That's what I know a lot better.
Yeah, me too. But I've gotten pretty good at making the conversion between both systems, and that. And NASA does everything by the metric system now. So, yeah. And what are your size limits on your robot? How big is it?
I don't know those.
Dimension-wise.
I don't know those off the top of my head right
Okay.
now.
I did mention earlier, NASA requires us to fit it within a box that is 0.75 meters by 0.75 meters by 1.2 meters long. In inches, that's about 29.5 inches square and about 42 inches long is what we're looking at for the size of the robot. And it has to weigh under 80 kilograms. And that's about 176 pounds. And so when we bring the robot into the arena, if it's an 80 kilogram robot, it requires 4 people to lift it in. At 40, you can probably get by with 3. It looks like you got 3 people in there.
Yeah, and
Today?
you can easily carry it with 2.
Yeah.
That's honestly, that's probably the biggest difference from our one last year.
Yeah.
We built ours so stout last year, it was easily 130 pounds.
Yeah.
It was,
But one of the interesting trade-offs here is you're trying to mine material, and what are some of the physical factors you have to dig?
to dig, you have to have the weight to be able so you don't spin.
Yeah, and yet NASA penalizes us on weight. So that creates some very interesting engineering challenges for us as we try to do this. Like some of the strategies you could apply is, okay, I make my robot super light, but I make sure I have strong motors, and then I will collect material and put it in holding pods so that I can artificially make my robot heavier, and then I can do more work. But I didn't have to expend 5,000 kilograms of rocket fuel for every kilogram of robot weight just to get it to the moon. That's what the golden number ratio is approximately. No wonder space flight is so damned expensive.
No kidding, it is.
Yeah. So, so tell me a little bit more about your team.
So we had about, like I said, we had about 25 people this year. We split them between the bucket design, the arm, the chassis, and the wheels, and obviously the computer side of that.
Yeah.
I'm mechanical, so I didn't have a whole lot to do with the computers.
Yeah. Thank goodness, right?
No, yeah, absolutely. I'm not a computer guy by any stretch, so that would definitely not be a team.
Me neither. I'm just a good old cranky. I work on the mechanical stuff, and yeah. So
I'd much rather turn the wrench than type the computer code
Yeah.
and everything like that.
yeah. How many hours do you think your team has into building this robot?
Oh, I'm not even sure. We meet, our designated meeting time is 10 to 2 on Saturdays, and generally a lot of people, myself included, put in a lot of time outside of that. We really
Yeah.
don't track how much time we spend with it. It kind of, I mean, it can vary. We can put 30 hours into it one week if we need to, or we can do only a couple.
Yeah.
It depends on if we're getting parts made right now, or if we're in the very beginning stages where we need to do a lot of research.
Yeah, I do a lot with tracking effort hours on
Mhm.
projects because I manage our senior design program and I keep track of how many hours our teams put in
Yep.
and doing that. I would estimate that on a typical Lunabotics team designing and building a robot that you're probably putting in close to 1,000 man hours of effort
I would say, yeah.
in building the robot. When you got 20 people working or 25 people working on a project, the hours add up fast. And a typical senior design project here at Iowa State will have 5 students working on a project, and within their lab time and that they do, they'll put in about 300 man hours of effort
Okay.
on that project. So when you think, multiply that by 25,
Yep.
and it gets quite significant. And I know that guys like you and the girls as well that are out there working on this, you put your hearts and souls in it to
Oh, yeah.
put a lot of extra time into it. But you learn so much from it as well. What are some of the significant things that you've learned, some of the big challenges that you've hit this year in doing this?
Well, obviously the biggest challenge, like I mentioned earlier, is not keep saying the what if. We can change every little thing, but that's going to add time. And
Yeah.
that's one of the things we ran into this year. We kept hitting the wall, and we'd have to get this done.
Yeah.
Which is why we had the technical difficulties earlier, trying to get everything to connect right.
Yeah.
But then just the time management, obviously the budget is always something important. And then just different ways you can go about this. There's more than
Sure.
one ways you can do this competition. It doesn't have to be a skid loader design like we're doing, or
Yeah.
a bucket or a bucket and chain system.
Yeah.
There's multiple ways you can do this. But like you said, weight's a factor, but
Yeah.
then NASA also penalizes on dust.
Yeah.
So if those bucket and chains, when they get spinning fast, they'll make a big dust cloud. We feel that this advantage for us is we don't have as much dust, and we can move a lot more material faster.
Mm-hmm.
But just
Yeah.
all the research that we gain and everything that we can move to next year,
Yeah.
and that, like me being a senior next year, I'll be able to pass on to people that are in my shoes now or just coming
Mhm.
into the program next year, show them this is why we're doing this. I know you haven't learned this in classes yet, but here's kind of something to tie all that into. And I've noticed that in my classes, oh, this is what they're talking about.
Okay, so that triggers into a very important point. But by doing hands-on stuff here, you learn to appreciate the things that we're trying to teach you in the classes.
Absolutely.
Then I suddenly understand how the math applies to what we're physically doing
Yes.
with building stuff. What have been some of your biggest aha moments?
So with mine, it's just all the physics of everything. Physics was never one of my strong subjects. So how's all this going to work together?
Yeah.
You've got all the friction of the robot and everything in the motors, and then obviously you got the weight and everything with it. I
Yeah.
didn't know all that in the classroom very well, but I got into here, and it just puts everything into a better perspective that I can.
You had to figure it out, didn't you?
Exactly,
Yeah,
yes.
yeah. That's one of the key challenges. We as engineers, I had a fun time this semester with one of my teams. I was talking with the engineers, and I said, "Well, how's the design looking?" He says, "Well, I hope it works." And I immediately told him, "There's no hope in engineering. You have to do the math. You have to figure this out. There's no hope here. You make it go." So, okay. Oh, okay. All right. So, Okay, I'm going to pull in one of the other members in here.
Okay.
Thank you again
You bet.
for
Thank you.
taking time with me today, and
Absolutely.
good luck.
Thank you
with the
very
run.
much.
Okay. All right. Okay, come here, sit down. I'm going to pull you a little closer.
Okay.
Okay. I have Grace Harding here from the Razorbots team. Apparently their run got scrubbed. They ran into a technical issue. Why don't you, Grace, tell me a little bit about what happened?
Yeah, so we had a couple of technical issues. So the first is that our network was unreachable. We think that when we went into the room, just as we were getting there, the Ethernet port on our laptop just died, so our Ethernet connection wouldn't work. So bad timing, but it's great because that's something that we can actually test when we get back. It's good to have a known problem. We've got Ethernet cables in the pit. We'll go back. We'll see if that works. We've got an Ethernet USB-C adapter, and it'll be a done deal that we can definitely fix before the next run.
So it's good we got that second run, right?
Yeah, so that one's all good. And then our other issue is that they didn't seem to be powers to the motors, which is would be really scary. But in mission control, we kind of just think that we had to scrub the run anyway because of the router issue or the laptop issue.
Yeah.
But we think that maybe the ground team didn't turn the e-stop so that they never let the motors get power. Which is
Okay,
just
that's a big issue.
a silly
Yeah.
itch, but it's everybody makes mistakes, and that's also we really hope that's what happened because otherwise we've got a much bigger issue. So
Okay, well, fingers crossed.
Yeah.
Why don't you explain for our audience a little bit? You mentioned e-stop. What is that?
right. So that's our emergency stop button. So whenever the emergency stop is pressed, the powers will not release to the motors or the linear actuators on the robot. It's a really big safety thing. So you reach out, smack the button down, it stops power to everything to make sure that nobody gets hurt. But if you don't turn it to release, then power can't come back out. So when you turn the robot back on, nothing's going to move because it's going to think, oh, I can't move anything right now. I'm in emergency mode.
Kind of an important detail, don't you think?
I think so.
Does your team that's in the pit, do they have a book that they follow to go through steps?
So we didn't send a checklist with them this time,
Ah,
which is it's
okay.
because we haven't printed it yet.
Okay.
But
Little
we're
details.
on the mic with them in mission control, and I think that would have been, one of our next steps because we're very familiar with how the robot works.
Yeah.
It's just with the problem with the port on the laptop,
Yeah.
the run has to go either way. So
Well, for our audience out there, one of the interesting things, if you ever get a chance to watch another NASA mission on TV, one of the things you'll notice is that there'll be technicians there holding a notebook, and everything that NASA does, they have a step-by-step guidebook as to what has to happen when, so they don't miss anything in putting things together, because the consequences, if they miss a step, could be at best maybe a scrubbed launch, which gets expensive, or at worst something like what we witnessed on Apollo 13. So very significant stuff, technological challenges in doing engineering, and Grace, you
absolutely.
get to experience some of that here.
yeah,
So
and it's
lesson
something
learned.
that we're really passionate about. Actually, the other person in mission control with me is in training to be get his pilot's license.
Oh,
so
really?
we actually have done a lot of reading through NASA's guidelines recently and
Mm-hmm.
piloting guidelines on how to make proper aviation checklists because
Yeah.
they're really strict, they're really thorough, they're great flight guidelines. So we definitely know how important those are. We just didn't have time to print them out before we got here.
Yeah, that's kind of an important point when you're flying up there. Is if you have a problem, you can't just pull over and open the hood and check out what it is.
Right.
You're kind of committed to a landing before you can do any such stuff. So, yes.
Absolutely.
So, anything else you want to share about the club and mission control?
Not much. I think we're just excited for our next run and going to go
Okay.
test out all those issues and make sure everything works and then hopefully dig a good pile of moon dirt.
Okay, well, great. We're very excited to have you guys here at CoSMiC participating in this competition. Wish you the best of luck on your second run. So thank you.
Thank you for
very
having
much.
me.
Okay, we'll see you later. All right, well, there you go. Another attempt, another scrubbed run, but that's all part of engineering and lunabotics. It's what we come to expect. It's one of those interesting things. We get very excited. We're very key up to do a run. Then all of a sudden, we got a technical issue and we have to go sort it out. That's the tough thing about engineering, and that's what really helps us make better engineers out of this. One of my favorite quotes from a Civil War general was, "Suffering builds character," and we certainly get an opportunity to develop the character of our engineering students here with participating in things like the space mining and just teaching them engineering and getting involved in hands-on projects and having to sort through these problems, because you got to keep in mind it's technical, it's machinery. There's no emotion in that stuff. You can't pray or hope that they're going to work. You have to work the problem as the engineer and make things work. So it's one of our biggest challenges that we go through being an engineer. So I guess next up is going to be Bison Robotics when they are ready to go. That is North Dakota State University. And I don't know at this moment what their run time is, but it is probably a little time from now. So we'll just hold tight here and look forward for the next run here at CoSMiC. This is the first time we're doing it, so NASA it runs into similar problems with their Lunabotics challenge that they have. And in fact, if you're interested, they're running a competition today. And if you do a search on Google for Lunabotics challenge, you will find links to their YouTube channel and what they have going on today, because they're the top 10 teams that ran earlier in the week at the University of Central Florida. I think they had about 30 teams competing out of the 37 that they originally were going to have there. They picked the top 10 teams, and then they run at NASA for the grand prize trophy and the first place mining trophy. There's a lot of things that goes on with the NASA competition. You do a STEM project, STEM outreach project that you get graded on. Because a lot of what we do with part of the competition too is about STEM education. So a lot of the teams will go to area schools, set up special projects. For instance, at Iowa State, we do a lot with going into grade schools and junior highs with robotic projects that the students can do. And they learn about how do you go about programming a robot, what would a robot typically do on a space mission. And we actually have some robots that they get to run. We have, for young grade schoolers, we have a little robot called a bee-bot. It looks like a honeybee, but we actually have a little 3D printed cover we put over him, so he kind of looks like our robot when it's running. And they do simple, what are called packet commands. They hit buttons and have it do certain steps, and we give them a map and say, okay, make this robot go from this point to this point. As efficiently as you can. Then we, for next grade up, 5th and 6th graders, we have what's called an M-bot. And the M-bot uses, again, packet commands, but here they're using symbolic commands on a computer, and they're putting together a whole program together. And for that, we have a large lunar map, and we have what are called waypoints on it, significant geographical points on the moon, that we challenge the students that you're going to start at this position, and you're going to test your robot. You're going to figure out how to program it. And we want you to hit all 5 waypoints and then go to the finish spot on the map and see if you can get your robot to do it in one run. And usually it'll take them about 12 to 20 repetitions on their programming run until they get their robot to do that. It's really quite fun to watch them do it, and it's a significant learning thing for them on learning how to program and plan and collaborate and work as a team. We also have a couple of other robots we created where, for various age groups, we set up a mini lunar arena, and the little robot has a track system on it like our robot with a push blade, and we have them try to build a berm, learn how to drive a robot, how to push a rock, how to dig material, and make a dirt wall that would be used to protect habitats on the moon from the rocket blasts for the ships that are coming in to bring supplies or take astronauts back home. That's the whole idea behind the space mining competition that NASA holds and that we're duplicating here at Iowa State University in CoSMiC. So we have a total of 12 teams here from various different universities. I'll go through their names. We have Sonoma State University. We have Youngstown State University of Ohio. We have the University of North Dakota, UND Lunabotics team. San Diego State University out of California, Team Creed. We have North Dakota State University, the Bison Robotics here. We have University of Illinois at Urbana-Champaign, the Illinois Robotics in Space, they call themselves. We have Northeastern University, the NU Lunabotics team. We have the University of Minnesota. We have Iowa State University, Cardinal Space Mining Club. We have the New Mexico Institute of Mining and Technology, the Miner 49ers. I really like that name. We have Virginia Polytechnic Institute and State University, otherwise known as Virginia Tech, and they're the Virginia Tech Astrobotics. And last but not least, the University of Arkansas, the Razorbots that we have here taking part in the competition. So far, we've had Iowa State make a run and get a fair amount of material into the berm building area, but they had some technical issues. Apparently a wire got pinched and it cut the power to the actuators that allowed the hopper to be tilted up, which also controlled the digging depth of the bucket ladder. And so they had to do a lot of creative thinking on their run to figure out, okay, we're kind of stuck here. How do we make the most of it? And one of the things I generally tell them is you have to go straight out and straight back to be an efficient miner. And they didn't do that this time. They did the Billy Preston and drove it around in circles. And I asked them, why did you do that? And they said, well, we couldn't put the bucket ladder down, so we tried to build a pile of material by going in circles and kicking it out, and then that created a deep enough pile that we could go forward and dig material. And that's some pretty good creative thinking on what you do when faced with an issue. And that's what engineering is all about, coming up with alternative solutions when faced with a problem. And it worked out pretty well for them. The robot's tough enough to take that, and so it was nice to hear how they dealt with the issue and made it work. Then we had the Razorbots come in. As you, if you were here a little while ago, they explained what happened to them. They had a network issue, and then somebody forgot to reset the emergency stop switch. This is what they call the E-stop. The E-stop is a NASA requirement. If anything would go wrong with a robot such that it needs to be immediately shut down, NASA requires a great big red button on the top of the robot that somebody can slap and then shut the robot off right now. And that is a good thing to have on these robots, believe me, but sometimes we forget to reset them. You gotta, once hit, you have to turn them and release them in order to get your robot back on. And when you're getting set up for a competition run, you get kind of excited and you kind of miss these sort of things. So something that Grace and I talked about is having a checklist when you're going into the arena so you don't miss those sorts of things as you're setting stuff up. Iowa State typically kind of forgets sometimes to do their checklists as well, but we have in the past written checklists for the arena team. I like to call them our lunar excursion team when they go into the pit, because they're dressing up in a full suit and they have full protection gear on and safety glasses and gloves and everything. It's like dressing up in a robot suit or astronaut suit. And but those suits are quite hot. They're uncomfortable, but they do it anyway, and they come out of that usually smiling. And so I'm very, very pleased in their attitudes that they have towards this. So we got another team. I'm thinking next will be North Dakota State University. Bison Robotics will be coming in with their robot. I hope to talk with one of their students and learn more about their robot and their team, and what they hope to do in the mining operations. Again, this is CoSMiC, the Collegiate Space Mining Challenge, hosted by the Cardinal Space Mining Club at Iowa State University. We are a student organization made up of students at Iowa State, mainly engineering students, but it's open to all students at the university. It's a club, student organization, affiliated with the College of Engineering. We have about 40 members. It grows and ebbs, but nice, large, active club. I serve as our faculty advisor. My name is Jim Heisey. I'm a professor of practice in the Department of Mechanical Engineering. I've been here at Iowa State since 2006. teaching engineering. Before that, I worked in industry for 25 years, various different companies. Have had a great career, but I think this is the best job I've had in my life, getting to work with these fantastic students here and all the enthusiasm they bring and the things that they learn and what we get to do here with developing the next generation of engineers and what benefit they're going to have for our nation and the world as they learn new things. As technology grows and challenges us, and problems in the world that have to be solved, I have a lot of faith in this generation and the great things that they're going to do. So CoSMiC, the intent here is over the next 3 days is our 12 teams are going to run in our simulated lunar environment. We have 22 tons of crushed lime rock in an enclosed room that the students have designed and built using SolidWorks, and they built it themselves over the last week. And it has a HEPA filtration system in it with exhaust fans, so it has a negative pressure, so it keeps all the dust inside the chamber, so none of it gets outside. It's about 16 feet by 18 feet, about similar size to what we run in there. And the idea is that the robot will, once loaded in the start area, have to maneuver through an obstacle area and then go into a mining area and dig up the lunar regolith that's in there and then deposit it in a build area to create a berm. And the team that builds the largest berm wins. But as we've already witnessed here this morning, it's not as easy as it looks. The technical complexities of these robots are quite high. There's a lot of various different systems that go into this. You have to have a digging system, a collection system, a propulsion system for moving the robot. There's a lot of mechanical components that go into that. Gearboxes, chain drives, gear drives, wheels or tracks, depending on what sort of system you decide to use for motivating the robot across the surface. Your digging systems can vary widely too. We've seen augers, we've seen scoops, we've seen bucket ladders. A bucket ladder is just a belt with a bunch of scoops on it that will scoop up material. We've seen buckets like skid loaders. We've seen claws used. In the years that we've seen over the NASA competition, we've seen some walking robots. We've seen robots with rotating drums with spirals on them that would kind of slide their way along the ground. Those were interesting to watch run. But the prevalent systems are wheeled systems and track systems. The most common system is the wheeled system. NASA's robots all use wheels for the purpose of durability and weight, because they can't afford to have these robots be too heavy. It takes a lot of rocket fuel to get something up in space and to get it landed on the surface of the moon or Mars. And as we've seen on some of the recent missions that people have trying to land spacecraft on the moon, it's not all that easy. What we accomplished in the Apollo program, because we had trained astronauts on board, was really quite significant, because out of the many landing attempts, I think only 1 or 2 or 3 have been successful, that have been autonomous robotic systems. We've had just as many systems fail, tip over, or crash altogether on the surface of the moon. So it's a very high technical challenge doing those sort of things. Our role in all this, though, is to be a test bed for NASA, to come up with ideas, put them together, put them out there to be run in the arena. NASA gets that information from us, and they use that to help factor what they do for designs in robotics. NASA's current space mining robot they hope to take to the moon soon is called Razor. R-A-Z-Z-O-R, and it's a little smaller actually than the size of the robots you see here, because space and weight is quite premium. And the whole intent behind that robot is to go collect lunar material that hopefully has water ice embedded in it, and then that would be processed in order to create oxygen and water and hydrogen for rocket fuel. The other thing they've since discovered in doing exploration on the moon, there is methane on the moon. The moon by mass, I've been told too by Dr. Phil Metzger, who's a NASA scientist, retired, and he's a professor at the University of Central Florida now. The moon is 45% biomass oxygen, but that exists in the form of oxides on the lunar material. So you could mine enough material and then process it using microwave energy at high heat to separate the oxygen from the base material, whatever it might be, because there's a lot of metalloids and other materials on the surface of the moon that could be used. So you could do a lot of different manufacturing of components on the moon. But then you can free up that oxygen, have the oxygen for the astronaut to breathe. And he had told me that, I asked him, well, how much material would have to mine to keep an astronaut alive for a day? And he told me approximately 1,000 pounds of moon material would have to be mined to create enough oxygen to keep one astronaut alive per day. So that's kind of the technical challenge we're looking at here, by the numbers sort of thing that we engineers always have to do when looking at putting a mission plan together. So that's the first thing we have to understand. What are the requirements for keeping a person alive on the moon? That's the first fundamental thing. We could send an astronaut up there, but if we can't keep them alive, what good is that? From there, what do we want them to do? And then we have to figure out things like, okay, how much energy is the astronaut going to have to expend? What is his diet going to have to look like? What is his caloric intake going to have to look like to get through that? What sort of habitat do we have to set up for them that can live? You know, these are all things that the Apollo program had to go through with putting their lunar module together. And one of the interesting things, if you ever get a chance to look at some of that stuff, how are the astronauts going to sleep on the moon if they were going to rest? That's a really interesting thing, because they had a hammock system set up that they could string in the lunar excursion module. So one guy would sleep low and the other guy would sleep high, and they were in a T configuration inside the lunar module to sleep. And for some of the missions that they went, the initial one with Buzz and Neil, they only stayed a few hours on the moon. That was the first time on the moon. They didn't know what to expect. It was going to be real risky, so they said, let's keep it to a minimum. It's just enough to get there, get some good science, get material, get back. And then we can say, okay, we made it. And then from there, subsequent missions, they planned more and more until the astronauts were staying for a few days. But you notice that they didn't stay for longer than that. One of the interesting things is, I always like to quiz the students, is how long is a lunar day? Does the moon have a day and a night? And the actual answer to that is it does. It actually is rotating in space. We just don't see it because its rotation is gravity locked with the Earth. So we always see the same side of the moon. But actually, as it's rotating in space, it's rotating. So a lunar day is 14 Earth days, and a lunar night is for 14 Earth days. And so if we were to stay up there for a long time, we have to figure out how are we going to get our robot to survive and our astronauts to survive a lunar night, because a lunar night will get very cold. I'm told that the temperature can get down below minus 170 degrees Fahrenheit, if you can imagine being that cold. Very little things work at that temperature. If we want to mine water on the moon, for instance, we're going to have to go into what are called permanently shadowed regions around the poles of the moon. Those are craters that never see sunlight. And the temperatures down there can be 40 degrees above absolute zero. What does that mean? Well, not even electricity flows at 40 degrees above absolute zero. So that creates some significant challenges with getting down into those regions to mine water, which would mean that you'd have to have a robot that can keep itself warm. You'd have to be able to beam energy down into it because it can't see the sun, so it can't run on solar panels while it's down there. So microwave technology comes into play for doing something like that. So these are some of the engineering challenges that would have to be overcome in order to do space mining. So I didn't know if you ever thought about those sort of things, but I thought it'd be fun to share with you today. So we're here at Iowa State University in the Student Innovation Center as a part of the CoSMiC Space Mining Challenge, affiliated loosely with the Lunabotics Engineering Challenge that is currently going on at the Kennedy Space Center. We have 12 teams here that have participated in the Lunabotics Engineering Challenge in the past. but they weren't able to go this year, so Iowa State decided, the club here, let's do our own competition and allow these teams to still get a good year of space mining in to do that. So that's what we've got going on here today. This is open to the public. We invite you to come in and see what we have going on, to come and see the lunar arena that the students are competing in, and to see the robo-pets and visit with the teams and their robots in the Howe Hall atrium. They're in there for the next couple of days through Saturday, and when we'll conclude this competition and hand out the awards. So I'm Jim Heisey. I'm professor of practice at Iowa State University in the Department of Mechanical Engineering and faculty advisor to the Cardinal Space Mining Club. Thank you for joining us online here today. And when we have the next team ready to go, we'll be back and share with you what's going on with that team. I believe the next team that will be running will be Bison Robotics from the North Dakota State University. Thank you. Okay. Okay. Wait until they give us a sign here. All right. Welcome back, everyone. We're getting ready. New Mexico Tech is going to do a test run this afternoon. Not a competition run, but a test run, since we have a number of teams that are still sorting the bugs out, so to speak. I've got Skylar Bunning here from the New Mexico Tech team. He's going to tell us a little bit about their robot and their team. So Skylar, first of all, thank you for being here.
Yeah, thank you for having us. We appreciate it.
Yeah, no, we're very excited to be able to put this on. So why don't you tell me a little bit about your team and your robot?
So we're a team of 14 undergrad students in the mechanical engineering department here at the Institute of Mining and Technology. And our robot is based off of a skid steer.
Okay. So tell me a little bit about the robot. It's a skid steer. How big is it? How heavy does it weigh?
It weighs 71 kilograms. It's a little, it's around a meter of long and then half a meter in height and width.
Okay.
Or not half, 3/4 of a meter, sorry.
3/4 of a meter. Yeah, that's the NASA size box limit, isn't it?
Yes.
So you're taking up every last bit of the space of the size box?
Most of it.
Most
Almost
of
all
it?
of it. Yes.
Yeah, but a little room for
Little
margin of
room, yes,
error.
of course.
Yeah, we do the same thing. Yeah. So, and you said how much it weighed again?
I weigh 71 kilograms.
71 kilograms. So let's put that in pounds. It's probably about 160 some
Yes,
pounds.
they're on there.
Yeah. How many people does it take to pick that robot
4
up?
people.
4 people. Okay. What sort of motors are you using in this?
We're using MMP brushless gear motors.
MMP. Okay.
Yes,
How
Midwest
big?
Motion.
Okay. How big are they?
So they
watts-wise?
have about 1,000 inch-pounds of torque.
1,000 inch-pounds of torque. How was that converted into watts?
I have no idea.
No idea. That's okay. Yeah, the reason I asked that question is because a lot of people want to try to put it in perspective as to how much power is that. You know,
Yeah,
I usually compare it to their hair dryers. Most hair dryers like 1,300, 1,500 watts. Of course, it's not the motor; it's the heating coil
Yeah, of course.
that does that. But it gives an idea just how efficient these robots are in the use of energy and mining. So tell me about the team. A little bit more about the team. How many do you have in the
Yeah,
team?
so we have 14 members. We're split up into 3 different sections. So we have our excavation, works on the digging part,
Yeah.
locomotion, which is the driving part, and then the autonomy and controls, which is all our autonomy and controls.
But they're all
aspect.
mechanical engineers.
All mechanical engineers.
That must be really stressful for the guys having to do the controls.
Yes,
'Cause
it's,
that's not a mechanical engineer's
yes.
normal. How have they done with that?
They've done pretty good. This run, we're not going to do autonomy on this run, and during our actual official run today. But tomorrow, we're going to try to get autonomy working, so we'll see. But
right.
yeah, it's pretty stressful for our members that are on the autonomy. And
I'm
control
sure
team.
I'm sure they've put in plenty of late
Oh,
nights so far.
They have, especially this past couple of months.
I'm pretty sure they're sick of coding at this point
Yeah,
too.
I would say so. Yeah.
Yeah. Wonderful. So, so how long is your now this is part of a class or part of a club?
So we do this. Yeah, we do it for our design clinic. So we have a 2-year design clinic program at New Mexico Tech. So it's part of a
Very
class.
cool. Okay. And it culminates in a senior design class. I
Yeah, it
assume,
would
as
be our
well?
junior and senior design class.
Very nice. Very nice. And who's your advisor?
Alice Dinwiddie, or Professor Dinwiddie, right there,
Okay. Okay.
and Dr. Mustafa Hassan Alian.
Okay. Excellent. How long have you been involved with NASA Lunabotics?
This is my 2nd year doing it, since it is classes at our institution. I started my junior year, and then now I'm a senior.
When do you graduate?
I just graduated.
Well, congratulations.
About a couple days ago.
Okay.
Thank you.
That's got to be exciting.
Yeah, it's pretty exciting.
Where are you heading off to after
I'm
this?
gonna do my master's. I continue getting an accelerated master's at New Mexico Tech.
New Mexico Tech?
Yes.
So you're going to sign your soul away to the university to do a little research?
Yes, I am.
Okay. Yeah. Well, that's excellent. That's excellent. What do you hope to do once you get done with that?
I don't know. I haven't really decided what area I want to go into.
Not quite sure what you're going to be when you
No.
grow up?
Yeah,
Yeah.
I just know I wanted to do mechanical engineering.
Well, wonderful. I'm sure you've had a lot of fun
Yes,
learning
I've
how
had
to
a
be
lot
a
of fun.
mechanical
Yes.
engineer. Yes, and this certainly is, I'm sure, added to that.
Yes, of course.
Yeah. So what are some of your high points and your low points in your experience in this?
As anybody that's done robotics, takes a lot of time.
Mhm.
And so that's definitely a low point, is the amount of time it takes, especially for autonomy and controls people.
Yeah.
My high point is putting all our hours. So as a 14-person team, we put around 4,500 hours, and to see your product actually work, it's pretty nice.
It's pretty exciting.
Yes,
You
it's very
can
exciting.
point at it and say, I made that.
Yes,
Yeah.
exactly. And just it worked exactly how we wanted it to work. So that's even more impressive and exciting for us too.
That is one of the fun perks of being an engineer,
Yes,
is it
of
not?
course.
Yeah. Excellent. Well, hopefully we'll have a successful run. If you are willing to sit in the hot seat with me for a while,
Yeah.
maybe you can tell me a little bit more. I'll pull the computer around here a little bit. And you can tell me about your mission control team and about the robot as it's running and what some of the strategies are. Besides obviously digging and making a big pile of dirt, something we do as kids in the sandbox very easily, but
Yeah.
this is not quite the same thing,
Yeah.
is it?
So I'd assume right now our autonomy and controls team is trying to get into our computer, or what we call SSHing into a computer on a robot. And I don't know if that's is that a countdown timer till it starts, or?
That's the countdown timer for the setup.
Okay.
So because it's counting backwards. When they get into the competition run, then
Yeah,
it'll
it
roll
counts up.
forward. So yeah. And for people watching, I'd like to point out here, we added a little decoration to the desk here. This is one of the trophies that we're going to be handing out. There's a base that goes on here yet, but we made this really neat trophy, and you can't quite see it, but inside this glass ball here is a laser etching of the moon. And so what we have is water jet cut aluminum here, 3D printed base and clips. We've got this glass orb that we got off Amazon, and then we got a special board with fiber optics, and our team member Mason Eck designed this and built 4 of these, 3 to give away
Nice.
as first, second, and third place trophies for the competition. And then we're keeping 1 for ourselves for having run the competition.
Of course.
And so really looking forward to this. So we got another 5 minutes before the run starts. So we're looking forward to seeing how New Mexico Tech does here. I love your team name, by the way, Minor 49ers.
Thank you. I actually don't know who came up with it, but we like it and we've stuck with it.
It's a fun one. Kind of rolls right off the tongue,
Yeah.
and makes one smile when you hear that. So how long did it take you to drive over here from New Mexico?
16 hours, but plus like stopping for gas and stuff, it was more like 18.
Yeah, so not too bad of a
Yeah,
drive.
not horrible.
How long of a drive is it to Florida?
Oh, that one, it was like 32 hours total straight to Florida
Yeah.
last year.
Yeah, from Iowa here to Florida, it's like a 25-hour drive.
Yeah, it was rough.
Yeah,
It was a
we do it
very
in
rough
2
one.
days.
Yeah.
That's a whole lot of camaraderie and character building. You do
Yeah,
it
it really was.
Yeah, because you're probably like us. You take a van or
Yeah,
two
we
and a
take a-
trailer,
yep.
and yep, we do as well. And I ride with the students. I always ask my wife, "Well, you should come along with me down to this competition, see everything." And she says, "No, I'm not riding in a van with college students. It's
Yeah.
just a little too much togetherness." But I've enjoyed it.
Yeah,
It's been a lot of fun.
You get to know all your members really well, especially on these type of trips.
Yes, you do.
Some good ways, some bad ways, but it's usually a lot of fun.
You build team camaraderie
Yes,
through
yeah.
stuff like that. Yeah, is one of my favorite quotes I use from a Civil War general. Suffering builds character.
Yeah, exactly.
Yeah, and we definitely know that we engineers get to build a lot of character in the profession that we do, because a lot of what we do is not easy, and which is characterized here in this competition with what we're doing. Okay, now we are operating. So they are getting themselves oriented. I'd like to point out there's about a 2.5 second delay between what they're seeing and what's actually going on in the arena. So expect to see some bumping and running into things on occasion, unless they are well practiced in what they're doing. And this team, you guys must have done a lot of
We've done
practice.
around 20 hours of practice time with this robot.
It shows. It shows. It's very, very efficient operation so far. And looks like we've had a little bit of wheel spin in there, judging by the clumps that are getting built up. But looks like it's doing a pretty good job. Digging. Nice little turn. I got fairly good load in there. Lost a little bit out of the bucket. One of your biggest challenges is you get going in here and then you get a load in there, and do you get more, or do you take that and dump it and then come back and get more?
Usually we just take more and dump it and go back, but since this is our practice, and I think we're just trying to figure things out for
Yeah.
a real one here in a little bit.
Yeah. Okay, pulled out of that pretty efficiently. For those who may be watching earlier this morning, we discovered that we had about a 30-second delay on visual and about a 2-second delay on sound. So that can really confuse you if you're trying to drive a robot by
Yeah.
sight. One of the things that when you're doing this sort of work is you want to practice at what's called time of flight. And that is when you instigate a command, how long do you hold the command, and do you understand exactly how far the robot's going to go? Because with the time delay, it's very easy to get stuck if you spin your wheels too long. And we've already seen here with your robot just how far it digs into the soil
Yeah.
when it stalls. Boy, that's a good load in the bucket there. Very efficient. Nice work. Not quite getting all of the material out of the bucket when it dumps, but that's the interesting thing about this material is what they call the angle of repose. Oh, it just drove over a rock. Don't get hung up. Now you're back in the start area. That's okay. Head back into the work area. No harm, no foul, right?
Exactly.
But oh, is he going to try to pick up a rock?
I think that's what he's been trying to do this whole time.
Ah. I think he got it. He's pushing it. Kind of got to dig underneath it. One of the biggest dangers here is you can see this very easily. This material is very powdery.
Yeah.
And you can get too much energy into there, and you can get yourself stuck real fast. There was one year we were competing. We had our robot digging away quite comfortably, and the team next door had a robot very similar to this, but they only had 2 speeds: stop and full speed.
Oh.
And they couldn't get the bucket to get a bite of the material, so he put his bucket down and just goosed it. And in about 2 seconds he was hung up in the dirt and fully stuck and couldn't get out, and he was spinning his wheels forward and backwards and all sorts of moon dust flying all over the place, but the robot went nowhere. So that's some of the things that we experienced in this competition. So okay, so sitting there doing a little thinking about what they're going to do. As you can see, the timer's not going because it's a practice run. They're just taking time to really gather data and see what they're doing. Maybe he's satisfied. He's kind of stepping away from the computer. Fun bit of history. 2014, Iowa State was the first team to complete a fully autonomous run. And it really wasn't so much autonomy as it was a fully automatic run. We had laser tracker to keep track of. Yeah, it looks like they're going to go in and pull the robot out. They had a laser tracker so that we knew exactly where to go to get back to the depository where we would put our material, and he just hit e-stop, so it looks like your practice run is done. And then the robot used touch sensors on the wall to know when it's gone far enough, and an encoder to back it up a certain amount. So we just had an automatic program set as to what directions it would drive and how far it would dig. And so they hit a start button and they sit back and let it go through the program. When they get done, they hit a stop button. Well, we had a problem in that run in that there was a power surge, and we hit the command to start the robot, but the power didn't come on in the arena until about 3 minutes into the 10-minute run. And when the robot got the signal, it started. It just went off and it did 7 minutes of digging. And when we got done, the judge said, well, that's nice, but we're not going to give you full autonomy because you didn't run for 3 minutes. And the NASA lead judge came back to me later and he told me about that. And he said, do you want to protest? And I I said, can I? And he asked me again, do you want to protest? And that was the hint that, yes, I want to protest. I said, yes. Yeah. Okay. 10-minute test run. Okay, very good. All right. Next team I've been informed is San Diego State University Robotics. They're going to do a 10-minute test run. Continuing with the story, though, Rob Mueller, the head judge, came back to me later. He reviewed the video, and he had a smile on his face. And I asked him, well, what's your judgment on that? And he said, I gave you full points. I said, he told me my students made it look like a government job. Because he said they hit the button, they put their hands behind their heads so that they could tell that they weren't touching anything. And then when it was done, they just reached down and pushed a button. He said it was like they were discussing, where are we going to go get a beer after we're done with this? So, but that's what autonomy can do for you. So I wish you guys good luck.
Yeah, thank you. We
with
appreciate
getting the autonomy done. Maybe you can make it look like a government job too when you make your run.
We appreciate it.
Yeah,
Thank you.
well, Skylar, thank you for being here, and good luck on your first competition run. Okay, well, as was mentioned to me, we got San Diego State University coming up next to do a 10-minute practice run, and then we'll hopefully they'll give us some good success, just like New Mexico Tech. For 10 minutes of running, that's a fair amount of regolith deposited there within the deposit zone. It'd be interesting to know just exactly how much was left there, weight-wise, kilograms, and volume-wise in cubic meters. So, and that's the whole intent here, is to get as much material as possible within the size box that we have there depositing material. So, again, this is CoSMiC, the Collegiate Space Mining Challenge, coming to you from Iowa State University and the Student Innovation Center. I'm Jim Heisey, faculty advisor for the Cardinal Space Mining Club, who is hosting this competition in Ames, Iowa. And we have 12 teams total here that are running, that were registered. We got 9 here on campus, I guess. What's our total team count we have? Is it 9? 12 including us? But I got 9 listed here, it looks like. I have 9 teams listed here on the running order. Oh, who's going today? Okay. So this is today's run list. Excellent. All right. Well, as you can see in here, we got in the arena, you can see those fans in the background. Their purpose is they're creating negative pressure in the arena. And we have HEPA filtration. That's to keep dust from going outside from the arena. And there's actually a filter in the ceiling of the arena to draw fresh air in, so that we can circulate air through that. The volume that these fans are running at, the velocity, will do a full exchange of the air in that chamber in about 2 minutes time. So we're moving quite a bit of air. I think we calculated out about 2,000 cubic feet per minute of air movement going on with each fan. But of course it has a filter on it, so that throttles it down a little bit. But yes, so our operators in there get the benefit of having some fresh air exchange in there as they operate. So they're getting the New Mexico Tech robot out. We're going to get the San Diego State robot in, and should be ready to go. So I'll be back in a little bit to explain more as the next team gets set up. We can see San Diego State coming into mission control room here, going to get their computer set up and get linked to their robot through the Wi-Fi. To do that, we have an Ethernet set up where the mission control room is in the opposite corner of this innovation center from where the arena is. So they're separated by about 200 feet, maybe a little bit better than that, of distance, and a whole lot of concrete. And they can't see directly what's going on. They can only see what they see on the cameras, what they either have in the arena or what they have on board. They get penalty points for using the cameras out of the arena, but most teams do, because we don't penalize too hard for that. But the big challenge here with running a robot like this is the time delay that occurs between what's happening in the arena and what you see on your computer screen. And so really, this is where autonomy really becomes an advantage, because if you can have the robot measure its environment and make decisions as to where it should go and what it's going to do next, that is a huge advantage in operating, because it's very easy to make a mistake with that delay and drive your robot too far or dig too hard and either get the robot hung up or get it stuck. That's a very common failure in this competition, is getting stuck. And so one of the other strategies that can be applied in running in a robotic competition like this is learning how to do time of flight navigation. And what that means is understand either when you push a control, how far or how fast is the robot going to go, and understand how many seconds you have to run in that state in order to accomplish a certain amount of distance or material gained or material deposited. So these are all the challenges in doing robotic mining that the students have to learn about and overcome. Of course, doing the autonomy is a very complex engineering task that they do. It involves sensor systems and a lot of coding, programming. It takes a lot of componentry that goes into the robot. And on top of this, they have to do a whole lot of strategy planning. What is their mission scope going to be? What does the mission envelope look like? How far are they going to go? How fast are they going to go? How many sorties are they going to do, going out and coming back to collect material? These are all key things that have to be figured out by the engineering team, and why we use the systems engineering protocol that NASA uses for doing these sorts of things. So we can get a team of people together, we can strategize, we can set guidelines or numbers, specifications to not only what is a robot going to do, but what sort of systems does it have to have, how big of motors, how big a scoop, how big of a hopper, how much power do we have to have in the drive system, how much power do we have to have in the digging system. And because it all runs on batteries, then how big do our batteries have to do or be in order to support this for whatever runtime? My understanding is that this year at UCF, University of Central Florida, where the initial part of the competition for NASA was held, they were doing 15-minute runs. And for the NASA part of the competition and our run here, it's a half hour. Well, that makes a huge difference as to the size of battery you've got to run or how many batteries you have to put on board. And the biggest challenge here too, the type of batteries that most of these teams run, they're a lithium polymer. And while they do have a very high energy density, we have to be very careful about how much power we pull out of the battery, how fast we pull it out, how far we pull the battery down, because that can damage the battery, or even worse, make it catch on fire. And LiPo batteries, as is the short term for their name, once they start burning, they're extremely difficult to put out. In fact, they're almost impossible to put out. So the safety protocol requires that we have buckets of sand available. Of course, we'll have one very big bucket there in the arena of sand material that we could use, but basically I'd have to douse the battery with sand in order to constrain the fire so it doesn't get out of control. And so I just, you're fine. No camera there. Yep. Have fun. I just, the club's heading upstairs to have lunch. Looks like they're doing pizza, which is the staple diet of most college students, I understand. So, okay. Let's see here. They're still working on the arena. Oh, he's going to go ahead and mark the box area where they have to deposit so they know where to put the regolith. As I mentioned, there's a competition going on down at NASA Kennedy Space Center this week. They're still making runs today. If you go to the NASA website or Google Lunabotics Challenge, you can get the link to their competition, and you can see what they have going on here. We are broadcasting on YouTube on our own channel, CoSMiC, for this competition. This is the first time we've been running this type of competition here at Iowa State. The reason we're doing that is because several teams, about 15 in all, that normally competed at the NASA competition were unable to get in because NASA suddenly found out through their contractor and setting up things with the University of Central Florida that they didn't have a facility large enough to house all 50 teams that they wanted to get registered, that they had to cut it back to 37 teams or less. And then we suddenly found that we didn't make the cut to get into the competition, even though we were the grand co-champions last year. For some reason, we didn't get in. So what do you do with that when faced with this situation? Well, I asked the club to think about that, think of something positive they could do, and they decided that since we have a bunch of other teams that are in the same boat, but we'd like to continue to build and compete, why not run our own competition? So with the help of Hannah Albrecht and Conference Planning and Management at Iowa State University and our administration and the College of Engineering, particularly thanks to Joel Johnson with all the help that he's done for us in putting this together, we were able to create the CoSMiC, which is the acronym for the Collegiate Space Mining Challenge. And my hat's off to the entire team, Cardinal Space Mining Club, for the excellent work that they've done. And now thinking of that, I want to pull one of our students in here a minute.
This is Fallen for Robotics.
Oh, yeah.
Get him on. This is the team that's about to.
It's about to run. They're getting ready to run. Okay. They're just Colin. Yeah, I usually read their name tag when they come in here.
Yep.
Okay. Well, Colin, welcome.
Thank you. Thanks for having me.
I'll move the mic over here a little bit closer to you because people want to hear you more than they want to hear me. Right?
I wouldn't say that.
Oh, no, that's for sure. No, we're very excited to have you here as a
Excited
part
to
of
be
it.
here.
Great. So how long of a drive was it for you coming here?
We actually flew, so we shipped our rover before our flight here.
Oh, you didn't just stuff it in with your baggage to fly over here?
No, no. Yeah, we kept the rover fully intact. We put it in a crate and shipped it out with UPS.
Okay.
So
Excellent.
yeah,
And I hope our ISU materials receiving did a fine job of handling the crate for you and getting it in one piece.
so we shipped it to our Airbnb, and then
Oh, you did?
Yeah,
Airbnb.
yeah.
Okay.
And then we
I
took
think
it
I
out
heard
right
about
over there.
that. They left it out on the porch in the rain.
Yeah, in the
I hope it
rain.
was sealed well enough.
It was.
Good.
Yeah, we were kind of surprised at how well the wood resisted the
I am
water,
really,
so
yeah, I'm really impressed. You know how much rain we had that night that it got rained on?
I heard. Yeah.
3.5 inches plus.
Oh my gosh.
Yeah, my basement flooded in my house.
No
not,
way.
Not bad, but it was enough
But it was
to be
noticeable.
yeah, enough to be annoying. Thankfully, the
man.
basement was not finished yet.
Okay.
It's a new construction, but yeah, that certainly made for a tense week for me going into things. And
No, I bet.
I bet you were very happy to see that everything was essentially dry.
Absolutely. Yeah.
Good.
Yeah.
Well, that's a pretty nice looking robot. Tell me about your robot that you have there.
Yeah. So we started the project back in August of last year.
Yep.
This is part of our senior design competition or senior design class for the year.
Okay.
So
Is it a year-long class?
it is a
then?
year-long class.
Okay.
So,
How many members in the team then?
so we have two 5-people mechanical teams and then one electrical computer engineering team.
Oh, I heard about
So-
that. You had to work with the Sparkies on collaborating on this whole thing between the Crankies and the Sparkies. So to speak.
Yeah,
That's my
the Crankies and
nicknames for the
Sparkies.
yeah.
I think
for
I overheard a
mechanical-
little bit.
Yeah, mechanicals and electrical computer engineers. We don't always talk the same language, do we?
No, not at
No,
all.
no. That makes for some fun and making things work. But
Yeah.
it looks like you had some good success on that all.
Yeah. I mean, it was definitely a learning process, learning to work with interdisciplinary groups, but over time that got a lot better, and then we got to where we are.
Yeah,
So,
learn how to interpret each other's language. So
Yeah,
to speak.
absolutely.
Yeah. Excellent.
Mhm.
So tell me about the robot itself. What are some of its key features?
Yeah, sure. So I guess we can split it up into two different subsystems. So we have our regolith handling section. I'll go with that first. So we have a bucket ladder excavation system
and then it has 1 degree of freedom. It's on a linear slide rail.
Okay.
We decided to go with 1 degree of freedom just because it's a little bit less complex and leaves.
I can
less-
certainly appreciate that.
Mhm.
We engineers, we're all about degrees of freedom. And,
Yeah.
And how many degrees of freedom in nature?
3,
6.
6.
Yeah, 6. You got your 3 degrees of translation.
Right. And then
rotation.
rotation.
Ah, you get
Yep,
it. Yeah,
yep,
good,
you're totally
good,
right.
good.
Yeah.
Yeah.
Brain
yeah.
fart.
So another technical term, people, that not everybody gets a chance to learn.
Right.
And we have a bunch of them in engineering.
Mhm.
We have to do that in order to amuse ourselves and stay sane and all the challenges that we have to put up with, right?
Right. No,
Yeah.
absolutely.
Yeah.
Yeah. Well, for the excavation system, we did a lot of research into the different archetypes
Yeah.
that's used in previous competitions. And we kind of narrowed down on 2 main ones. It was the bulldozer and
Okay.
the bucket ladder excavation system. And we
Okay.
decided to go with that.
What made you not do the bulldozer? What was the reasoning behind that?
Just after watching a lot of proof of life videos and competition videos, we just found that bucket ladder systems were more effective in general.
Yeah.
There were obviously teams that performed very well with the bulldozer, just like the last one.
Yep.
So it's in general, we found this one to be more promising.
Okay. And what about the collection and offload?
Yeah, so our hopper, we also did narrow down on 2 different designs. It was a simple unloading mechanism with some kind of linear actuator, and then
Kind of like a dump truck or something
Yeah,
like that.
exactly,
We
a
call
dump
that
truck.
a tilting hopper.
tilting hopper. Gotcha.
Yeah.
Okay. And then what you see in the back on our vehicle is a conveyor belt. So it's an active deposition tray. So that's what we went with. This also has actually no degrees of freedom. It doesn't
Yeah.
it doesn't have a pivoting point.
It
so-
doesn't need to move. It just runs her right out the back, doesn't it?
Yeah, absolutely.
Yeah. In ag equipment terms, they call that a live bottom.
A live bottom.
Yeah, because it has a flat belt on it, and the whole bottom's live, and whatever's in there is going out when it's turned on.
Right.
Yeah.
Absolutely.
How fast does it go out?
I guess you'll see in a minute. Not too
Yeah.
fast, because we don't want it to spew out dust or anything like that. We want
Yeah.
it to be kind of in a consistent pile.
Well,
So-
some fun facts over the years that we've been going to the competition. We've seen a few teams that have done different things. One team from Australia, when they had international teams at the competition at NASA at the visitor center, had a beautiful robot that it was a scoop system, and it would dump it into their hopper, and they had the light bottom, and that thing carried a beautiful arc of material right out of the hopper and right into the deposit bin,
Oh wow.
just the right amount. And then a few runs later, another team came, the same sort of system, but they obviously hadn't done any testing, because when they turned the conveyor on, all the material cleared the hop or the depository and went right out the back of the arena.
Oh, no.
So,
Yeah, that's where testing comes into play.
yeah,
for
that's
sure.
where, well, a little bit of engineering can figure that out too, you know.
Yeah, no,
You
you're totally
use
right.
physics, you can calculate the arc of movement that
Right.
the material will go on,
Hmm.
provided you know how much gravity you're working with.
Right.
Yeah,
Yeah.
yeah.
Yeah, obviously if you're on the moon in this case, it would just
Yeah,
You'd
it would
want
go a
it to
lot
go a lot-
farther. Yeah,
for
yeah,
sure.
it certainly would. You know what the difference in gravity between the Earth and the Moon is?
I feel like I knew it at one point.
Yeah, it's about 1/16.
1/16. Okay.
Yeah,
Yeah,
So-
that's a very big difference for sure.
that's a huge difference. That's why the astronauts had to learn how to walk on the moon.
Hmm. Yeah.
And it's kind of fun to see how they did that. They actually hung them on trapezes sideways, and then they had to walk on these surfaces at a large angle and learn how to walk,
Oh,
so
wow.
that we'd only have 1/16 of the downforce to work with.
Right.
And even with that training, some of them still wound up falling on the moon, and then getting back up in those spacesuits was a real challenge
Yeah,
as
those
well.
huge bulky spacesuits.
If you do some look on YouTube and some of the moonwalks, you can find some of that footage where some of them tripped and yeah.
Oh man, that
Well,
must have been fun though.
Oh,
Mm.
yeah, I'm sure it is. One of our Iowa State alum, Clayton Anderson, is an astronaut, retired,
Okay.
and he comes teaches a space camp here at Iowa State. And I asked him one time about being in space, And what is that like? And he said the interesting thing is, insulated as spacesuits are, and they have a thermal suit that they put on, you can still feel the heat and the cold, and they're extreme in space because there's no atmosphere. It's
Right.
a vacuum.
Mhm.
And the sun side of your suit is getting like 300 degrees Fahrenheit hot, or 400
Really?
degrees, yes.
Oh, wow.
And the shadow side of your suit is like minus 100 degrees below zero.
Wow.
And he said you can feel that to the suit. Now it insulates you so you don't feel all of it, but you can feel that heat, you can feel that cold when you're in space. And
Yeah.
it really makes for an interesting experience being up there.
Right.
And then the International Space Station, I asked him, what's that like? And he says, well, it's interesting because when you first get on there, you smell a lot of hot electronics or burnt smell. But you get used to it after a while because the air is highly ionized in the International Space Station. Very interesting. And of course, on the moon, you don't have to worry about it because there's no atmosphere at all. So,
Right.
yeah. So you want to make sure you have your spacesuit on.
Yeah, absolutely.
Yeah. So it looks like we got another 7 minutes here to go, maybe, before they're ready to go.
Yeah.
So. Tell me about the drive system on those wheels. What do you have on there for like motors and gearboxes, and how big are the wheels? And
Yeah. So we went with Kraken motors. They're super popular in FRC competitions.
that
and,
they are. We've been using them as well.
Yeah, and
Yeah.
2 of our team leads have a lot of robotics experience. One of our team leads is actually a high school robotics coach, and
Oh,
he's been in
really?
the field for about 9 years now. So
Oh, wow.
yeah,
Okay.
lots of experience on that side of things.
Yeah. So what do you have coupled with the Kraken motors to drive those wheels?
Like the battery system.
No,
and
the gearboxes.
Oh, the gearbox. Yeah,
Because I'm
so
sure the Krakens aren't driving those motors directly.
yeah, no, absolutely.
You engage that motor in that big a wheel, and you are out of here.
Yeah. Well, we have on each side there's 4 motors total, 2 on
Yeah.
each side, and then
Yep.
a 4-stage gearbox on
Ah,
each side.
4-stage gearbox. So it's
Four-stage,
a
yeah.
planetary. Do you know who manufactured it?
Uh,
How big is it, the gearbox? Can you tell me in either centimeters or
I
inches?
want to say around 6 inches high and
Okay.
4 inches wide.
Sounds like a sizable chunk of metal.
It's a very sizable chunk of metal.
Yeah.
And then the wheels are chain driven with the
Oh,
sprockets.
Okay, so you got some chain and sprockets in there to
Mhm.
drive the wheels. So
Yep.
what's your top speed on the robot, you think?
Around 3 feet per second.
3 feet per second? Okay.
I think that was the calculation.
That's about a yard.
Yeah.
A yard a 2nd. A little under a meter per second.
Yeah. But
So-
we will be running it a little bit slower just for
That's your top speed.
yeah.
Yeah.
Mhm.
Yeah.
We definitely don't want to be running it at top speed, especially with the latency. on
Well,
live
given that
feeds.
this arena is 16 feet wide and 18 feet long,
Mhm.
at 3 feet per second, you're covering the whole arena pretty short order
Yeah,
at
absolutely.
that speed, definitely.
Mhm.
Yeah, that's one of the challenges here with doing this sort of thing.
Absolutely.
Okay, the mission control team is stepped out. I think maybe they're having issues with getting connected. With the laptop there? Okay. Just been advised that the mission control team is going to go down by the arena and run it from the laptop there. They're walking by, heading off into that corner. We have the mission control room is in the southwest corner of the building, and the competition arena is in the northeast corner of the building, separated by about 200 feet distance and tons of concrete and cement blocks. So sometimes if you can't get the Ethernet to work quite right, you can have some problems with getting connected to the robot. As you could well imagine, it's an even bigger challenge when you're separated by about 290,000 miles of space between
Right.
the Earth and the Moon.
Mhm.
And here's a fun little fact that while we're waiting for them to get set up, I do a demonstration of space, getting people to understand just exactly the distance in there. So for fun, I've got 3 balls. I have a ping pong ball, a tennis ball, and a softball. And the softball is my Earth, And as I tell the students, this is Earth, and my ping pong ball is the moon. And that's the relative size difference between the two from a ratio standpoint. And then I asked them, given the diameter of the Earth, the diameter of this ping pong, how far apart do you think they are scale-wise in this model? And how far apart would you think they would be, Colin?
Maybe from this pillar to the end of the room over
Oh, the
there?
end of the room over there?
Or
Well,
maybe even from
that's a good guess, but you would be wrong. And this is the surprising thing about it, because they've been talking about, well, let's go to Mars. We should go to Mars. They're actually going to be about 12 feet apart.
Oh.
On this model, the softball Earth, ping pong ball moon, going to be about 12 feet apart. That's how close the moon is to the Earth.
Wow.
Yeah.
I'm not really
Now,
sure.
the tennis ball is Mars. And this is where things get really interesting. How far away do you think Mars is at its closest point to the Earth? How far away do you think it is?
I would assume it to be like exponentially farther.
Well, it will be quite a bit farther, yes. But how far do you think that is?
Maybe from
From that wall over there?
that wall over to that wall?
No, that wall. Well, you would be wrong again. At its closest point, the distance between that softball and that tennis ball is going to be 1/4 of a mile.
Wow.
And at its farthest point apart, it's going to be 6,000 feet away, over a mile.
Wow.
And so when you think about going to the moon and going to Mars, that is the big challenge that we have in space travel. Now, here's another fun thing. Pluto, which we recently had the New Horizon fly by. But it's amazing to think, because that space mission, what's that? Oh, robots moving. Okay, here we go. They're ready to go. I'll come back to that later about Pluto, because that's another fun one. Okay, is he supposed to be digging there? It's a practice run. Okay, so you're gonna let him get away with that. Yeah, okay. Yeah, it's a good test of the dig. Yeah, it's doing quite nicely.
Yeah.
Yeah. Nice motation on the robot.
Mhm.
I was talking earlier, Caterpillar says the most efficient way to do mining operations is to go straight out and go straight back. And it looks like you're set up well for that.
Yeah. That's kind of the main maneuver that we're going to be focusing on throughout this competition.
Yeah, do those wheels turn at all? They rotate, of course, but do they turn at all?
They don't turn physically.
So how do you turn the robot?
Just I guess using opposite speeds on opposite sides.
Opposite directions?
Opposite directions.
What they call skid steering?
Skid steering.
Yeah,
There you
skid
go.
steering.
Yeah. So
Yeah,
yeah, exactly.
Yeah, don't they have a piece of equipment they call a skid steer?
That sounds very familiar.
Yeah, it does, doesn't it?
Uh-huh.
Yeah, the little skid steers with a bucket on it that is used in construction a lot and farming and stuff like that.
Okay.
Nowadays, they put tracks on them too.
Oh, okay.
Yeah, you see a lot of them with tracks on them instead of the four wheels.
Yeah.
They drive a lot nicer with the tracks on them than the four wheels. They
Like you're talking about like the treads with
yeah.
yeah.
Oh
okay.
yeah.
Gotcha.
The rubber treads. Yeah. It's interesting how technology changes things. I'm always teasing the NASA engineers. Why don't you use tracks on your robot? It'd drive a lot smoother. But they say no, I won't do that.
No.
Because they're scared about weight and reliability. Oh, that's really doing a nice job of picking up material too.
Yeah.
That get you excited?
It does. Very
Yeah.
excited.
Yeah. When you see things working as well as you want them to.
Yeah, we did a lot of beach testing throughout this past year, and we've been generally very successful with that. So we were kind of hoping for the same results.
Yeah, some of your
competition.
teammates showed me some of the piles of material
Yeah.
that you couldn't see the robot behind the pile.
Yeah.
It was so big. That's pretty
It was.
impressive.
Yeah.
Yeah. So how many pounds of material do you think your robot can dig up in an hour's time?
In an hour's time.
Yeah. Because we're thinking
Oh.
of space here. You're going to go to the moon and mine.
Yeah, that's tough to say.
Yeah. I'll give you an idea. One of our robots back in 2014 wound up mining 1,000 pounds of material in 40 minutes.
1,000 pounds. I don't know.
1,000 pounds.
Should we test that out with this rover?
I think you could do better.
Really?
At the rate that you're collecting, I think you could do better.
Yeah.
This is very impressive.
Thank you.
The annoying thing about it is that West Virginia was there too for that same competition, and they wound up digging 1,040 pounds.
Wow.
Yeah,
10,040
40 pounds between the two of us after 40 minutes of digging. So we took second in mining. We took first in design. But my hat's off to West Virginia. They had a very robust little system using a bucket and a hopper much like yours for unloading
With the
material.
conveyor in the back.
Conveyor in the back.
Gotcha.
They would take it, scoop it up, bring the bucket all the way over the top of the robot, dump it into the hopper, and once they had the hopper full, they'd back it up and dump it out. We had a tilting hopper and that
okay.
tilting hopper also. The bucket ladder was attached to the hopper, so the bucket ladder
Interesting.
digging depth was controlled by the same actuators that tilted the hopper to dump it out.
So when you dump it out, the excavation system tilts as well.
Tilts right along with it.
Okay.
And that creates for some interesting moments because you got to make sure you know where your CG's at because you could face plant the robot too when you go to dump
absolutely.
site. You got to have
Tilts it too
something to
far.
lean against when we dump. Otherwise, the robot's just going to go right on over the load. And,
Yeah, absolutely.
Yeah. Later years, we kind of fixed that in the design, making sure the CG never shifted too far, and it by strategic placement of the motors,
Right.
to keep the CG where we wanted it. So
Yeah, we tried to keep our CG relatively middle, as you can see with the mostly symmetrical design.
yeah, now he's doing a little dancing there. It looked like, or just trying to turn it.
Yeah, so what that is, once you get to the end of how much you're depositing, there's a little bit left over on the sides of the deposition bin.
Oh.
So what they're trying to do is shake it around a little bit, try to break it up, and then,
Oh, cool.
and then convey that out.
Yeah, do a little dancing move to get the
Oh,
load
yeah.
leveled out. That's pretty cute.
Yeah, there it goes again.
Yeah,
Little shake.
little shake.
Mm-hmm.
I think there's a country song by that name too.
Little shake.
A little
Huh?
shake. Yeah.
I wouldn't be surprised.
Yeah, looks like he's just dumping the material out right there.
Yeah.
Oh, that's very good. Look well. Yeah. So, so did you guys compete at NASA last year? I'm pretty sure you did.
We did. We
Yeah.
did.
How'd you do?
So I believe the rover didn't work on arrival, so we weren't actually able to compete.
Yeah.
But when we were when the previous year's team was testing it, it seemed to work perfectly well on the beach.
Okay.
We did make some improvements based on last year's design, such as the wheels. As you can see, they're kind of large.
Yeah. Well, that
But,
gives you more contact area, doesn't
Yeah,
it?
absolutely. That was
Yeah.
that was the goal.
There's nothing like getting stuck in the arena, is there?
Absolutely.
No, it's not fun.
Mhm.
That's the main reason we always use tracks. It's hard to get stuck with tracks, but
Okay.
I still don't have NASA convinced to use tracks on their rovers. Yeah. Their main complaint is they say, well, tracks are heavy, and I always like to tell them, well, tracks aren't heavy. It's just that the vehicles the tracks are on are heavy.
Yeah. Design itself.
Yeah.
Yeah.
Well, it's all about moving Earth and
Right.
being productive, and in order to get a lot of power to move material, you got to have a lot of thrust to do it. If you're using a bucket or a blade or something like that.
Yeah.
Bucket ladders like this are a little easier and take less power. But there is limitations as to what they can do as well. But depending on your mission scope, they work quite well for this, don't they?
They do. They do.
Yeah.
It's a simple yet effective design.
Now, do you have a Falcon 500 on the bucket ladder as well?
Yeah. So you can't really see it. It's on the other side.
Yeah,
but that's what's
he's
driving.
pointing at the robot for me as to where it is. You and the audience can't see it, but that's okay. But yeah, it's a very nice design that you have there. It's fun to have the clear sides in the hopper so you can kind of see how much you've got.
Oh yeah, absolutely.
Yeah.
The polycarb
Yeah.
sides. Yeah. And it also takes out a little bit of the weight that would have been.
Yeah, if you used aluminum sides or something like that.
Mhm.
Yeah. Yeah. We one year we stuck a GoPro on the side of a robot and so that we could see just exactly how the material was coming off the bucket ladder.
Oh, wow.
Because it was in an enclosed kind of enclosed chamber, but it had clear sides on it. And we played the video back afterwards and noticed that the whole background picture all of a sudden rotated almost vertical. And when we went back and checked the video, because we hadn't been watching the robot, we discovered that we drove through a crater and the robot came out almost vertical out of the crater and then came crashing back down again.
Oh my gosh.
Yeah, it was pretty amazing, and continued on to do its job. And that was the year we were driving autonomously, and
Okay.
so once you hit the go button, you really don't have control of what the robot's going to do. It's on
Right.
its own.
Absolutely.
And that particular year, we were not worried about obstacle avoidance. We had the robot designed; it could drive over anything that was in the arena, rocks or craters, and did all of it quite well.
And that used tracks, I
Yeah,
assume?
tracks.
Okay.
Yeah.
Gotcha.
Yeah, it had designed a high ground clearance to it because there was enough height in the size box that we could get away with
Oh.
having the height underneath the robot. But
Okay.
now with the 3/4 meter size box for height, you no longer could afford to have that big high clearance
Right.
on the ground clearance if you want to have enough volume in the hopper to make
Yeah.
it worthwhile to collect things.
Absolutely.
Well, Colin, thank you for sitting in with us on this run. Looks like it
Yeah.
was a very good run.
Thank you for having me.
Report back to me later and let me know
I
how
will
much you
do.
guys did.
Yeah, sounds good.
Okay. And again, thank you for being here at the CoSMiC competition.
Thank you for hosting us.
Yeah, it's our pleasure.
Super exciting.
Okay. Okay, so up next will be the New Mexico Tech minor 49ers doing their actual competition run. And so we hope to see something exciting there with them. Okay, and we're back. New Mexico Tech is set up for their competition run in the arena, and they will be taking off here pretty soon. I got the team sitting here uh, ready to watch, and everybody's got their fingers crossed, including me, that we have a good run out of this. Okay, so we got the 10-minute countdown for auto connection with a robot started. Our arena crew's doing a little more smoothing of the arena. That material gets pretty compacted as we walk over it, run over it. We try to keep fairly consistent conditions in the arena. It gets too hard packed, it gets very hard to dig up. It gets too loose, it gets very easy to get stuck. So they do a good job of trying to keep things in good condition. The one thing that you don't see in this arena that you see in the NASA competitions is craters. You know, we haven't dug any craters in there. Figured it's hard enough just getting the robots going. So the team obviously didn't think that craters were too important, but they can kind of make things fun from time to time. But we don't have any craters in here today. Just rocks to have to drive around or over or whatever is the design of your robot. The biggest risk driving over a rock, of course, is getting hung up on the rock and then not being able to move off of it. But again, the whole intent here is to build a berm. The biggest berm wins in this competition. And so they'll maneuver from their start area through the obstacle area into the mining area. And there's a couple rocks in the mining area that they have to work around. They can choose to move the rocks. They can choose to bury the rocks if they want, or they can just work around them, depending on what the mission control drivers decide to do. You can see the blue box that's there on the lower left. That's the area where they deposit material to build their berm. We have a LiDAR unit donated from CoSMiC Industries. They are located out of Germany. They specialize in security equipment and LiDAR-based type instrumentations. LiDAR is an acronym, stands for laser direction and ranging, and that's used quite a bit as well in autonomous operations. Allows the vehicle to see obstacles and to see terrain and make a decision based on programming as to what direction it should go. In this case, we're using the LiDAR for measuring the size of the berm that's deposited. And we have done some tests, and it's surprisingly accurate. We put a package of Oreos in the arena just to see if it would pick up the Oreos, and it did. And it gave us a very accurate accounting as to the size of the package and how many Oreos were in the package as well. It was pretty interesting. And then my understanding is the Oreos disappeared. I wonder where they went. So we got about 6 minutes to go here. So again, this is the team for New Mexico Tech. The Miner 49ers is the team name. You could describe the robot as a skid steer style robotic mining apparatus. It's got a front bucket with 4 wheels. and it uses opposite direction motion in order to create rotation on the robot to get it to turn. Not a very efficient way to turn, but when all you're doing is straight back and forth type operations, you can take a little efficiency in the maneuvering if you can gain efficiency or simplicity in the system for operation. And simplicity and toughness are certainly a key part of what comes together with doing space mining. So we got 5 minutes and countdown here. Fortunately, when it hits 0, there'll be no ignition of rockets or anything like that. Shouldn't see. The last thing we want to see in the arena here is any sort of fire. That's not what we want to see here. We want to just see nice operation. And the other crazy thing, we don't want to see clouds of dust either. The whole idea is that you have dust-free operation, very efficient, very smooth, and picking up material and depositing it. Again, I want to give special thanks to our sponsors that made this possible, such as Caterpillar and SICK, who I've mentioned already, Danfoss Corporation here in Ames, Iowa, Collins Aerospace, who donated money to help make this possible. We also have Mechdyne and Iowa Space Grant Consortium supports us as well, and the College of Engineering. Now it'll be interesting to see what they decide to do here when they get down to the 0 and the competition run starts. Do they take time to turn the robot around? Do they just back it out? And once they get into the construction area, mining area, do they go straight back and forth? Do they maneuver around the 2 rocks that we have in there? So we'll see what sort of strategies they choose to do. The teams are allowed to, in this, if they want to move the rock out of the way, they can. There's no penalty for moving a rock. If they want to pick up the rock and dump it into the berm area, they're welcome to do that too, because that immediately adds to the volume of the burn. So it'll be interesting to see what the Miner 49er machine decides to do here as they get ready for the competition run. Repositioning the camera, okay. We give the teams options to have camera motion or pointing directions altered so they can see what's going on based on which cameras they want to use. Okay, and they're getting the arena closed up, ready to go. We got less than a minute to go. Again, this arena was designed using SolidWorks by our Cardinal Space Mining Club team, and they constructed it over the course of this week. They started on Friday, finished up on Tuesday. Regolith was loaded in. We had planned for 2 hours of loading, but thanks to ISU facilities and management, they had that arena loaded up in about 10 minutes. Oh, they're going to plug in? Okay, so they're having issues with connecting. So they're going to go to the arena and plug in over there. Apparently they're having problems with their Ethernet cord between the corners of the rooms. Yeah. In the past, NASA would say, tough, that's your problem, not ours. And that's not our philosophy here. We will do whatever we can to accommodate the team so they can get a run in. So we're going to go ahead and let them move over to close to the arena and plug in there and be ready to go. So Anna, how are things going in the pit?
Pretty good.
Pretty good. How,
We're gonna have a substitution here later though.
okay, tell me about it.
So we had a bit of an issue with one of our cables.
Okay.
And the team from Arkansas was having issues connecting. It turns out to be an issue on our end with our Ethernet cable.
Okay.
So we're replacing that, and we're giving them a makeup run at 3.
Okay.
So after this one.
Okay.
Yeah.
Excellent. So having a good time so far?
Oh yeah, always.
Always, yes. Anna's been one of our club members. How long you been with the club?
This is my 5th year.
5th year.
Mm-hmm.
But you're now graduated and off working in the real world?
Oh yeah, still job hunting. But
Still job hunting. Okay.
graduated.
Yes. Well, we certainly love having you around helping us out with everything here.
Yeah, it's been a ton of fun. It's been a great event so far. I'm really glad to be a part of it.
Excellent. So, and where are you from for people out there that don't know?
I'm from Marion, Iowa.
Marion, Iowa. I know right where that's at.
Yeah, right by Cedar Rapids.
Right by Cedar Rapids.
Mhm.
Excellent. So, well, I hope you find that magical first job.
Yes, I
So-
hope so too.
Should be good stuff. All right. Well, good luck with the next run, and I hope we can get that Ethernet fixed soon. Remember the trophies they had last year at NASA? Oh, they're great big tall sports trophies. We never received the grand prize trophy yet. Yeah, they gave it to us and then took it away, and we never got one back. We have our mining trophy down in our build area, but we've never seen the grand prize trophy yet. It's probably sitting in Alabama. Okay, well, they should get hooked up here pretty soon. As soon as they get going, then the competition counter will start. And our crew here will continue working on the Ethernet connection between Mission Control and the arena so we can get that sorted out. And we'll have a substitution. Illinois Robotics is going to run at 3, I believe it is. So they get a chance to get their robot going since we couldn't get them connected earlier, probably due to our end and not theirs. As mentioned, we're trying to be as flexible as possible because this is the first time we put on a competition of this sort. So as we discover our technical issues, we'll work through them, get them resolved, and during the meantime, allow the teams to do what they came here to do, and hopefully have very successful runs in the arena. robot to the network. Any news from them? Okay. Yeah. Well, that's what we get with working with computers. Yeah. You're starting it now? Okay. All right, so they're starting their run now. Did they get connection established with the robot? Okay, so they're going to give them 5 minutes to get connected into this 30-minute run, and if they don't, then they're going to move on to the next team. Fingers crossed. Is the long wait if you can't get your robot connected as time ticks away. And every minute feels like an hour as you're trying to get your robot connected. We've certainly had issues with this in the past, even with the Iowa State team. I remember well, in 2015, we thought we had a very good robot because we just did a modification to our 2014 robot and was actually expecting it to collect 25% more material than the 2014 robot did. And then we got into the first run of the arena and it wouldn't connect. And when we finally got it connected, we gave the command for it to lift the hopper to get ready to run, and the actuators, instead of going the same direction, went in the opposite direction and broke the robot. And so we had to do a frame repair to the robot, and on the second run, we couldn't get connected at all. So that year was very much a heartbreak for us. And these are the sorts of things that make this competition very hard. Hopefully we get a connection here soon, and Miner 49er will be on its way. Okay. What's going on? Sounds good. Yeah, I'd rather have the teams running rather than doing the NASA thing. So, okay. Did they get running?
They did get running, at least they get it to a small amount after we get kill the DQ.
Oh, okay.
They may disconnect it because they're going to move back to the control room, but they said no to say they're going to get reconnected and set up.
Okay. Are they going to then reset the time for the competition run? No,
Started.
it's already started.
Yeah.
Okay.
So we gave them.
Yeah. Okay. So it looks like what's happening here is we've given them a chance to move close to the arena. They still couldn't get hooked up and maintain a hookup. So this competition run for New Mexico Tech is going to be a scratch. But we are going to do a change in our mission control setup and move it closer to the... Oh, they're not going to scratch it yet. So we'll give them another run chance. That's good. I liked hearing that. But we're gonna relocate mission control, is my understanding, and move it closer so we can get over these technical difficulties with our mission control room and continue the runs. So just hang tight with us as we work through our technical difficulties. As I said, this is the first time we've been doing this at Iowa State University. This is an entirely student-run operation. Our thanks to our corporate sponsors for helping us do this, and for all the teams that coming and participating, and everything that they work through. And we will get these runs going here in better fashion here as we proceed through this afternoon. We still have 2 full days of runs to get everything in, and I'm confident we'll get every team through this for good runs, so they can figure out how capable the robots are. So we're just letting the competition timer run here while we get things adjusted and set up. My team is scrambling. They're doing their work with getting some logistics taken care of. And I'll be back on as soon as I get some more information. Okay, we got motion out of the New Mexico Tech just as the team walked away out of the arena or the stepatorium here. Now all of a sudden they are running, and we'll see what sort of ground they can make up here, as it's moving very nicely. It has nice maneuverability. We'll see as it gets into the okay, it's into the mining area. We watched this thing earlier do some scooping, and it was very efficient. Did a nice job with it, with their bucket, so we'll see how they do. Okay, he's kind of out of my picture here because I can't quite see what he's doing, but I know he's getting his bucket position. Okay, he's got to pick up a load of dirt. That's good. And he's going to maneuver around a rock. Oh, watch out for that rock. This vehicle does appear to be very maneuverable, and it carries a fairly good quantity of material in its bucket without tipping over. Very impressive little machine, very efficient. Okay, here's their first load. It figures path back through the construction area. Maybe you can get that rock move, get it out of his way. Looks like he's getting ready to do just that with one of the other rocks. Going to try to push it into the, maybe not. Nice thing about these bucket systems like this is you can use them either as a scoop or a blade. And you can push material, get it to engage down, get a good pickup. Looks like he's doing a little bit of both. Now he's digging in a little bit more. We've seen this robot get close to being stuck and then able to drive itself out of there. The wheels have been very effective on this one. And now all of a sudden we seem to stop moving. Sometimes what can happen here is you can have everything working really nice, then all of a sudden communications drops out. And then you got get reconnected again. And nope, he's got it. It's, oh, well, now this is interesting. We've seen this before. You get greedy and you get a lot of material in your bucket. Next thing you know, you can't get the back end of your robot down. But it's doing quite nicely. Oh, we got the rock this time. That's why it tilted. Very good. That was a good run. Now he can dig and not have to deal with the rock. And go about making his regolith pile. One of the things we found over time is that the angle that you want to get your hopper or your scoop or anything that you're dumping material out of, you want to get that to 50 degrees off horizontal, that is 50 degrees down, and then all the material will come out. If you don't get it there, if you get 45 or 40 or something less, not all the material will slide out. And that has to do with a thing called the angle of repose. If you were digging in sand, the material will roll right out for you. But on regolith like this, until you get that higher angle, the material just won't move. So doing a good job. Oh, he's going for a hard dig here. Okay. Motion on this robot is excellent. Okay. Well, that looks like a good scoop. Yeah. Okay, good dump out of that one. There's getting a pretty good pile build up here. This is excellent. You're going to keep working the same area. They can do that. We got over a foot of depth of material in here, so depending on how far he wants to go, they can't dig all the way to China, but he could get a good start. And now, as long as he doesn't back over that rock, right beside it. It's a fun little machine to watch. We've had a number of machine designs like this in the competition in the past, some more successful than others. I would say this is one of the more successful designs. The maneuverability is excellent. They're able to get enough traction out of their wheels with the weight of the robot to get a good bite with their scoop. It's not too wide. And so they can pick up just the right amount of material and get it deposited. Actuator speed is good. Sometimes you can have your drive systems too slow or too fast. So it's a matter of optimization. This one seems to have a very fluid and fast motion to it. He's got that scoop just about full. That's excellent. That's a good run right there. Good sortie. Looks like their communications dropped out again. Normally we get that, and he's back in. We've had this in the past too with our competition runs where we would have the communications constantly dropping out. And then we'd have to hook up back in, and would do that several times over the course of a run. It's just all part of robotic operation. Oh, another good scoop. Yeah, I see a lot of material in there. Well, we got 3 very good piles in there and a rock. Maybe that's a Charlie Brown moment right there. He got a rock. Maybe we could put the great pumpkin in there sometime too. Get extra points for harvesting the great pumpkin. Oh, very impressive little machine. Very good maneuverability. It's doing a very good job of regolith mechanics with getting material picked up. I know the arena workers are not going to be happy to have to put all that material back and rake it smooth again, but that's okay. That's what we're here for. Oh, nice, nice. Well, what they're doing is they're vying for a first place trophy here. I have one of the trophies sitting here on the table. That was designed by one of our club members, Mason Eck, who then went ahead and fabricated these. Very beautiful trophy. I think that any team that wins it will cherish putting it in their display case. Represents the spirit of the competition very well. Okay, it looks like we got 10 minutes left in their run. They're doing quite well for the time that they had. They're making good use of it. They're being very efficient. Just back and forth, not worrying about how deep a hole they're digging. They're just driving right out of that and depositing material. It's excellent. So looks like they're doing a little thinking what they're going to do next. Oftentimes too, we'll get in these competitions, mission control team will decide, okay, we've done this so far, what should be our next strategy? Do we want to shift where we're mining? Do we want to take a risk and move a rock? He's got a fair amount of material in that bucket yet, as we can see there. He's going to go ahead and dump that. Get that angle. There he goes. Okay, now he's got it all out of there. That's excellent. As you can tell by the way he's moving around, he's getting some pretty good holes dug in there. But this robot is doing a great job of driving it out. The biggest challenge is you go, think you have a good bite of the material, you move a little bit, and then you hit a bump, and all of a sudden your bucket's up out of the material. But he's got a very good scoop there. Oh. Now, Iowa State in its first demo run got a very good amount of material, even though they had technical difficulty with their demonstration run. But this team looks like they're going to give Lance 1 a good run for its money, even not having a full 30 minutes to do it in. Get their communication issues all sorted out. I think they're going to have a very good second run. This is going to be a team to watch. Another good bite. Oh, good. All right. Don't get yourself stuck, boys. There we go. It's got to be able to drive out of that. There he goes. We have seen it happen in the past too, where some robots drive in an obstacle and as they come out of it, they get the tilt too high and they wind up on their back. Uh, I don't think this machine has any sort of that sort of stability problem. So doing a very nice job of cleaving material and getting it deposited. And they pretty much filled up the whole size box with material. So now it's just a case of how high can they pile it. You can see what's called the angle of repose on this material. That is the angle it takes as it's dumped on this crushed ag lime. I hear some of the team members over there going, whoa, whoa, whoa. And that's because this material is loose now, and so it flows easily. And that creates some disadvantages, and it makes it hard to fill the volume of the arena. Oh, now he's got too much load in his bucket with the angle that he hit. This is one of the big issues in this is stability. Being able to keep your robot upright, not tip over, and not get stuck while mining. And the further you dig, the more uneven the construction area becomes, as we're seeing here as they're moving. And he puts the bucket up high, and now his CG is raised way up. And as he moves out of this hole, it'll be interesting to see how stable does a robot go with doing that. Okay, here we go. I'm really impressed with how well this robot turns using skid steer. The secret to a very maneuverable skid steer is weight balance and ratio between the width of the wheels and the wheelbase of the vehicle, so that when you do the opposite direction turning of wheels, that you can get the robot to respond. What's he doing here? He's going for the rock. See if he can nudge it. Ugh! Everybody over here is grunting for the robot. Watch it roll that rock. Oh, there you go. Roll it out of the way. Very nicely done. Yeah. Oh, I'm sure it is. Maybe I better watch on the other screen. Yeah. Yeah, live feed over here. Yeah. Wow. Yeah, I'm quite delayed on my computer. I was watching my computer. But yeah, very impressive run here by New Mexico Tech. That is, now he's going to nudge it in there. And they're allowed to do that. They can reshape that berm if they want to get as much the material inside the size box as they can. like another little nudge of material here. Oh, very good scoop. But yeah, it's all about balance. Sometimes you get too much, you got to get it offloaded quickly and then nudge it into place. There you go. Now, as impressive as this is here, what we're watching is you have to keep in mind that what Mission Control is doing there is they do have a time delay between what's actually happening in the arena and what they're seeing on their screens. And so this operator is doing an excellent job of dealing with that, understanding what his robot is capable of doing. Oh, a nice little wave. See if he's, and looks like they are done. Very impressive run by Minor 49ers. Let's hear it for them. Even with all the delay and communication issues, they've come through with an excellent run. Now the arena crew has to go move all that regolith back into place. Thanks, guys, for keeping them gainfully employed. Okay, who's up next? Okay. Ooh. Let me know what you find out on the scoring on that. Run, understanding how much volume of regolith is there within the size area. And as soon as I get numbers back from the arena judges, we'll let you know what New Mexico Tech did, the minor 49ers, with their wonderful little bucket skid steer system. And this machine worked very well. Very impressive maneuverability, very impressive digging capacity. It looked like the robot was optimized very well. Good range of motion, good speed on the actuators, just enough mass to be very effective in this material. And now that they got our arena all tore up, it's going to take us a little bit to get it reconditioned for the next run. I've been told that Illinois Robotics and Space will possibly be the next team to run, and we'll know more as we get closer to this and keep you up to date as to where we're at on that. Again, this is CoSMiC, the Collegiate Space Mining Challenge, coming to you from Iowa State University and the Student Innovation Center. I'm Jim Heisey. I'm the faculty advisor for the Cardinal Space Mining Club. Coming to you live from Ames, Iowa. Okay. So next up is going to be run as soon as the arena's ready to go will be the Razor Bots from the University of Arkansas. Okay, I'm going to go back live online, but not arena or separatorium. Yeah. Hey, we're gonna switch things up here a little bit for a while. We've got our pit area live on camera now for everyone to see. For those of you online that are watching the competition, you can see our teams in action. Competition runs today. Some very impressive runs in NASA as well. With depositing of material. I just had a chance earlier to watch University of Illinois Chicago do a very nice run and deposit a fair amount of material. But I'd like to, don't mind saying that New Mexico Tech here, the minor 49ers, I think actually did a better job on depositing material. They had a huge pile. So we're looking forward to seeing more of that here as we get through the teams. This is our first day. We are in the process at the moment of relocating mission control. We found our connection issue was somebody ran over our fiber optic line and we think broke it. And so now we got to move our connection a little closer to the arena and the hallway so that we have a good fiber optic line or a good Ethernet cable running between the mission control booth and the arena. So we'll get that set up. Everybody's moving the equipment right now, and we should be ready for the next run in about 10 minutes, 20 minutes, and going. During the meantime, enjoy the view of the pits. It looks like the picture is stalled on that. Is it live or is it just a photo? Some people are waving to folks back home. We have 11 guest teams here in our club from Iowa State University. We have 9 teams that are scheduled to run today. We're going to get through all of them before the day is done. During the meantime, the competition in Florida is running. This is their last day of their mining events. And they're just getting ready to do their innovation awards at the competition. Everybody is getting in the student education center there. I see a lot of familiar people in the pictures. We'll zoom in a little bit more. I know all of the teams here would have really loved to have been there, but alas, that can't happen for everyone because of limited availability of spaces.
Hello, teams. Who's ready for the Innovation Award? Who's really ready for the Innovation Award? Yeah. So kudos to Colony Crew for persevering. We are going to give away the Innovation Award. This is not the beginning of the final ceremony. The final ceremony needs a little bit more time for our judges to finalize the scores.
Looks like they're done with the competition runs at Kennedy Space Center. They're getting ready to give out the Innovation Award, but then the judges are still working on computing all of the scores to make the selection as to who are the award winners in the robotic mining. And I'll keep monitoring that today and report that online here as things proceed here. We always want to congratulate the teams that did make it into the NASA competition and did make the final 10 to be competing at the Kennedy Space Center. It's a great place to be, very exciting time. We hope to be there again next year doing that. So our pit area that you see here online, this is the atrium of Hall Hall. I am located in the Stepatorium at the Student Innovation Center. The arena, competition arena, is also in the Student Innovation Center in the space they call the outdoor storage area. It's a caged in area that has an overhang, so if there's any weather, we don't have to worry about it. Right now, we have a mild breeze and sunshine. We had some rain this morning, but it didn't bother our operations at all. And so we had very good success. NASA right now is in the process of giving their innovation award to one team who showed the most unique and inventive design.
We have a special prize, a flag that was flown in space on the last Artemis mission, and we have two of them. We have to pick two innovation prize winners because we have two flags. Not a problem. We'll pick two.
Very cool.
Flown aboard the Artemis 1 mission, which launched on November 16th. Took a bucket drum. Took a bucket drum and they made a big bucket drum. Then they raised and lowered the bucket drum, which is really big. Making it work with a different right size. But it was just different. And if you're innovative and different, that's what this prize is all about.
Very nice prize. It's not a big flag like you would think of a flag. It's a little flag. It looks like about 4 inches by 6 inches. Has the Artemis mission logo on it. Nonetheless, it's mounted on a very nice plaque denoting
University of Illinois in Chicago.
University of Illinois in Chicago received the second innovation award. So congratulations to both teams for very good engineering.
It's not a first and a second, but both equal. both get the innovation prize because we have two flags that are flown in space. These are very special flags. So congratulations to you. Now, you may have noticed that last year they won the Innovation Award too with a similar design, so you may say, well, can you win innovation 2 years in a row? Well, then it's relative to the other team. They were still more innovative than most of the other teams. But you saw the way that robot digs itself into the ground and then gets out again. It's pretty amazing. So congratulations to the team.
The University of Illinois Chicago, their innovation that they did, they have a very unique digging system. They have a hopper that lowers down to the ground, but they have a very powerful vibrator that then forces using vibration, forces the hopper down into the soil, and they can pick up a significant amount of material.
So don't go too far.
And then that uses the vibrator and a slight tilt to shake the material back out of the hopper into the dump area. So, and shortly, NASA competition in Florida will have their final awards ceremony, and I'll read off that as information becomes available on that. So stay tuned. We'll give you information on ours as well as we get ready to run. We just about got mission control ready to go again. They're getting everything set up. You can see pictures from our arena and from our pit area. Pit area's feed is dormant again. So we'll work through that. Start in about 13 minutes. We'll be keeping an eye on that. It's 3:37 here, and we've got next up, University of Arkansas Razorbots. Looks like they're going to be running in the arena, and we promised to get through the team scheduled for today on their runs, and we'll keep you posted as how things are going here. We had a very good run by Michigan Tech or New Mexico Tech, deposited a lot of material. Been watching the runs at NASA as well. And I like to say that we're having some very good success here as well. Okay. Yeah, we can do that tomorrow. But we're just getting ready for another lab. Also monitoring the NASA competition. Yes, they're getting ready to do their final award ceremony. And so I'm talking live to the people online right now. This is okay. This is part of what we do. It's just a very loose, easy. For those of you online listening, I have the Student Innovation Director, Jim Oliver here, Dr. Jim Oliver with me. Say hi, Jim.
Hello, everyone.
I get a chance to talk to him more tomorrow, so we'll talk more about the great things that we have here in the Student Innovation Center.
Sounds
And
great.
I want to thank you so much for giving us the opportunity to do this here.
It's a fantastic
this week.
event. It's going great so far. Really well organized, and great job, Jim.
Thank
Yeah.
you. Well, thanks to the students. They
Yeah.
did all the work. I told them I don't have any bandwidth this semester. I'm just way too busy. It's all got to be on you guys. And they said, well, okay, Mr. Heisey,
Yeah.
but you're going to have to be the MC.
Oh. And your voice is holding up pretty well. for the
Yeah,
full
doing
day.
okay.
Yeah,
Well,
yeah.
I'm used to lecturing long times, so as long as I got my liquid with me to keep the old voice
All
box
right.
going, I'll do all right.
So yeah, let's do it tomorrow. Let's sit down.
Yeah,
and,
let's do that.
Talk about
We
it.
got a lot of fun things to do,
Awesome.
and looking forward to expanding the lunar test
Yep,
chamber.
yep. We just talked about that in our management meeting.
Yeah,
Yep, yep.
and maybe doing more of this in the future.
yep.
Caterpillar asked me once, will I do this next year? And I flat out said no,
Mhm.
because I want the club to compete. But if things change in that, I know we can do it.
Yep, yep.
And it'd be fun to see where it goes from here.
Yep. No, it's a great event, and everything's working like clockwork. So congrats, and
Tell the
yeah.
students,
yeah,
it's
yeah,
all
no,
on them.
They did a great job setting it up and dealing with all the administration, the
Yeah.
safety guys, and all of that. stuff.
All of
Yeah,
that, a lot of work, and
Yeah.
thanks to Hannah and CPM for helping us out, and the folks at facilities.
Yep, yep.
They told us it would take 2 hours to load the material in the arena, and it
Uh-huh.
took them 10 minutes.
Wow.
Next up will be the Razorbots of University of Arkansas, and in about 3 or 4 minutes, the NASA final awards ceremony will be going on at the Kennedy Space Center Student Education Center, where the other 10 teams that made it through the UCF competition have been competing through today, and we'll find out who will be the winner of the mining competition there, and we'll get to figure out how much they mined and compare that to what our team's doing here. And who will be the grand prize winner there, and on Saturday we'll find out who will be the grand prize winner here. Reason we're doing this competition is because NASA, in putting this competition together in Florida, ran into some logistical issues, and they could not hold all 50 teams there at the University of Central Florida, so they had to cut the field down to 37. And so 13 teams, they utilized the project management plan submitted, and while we had our plan in, when they printed it off, it wound up being 6 pages rather than the required 5, and that happened to several other teams as well. And so as a result, 5 of the top 6 competing teams from last year did not get into the competition. That includes Iowa State. Of course, we were very disappointed about that. But rather than take a negative approach, we decided to take a positive approach, because for all of these teams that were involved, to not be able to go to competition really disrupts their opportunity to, whether it be a senior design class or a student organization club, getting sponsorship, getting experience. We decided we need to hold a competition here if we have the capability to do so. So thanks to our sponsors such as Caterpillar, Iowa Space Grant Consortium, SEEK, Sensor Intelligence, Danfoss Corporation, Mechdyne, Collins Aerospace, and the Iowa Space Grant Consortium and the College of Engineering for supporting us and giving us the financial means with which to put this competition together. And so we've set up our arena here, designed and built by the Cardinal Space Mining Club in the outdoor storage facility area of the Student Innovation Center. We've got 22 tons of crushed lime rock in the arena, and that is what we're using as a lunar simulant. That has been used by NASA and by the University of Alabama in the past as lunar simulant. It's a little easier to work with than NASA's BP-1, which I have examples here with me at my desk. And our material at Iowa State that we use to test in is very similar to NASA's BP-1, but we did some research on that, and we found out that to buy the BP-1, to get it from Arizona, we were going to have to spend $300 per 100-kilogram bag, and for the amount that we needed to fill our lunar test chamber, I was looking at $250,000, $250,000 to fill our arena with BP-1. Well, we don't have that sort of budget, so we looked at, well, can we find a material that behaves the same? So I had some students do some research, and we came up with what we call ISU-1. And ISU-1 looks just like BP-1. It behaves just like BP-1. It's about the same weight as BP-1. Has the same angle of repose as BP-1, the same compaction rate. But what it's made of, BP-1, is basaltic mining tailing. So it comes from an ancient lava flow. It's mainly basaltic rock and very small particles. Particle size about 0.05 millimeters in size on up to about 4 millimeters. The ISU-1 material is made out of 5 parts Portland cement, 3 parts coal fly ash, 1 part fine sand. So we have particulate size of 0.005 millimeters on up to 2 millimeters in size. And same densities, about 1.5 to 1.8 kilograms per liter. Angle of repose 57 degrees versus BP-1 of about 67 degrees, so it's pretty close. Compaction rates, loose, it's about 1.3 kilograms per liter. Compacted, it's about 1.6, close to 1.7. BP-1 is about 1.3 loose to 1.8 compacted. And we find it to be just as abrasive, just as nasty to work in as a BP-1. And so we have a number of teams across the country here who compete in the NASA competition that ask to come to Iowa State and test their robots in our lunar test chamber located here in the fantastic Student Innovation Center. And we hope in the near future here to actually expand that chamber so that we can do more testing in the future as we go forward here with preparing the next generation of engineers for the new industry that will occur in the next decades, which will be space mining, resource collection from outer space by either mining material on the moon or Mars, or going to the asteroid belt even and collecting materials. There's several companies out there that are working on that right now, have what they call 30-year plans for how they're going to go to the asteroid belt and collect vital resources for space exploration and travel and the support of space stations, because it costs quite a bit of material and cost just to get supplies up to the International Space Station, because space flight, the Earth is has what's called a very large gravity well given its mass, and it takes quite a bit of fuel and energy to get cargo up to the space station. But if we could take some of those needs and instead of collecting them on the Earth and taking it up to the space station, and instead collect them in space, like from an asteroid or from the moon, which takes a lot less energy to get away from than the Earth, then it's a very easy space flight back to the International Space Station to drop those materials off to maintain operation of that vital research center. Same would be true for NASA has a plan for the future for going to Mars and going to the moon, of having a space station that has an elliptical orbit that goes out very close to the moon, then comes back around the Earth and heads out toward the moon. It's called Gateway. And you can look this up online, do a Google search for Gateway, and you can see what the plan is for that and how that would work for going to the moon. So it significantly cuts short the energy required for heading to the moon to do exploration and research. And when we go back to the moon, we're not going to stay for a few hours or a few days. The plan is to be there for a much longer time, so it's going to take a lot more resources. And so it's going to be a case of where are we going to get those resources from. So the plan is to send robots up, and NASA's first robot that will go to the moon with one of the next Artemis missions is called a little robot called Razor, Rassor, and it's going to mine material on the moon and put that into a deposit system that will then process that and extract water and oxygen and any other of the chemicals that they might need for operation on the moon. Their system that they have, it has 2 bucket drums on it. They're little round cylinders with a whole bunch of scoops on the outside, and as it rotates, and they're designed to rotate opposite directions from each other so that the net force is 0 on the robot. And it's powered by 4 wheels, and the drums themselves are on booms that stick out beyond the end of the robot. The interesting thing with that design configuration is that if they were to tip over, the robot has a self-riding configuration. It doesn't matter whether it's on right side up or upside down. It operates the same both ways. And it can actually use the bucket drums for propulsion and for aid in climbing over obstacles. The robot is very adept at getting places. The trade-off, there's always trade-offs in engineering, but the trade-off is it doesn't collect a huge volume, but it's very energy efficient. So if they were going to be doing the mining on the moon, they would have to have several of these in order to have enough mining capacity to get enough material to support 1 astronaut. In talking with Dr. Phil Metzger at the University of Central Florida, he used to be a researcher at NASA at the organization called SwampWorks, where they do a lot of this research. Rob Mueller is the director of that area, and he is the lead judge for the NASA Lunobotics Challenge. I see we got our guys in the box getting out there, getting ready to set up the arena for the next run. We should have another team coming in very shortly. Rob Mueller has their own lunar test chamber down there, and talking with him and Phil, I asked him how much material would have to be collected to have enough oxygen to support an astronaut for a day. And their estimate is that it would take 1,000 pounds of material per astronaut per day to support an operation on the moon. So that is the sort of challenge that we're looking at in doing that. The big challenge is how do you keep a robot charged? How much power do you use? To give you an idea, our 2014 robot that we had, which was called Hermes 2, that operated on about 400 watts of power on average. It had several motors on it, but not all the motors run at once. But running at about 400 watts of power, that robot was able to collect 1,000 pounds of material in about 40 minutes. And we did that at a place called Pisces. It's the Pacific International Space Center for Exploration Systems, at a competition called PRISM, which was the Pacific Robotic International Space Mining Competition. And in that, we were mining on Mauna Kea at an altitude of 9,500 feet, about 10,000 feet. It varied depending on where we were at. And we were mining material that was just like the surface of Mars. And it was the same place where the Apollo astronauts trained and where Curiosity rover was tested before going to Mars to see how it would operate. And our robot was able to do that very efficiently. It was a lot of fun to watch them do that. But it was not the typical 80 degrees that you like to think Hawaii would be in the middle of the tropics. At 10,000 feet, the warmest temperature we got up there on a given day was about 55 degrees. Most mornings we got up there, it was just above freezing. So very interesting experience in Hawaii, being at that altitude and doing that sort of work. But that's what space science is all about. And we had a lot of fun doing it and learned quite a bit at the same time. So that's what this is all about. We're creating systems to support exploration in space. We are part of Project Artemis, a small part, indirect part, but a critical part nonetheless, with the sort of technologies that these young engineering students are developing, and they'll go on and get wonderful jobs being a part of all this in the future, and creating opportunities for exploration and knowledge and furthering humankind, and at the same time too learning more about our Earth and how we can take care of it as well. And that is a great thing about engineering. So as we're getting things set up, my people in the box, all the club members are doing that. Who do we have working in the box now? It's who? Oh, Denise. Okay, Denise and John are in the booth, so shouts out to them. It's a very tough job. The suits they're wearing there, they're a Tyvek suit. They do not breathe, so you sweat like mad while you're working in those. But it's a nice cool day out, so that helps a little bit. We got very good air exchange going in there, so it's not too hot at all. But you still sweat like mad in those suits, so my hat's off to them. They have to go through training to be able to do that. They have to wear special PPE gear. They follow protocols as set by our engineering health and safety, or environmental health and safety people. They're very good at what they do, and they help us be safe and do things well. And we follow a lot of the NASA protocols that they have in operating in their chambers. And we do this as well in our lunar test chamber that we have in 0240 Student Innovation Center. That is our lunar test chamber by that name. And we have 7 tons of material in there. We've got 22 tons of material in this competition chamber. It's crushed lime rock. When we're done with this material, facilities will haul it out of here, and we'll probably wind up using it in the Hanson Livestock Pavilion, because they use crushed lime rock in those sort of facilities to help control odor and moisture for livestock arenas. It's a very, very good material, that. But for us, it makes an excellent material for mimicking lunar material, because it's the same particulate size. It has angles of repose that are very similar to lunar material. It's just not the same chemical makeup, because it's more calcium based, because it's lime rock, as opposed to basalt base, which is lunar material, or carbon base, which is our ISU-1, because it's out of Portland cement and coal fly ash. But nonetheless, all 3 of these materials create unique challenges for the robots to be able to dig in. They're abrasive, they're sticky, they can get very soft and floaty. You can get stuck in them very easily, or they can get very hard to cleave and get the material dug up. Creates all sorts of wonderful engineering challenges for our teams as they design their robots to work in the environment. The chamber that the students are working in is 16 feet by 18 feet. It's got a head clearance of about 6 feet, so they have to duck every once in a while working there. We were constrained by the depth of the arena and the height of the room that we're working in. So that does create some challenges working there, but they're doing a fine job of it. And the students are very excited to be able to do this event, bring it to you from Ames, Iowa. So looks like we have 4 minutes until the next team comes in to set up. At the same time, NASA's getting ready at the Kennedy Space Center, Space Education Center at the Visitors Complex for their award ceremony. I'm going to keep an eye on that and see how the teams there are doing. They're just wrapping up their competition as we are just getting our competition going. So we have 12 teams here, Iowa State, 11 others. Go through that list again as the teams that we have here, if you haven't been following us throughout the day. We have Sonoma State University, the SSU Lunabotics team. From Youngstown State University out of Ohio, we have the YSU Penguin Moon Miners. From the University of North Dakota, we have the UND Lunabotics team. From San Diego State University, we have Team Creed. From North Dakota State University, we have the Bison Robotics team. From the University Illinois at Urbana-Champaign, we have the Illinois Robotics and Space. From Northeastern University, we have NU Lunabotics. From the University of Minnesota, we have the University of Minnesota team. From Iowa State University, we have the Cardinal Space Mining Club. From New Mexico Institute of Mining and Technology, we have the Miner 49ers. From Virginia Polytechnic Institute and State University, Virginia Tech, we have the Virginia Tech Astrobotics. And from the University of Arkansas, we have the Razorbots. Now, so far, we've had 2 or 3 successful runs in the arena. We hope soon here to have Arkansas, who their first run was a scratch, to come in and do their next run. And hopefully that one will be successful. Earlier, we had New Mexico Institute of Technology did a run, and they did a magnificent job of mining a lot of material. I haven't had a chance to find out just how much they got, but I can tell you with a lot of confidence that they mined more material than some of the teams I saw down at the Kennedy Space Center. And that's to be expected because we have 5 teams here that were amongst the top 6 teams at last year's competition, including Iowa State. And so we expect to have a very good competition here with these teams. I can see here that we've got the robot in place for the Razorbots. It looks like we got about 1:30 before their time to start. We got movement from the robot. That's an excellent sign. So we got connection. So we'll be ready to go here in a little bit. I don't have any of the team members over here yet. I'd like to talk to one of them if I can get them over here. So I'm sending our club president, Sebastian, off to go find some of their members and get one of them over here so I can quiz them while the robot is running. That's torture for them, but, we'd like to know what's going on. So, for those who are just joining us, I'm Jim Heisey. I'm the faculty advisor for the Cardinal Space Mining Club. I'm a professor of practice in the Department of Mechanical Engineering. I've been teaching at Iowa State since 2006. I was in industry for 25 years before that, hence the title professor of practice. I really enjoy working with the students here at Iowa State. I am the coordinator for our Capstone Senior Design Program, where we do projects with industry. Thanks to Iowa State Extension Cirrus office, they help me find projects for our students to work on. But I really enjoy working with this club and designing robots for mining in space and going to the Kennedy Space Center to compete. But having the opportunity to put this competition on as well is equally exciting. And we're having a good time doing it. And the teams that are here are very excited to be here. And so hopefully we can bring you some great action with this next run from Razorbots from the University of Arkansas. So as you can see, a very similar design in some ways to the robot that we just saw run a little while ago from New Mexico Tech. It's a wheeled system with a bucket on the front, though their boom is a little bit of a unique design. It'll be interesting to see exactly how they go about collecting material and depositing it in the berm building area, which you see marked in there in the blue chalk box, and that's where they deposit material. Right now, one of our arena workers is loosening up some of the material that got dug earlier, so it's not so compacted. This material, the crushed ag rock, it can get quite hard to dig up if it gets compacted too much. We walk on it, it packs it down, it makes it difficult to dig up. Plus, we want to have it a little fluffy to create some unique issues, and we don't want any clumping of the material. So I think they got it pretty much under control. You can try scooping this stuff with the shovel, but when it gets compacted down, it gets really hard to get a shovel down into. That's why we're using a pitchfork. It's not an Iowa thing. It's a Terra Mechanics thing as to why we're using the pitchfork. So it sounds like we're ready to go. And here we go. So they got a good start, good motion on the robot, nice turning, nice maneuverability. We'll watch it disappear out of the start area picture and proceed into the obstacle mining area. They got to contend with that rock. I really like the delicate design of these wheels. Now, what's interesting is the previous team had a very significant, oh, they're going for the rock right away. This is interesting. Let's see if they can get that picked up without the robot tipping over. That's always a challenge. You pick up one of these rocks and given their weight, you go to try to pick it up, and either you don't have enough oomph in your bucket to pick it up, and that seems to be kind of the case here. It's interesting. Or maybe he's just going to push it out of the way for now. This is interesting. He's getting some good motion out of that robot. It's an interesting thing. The other robot had very tall cruisers on it, and it dug holes very quickly. This robot's not quite as deep on its grousers. They only look to be about maybe about a centimeter or two in height, and they're not digging in as fast as the other teams. Okay, he's decided to drop the rock off, and looks like he's going to start to dig material, get his robot turned around. But here again too, when you can't get quite as deep in the material, you don't get as much thrust force out of it. So it becomes a case of optimization as to your cutting edge on your bucket, the width of your bucket, how deep you're trying to cut in the material, all these different factors that come into play, making for an efficient mining machine. But he does have a fair amount of load in that bucket, so it's got a good start, get himself lined up to where he can go straight back and forth and mining material, and should work out well. Great, so I've got a team member here from Astro Robotics, and we'll go ahead and get him set down. And welcome, and you are?
Jaden Timms.
Jaden Timms, welcome. We're very excited to have you here.
Yes, sir.
As a part of this competition. I've got the NASA award ceremony on the other computer. We're going to keep track of that to see who does what there while we're doing stuff here. So tell me about your team and about your robot.
So our team is really a conglomeration of every person, whether they be undergrad or senior,
Okay.
all the way up, despite it being a creative project design,
Okay.
which is our capstones.
Okay.
So this is really more of a capstone project
All right.
that we do, but we want undergrads to be here as well, so that we don't lose knowledge.
Yeah, because that turnover of technology as the seniors graduate can have a huge impact
Yes, sir.
on a competition team. You're not set up then, I take it, as like a student club or something like
No,
that.
sir.
It's just all part of the senior design program.
Yes, sir.
That's great, because some of the schools do have clubs set up for this, as opposed to having it as a part of senior design. Others, just as your school is set up. So tell me about the robot. Does the robot have a name?
Not that I'm aware of, at least.
Okay, yeah. So we've got a very interesting, I really like the elegance of your wheel system that you have on this. They look very lightweight. What's the robot weigh?
It weighs 36.25 kilograms right now.
Okay. If for pounds wise, we're probably looking at, doing the math here, 2.2 pounds per kilogram, 36. We're probably looking at about 80 pounds.
Yes, sir.
So about half, it's a little under half of the allotted weight that NASA allows us for. And so that makes for a very efficient mining system.
Yes, sir.
Not too heavy, not too light, just enough thrust to get some good material picked up. Now, it looks like we got some material dumped, maybe. No, maybe not. I don't know what's going on there, because he was doing some good motion and all of a sudden things kind of stopped. Tell me about that mast on the top. Is that a camera, a LiDAR, or what?
That is a camera up at the top. It's our camera system.
Okay.
So I'm not really part of the computer systems, so I don't 100% understand what's going on there, other than as camera so that way you can see and sense where it's going, which is what this right here, this little paper in the bottom left screen is actually for, is for autonomy.
Ah, okay.
So that's our known position.
Okay. known position, then it maneuvers based off of that.
Yes, sir.
And so probably you did some teleoperation to get some obstacles out of the way, and maybe they're setting up for autonomy.
That may be what they're doing, but I'm not 100% sure because
Yeah.
I'm mechanical.
Okay. Yeah, that's fair enough. Tell me about some of the mechanical systems in there. What sort of motors are you using on this robot?
Specifically motors. I do not remember the name of the motors that we've got, but we do have it geared down from like 100-to-1 ratio,
Mm-hmm.
and we've got it geared down so that we can get as much torque as possible out of the motors.
Yeah, that's very typical on these robots. It's
Yes.
extremely high gear ratio for getting torque multiplication. Okay, we got some movement again. That's great.
I think they were doing autonomy setup.
Autonomy setup. Yeah.
Yeah. Yep, there it is.
Yeah. Okay. So walk us through this whole autonomy setup as to what you expect the robot to do under autonomy.
Under autonomy, it should be able to dig, and also that's why the bucket looks a little odd, because we went with a hybrid between a shovel bucket, and a dozer blade at the same time.
Uh-huh.
So it should be able to power itself over any obstacles, as well as dig itself out, which at that time it dug itself in. But
yeah.
it should be able to push, pull, and carry a load. But I guess we're not doing too well on the loading.
Oh, I would tend to disagree. I think you're doing quite fine because you're not stuck yet, and that is a good load of material.
Yep.
And it looks like you're going to get a good deposit into the area.
Yes, it is.
Yeah. So very good. Your actuator speed actually looks good too. It doesn't take too long to get things in the position where you want it to go. That's always the challenge in these things as well. Now it looks like he's up against a rock. As long as he doesn't back over and get hung up, we're okay.
We shouldn't. I don't think we should, but based on like our torque and our fins and excess fins that we've got on the wheels, it should be able to just power over them.
Okay.
But still field testing, so
Yeah,
we'll see what happens.
Yeah. No, it looks like a very effective, nice design, and at a good competition weight too. Our lightest robot we ever built weighed in at 31 kilograms, but most of our designs have been in the range of 40
Yes, sir.
to 50 at Iowa State. One year we actually had two robots that nested together to fit in the one size box. And we did that 2 years in a row, and each one of those weighed in at about 37 kilograms. So we used up just about the whole weight allotment and size allotment. But we had two robots running. But we found out that putting two robots in the space where one operates, not necessarily a good idea.
No, sir. I can see the challenges there.
Yeah, you got to get out of each other's way.
Yes, sir.
If you don't have enough driving practice to figure that out, it can get to be very chaotic, and it was for us in those years. But we still had a lot of fun, and we had some good success with it.
Yes, sir.
Not as much success as we had in later years when we decided, okay, this experimentation with two robots is enough. We've learned from that. We're going to stick with one from here on out. And very impressive maneuverability on your Razorbot.
Well, thank you. Yeah, we just like razor blades.
Yeah. It's a very elegant design too. That really nice asymmetric single arm for operating things, and the bucket seems to have very good motion. Very nicely done.
Yeah, with that single arm, we were actually able to shed from our last year's robot to this year. With the entire redesign, we were able to shed at least 60 pounds.
Wow, that's impressive.
And mostly due to the redesign of the chassis and that arm.
Yeah, a lot of that metal looks like it's a pre-finish white. What is it made out? Is it aluminum material or?
It is aluminum, and we bead blasted.
Oh, you bead blasted it.
Yes, sir.
Okay.
We bead blasted, and that's what most of it is finished.
Okay.
It helps with keeping it from sticking so much.
Oh, okay. So creating enough of a surface texture that material doesn't stick to it. Ah, very good.
Moving the rock.
Yes. That can be very challenging. We've seen teams last year at NASA try to move the rocks and then get themselves stuck. And so just taking a quick look at the NASA operations in Florida to see if they're getting close to giving awards. And nothing yet, but I see a big check there, which means they're getting ready to give off some of the big awards. The awards they give at NASA involve STEM outreach project, systems engineering, technical presentation, and the mining award, and then the grand prize award. They used to call it the Joe Cosmo Award of Engineering Excellence after one of their famous engineers who, Joe Cosmo, quite a name for somebody who's dealing a lot with space. He did a lot of the engineering of the NASA spacesuits. He had over 270 patents in space suit design. And he later created an organization called the Desert Rats, where they spent a lot of time out in Arizona and New Mexico and Utah doing a lot of space type testing and exploration, figuring out how if we were to go to the moon or Mars and do long-term exploration, how we might carry that out, designing equipment. They designed various different types of long-range rovers, various types of digging equipment, analysis equipment, and did a lot of fantastic work. Excellent gentleman to get to know. And I was kind of disappointed when they decided to no longer call it the award after that. He had retired, and they decided they needed to move on and then just go with the grand prize award for the top team competing in that competition. Of course, the two key people for the NASA competition that we most need to thank for the opportunity that this creates for all of our engineering students are Rob Mueller of NASA at the Kennedy Space Center, the director of Swamp Works, which does a lot of the research work on surface systems for going to the moon and Mars, and Mr. Eric Reiners, Vice President at Caterpillar, who is the major corporate sponsor for that competition, and through his support here has enabled us to do this competition as well. So my thanks to Eric for his assistance on this. Let's see, we've got, it looks like a couple of deposits into the berm area, and we still got 17 minutes to go. So as soon as they get some things sorted out, this is always a fun thing in these competitions. We get halfway through a run and all of a sudden mission control team has to decide, okay, this isn't working quite for us, so we need to make some changes in coding or strategy. And so they're talking that over with themselves. Not high pressure at all, right?
No, not at all.
What do you suppose they're discussing over there?
So more than likely what they're discussing over there is our feathering angle is not correct.
Oh.
We have a very specific angle that we have to attack at. Otherwise, we will dig too far and lose complete traction.
Okay.
And that's the problem that we've been having with autonomy is the feathering angle. It kind of likes to bounce. And we have a very tight tolerance for the angle.
Well, not only that, but you talk about terrain and what impact that can have. You try to get your bucket set in that. It sounds like if we were to really make it work well, we have to have some sort of sensor system that would sense the distance from the ground to the bucket and automatically adjust that. But unfortunately, you would think we'd use a sonic sensor or something like that, but NASA doesn't allow the use of sonic sensors because, and why do you suppose that is?
Probably due to no sound waves being able to transport through space.
That's correct. The moon has no atmosphere, so a sonic sensor is totally useless, very useless on the moon. Infrared sensors can work quite well. The only problem is you generate a lot of dust, and that does happen on the moon very readily, and it will blind the infrared sensor. So for something like this, a laser tracker works far better. It can cut through the dust And so that's what we see a lot of teams using are LiDAR and laser units, and we've used them in the past. One of our more creative designs that we had at Iowa State, we had a laser target emitter tracker that because the year before we had found that thanks to the terrain we might miss the target when we turn around. we put it on a servo and put the servo through a sine wave movement
There you
so
go.
that the laser was sweeping. And
That's actually a really good idea there.
yeah, and that way we're guaranteed to not miss the target when the robot swept around to find home and head toward the target. It worked beautifully.
That's perfect.
So, you know, a lot of design innovations like that we take a look at a problem, or we go to do something, it doesn't work as planned, try to figure out, assess why. Okay, why is it not working?
Yes, sir.
And then make a engineering change and overcome the issue and become accessible. So hopefully we've lost about 4 minutes here since we've been talking. A little concern on the robot. Hopefully they get something figured out here soon and can get the robot rolling again and get some more material.
I hope so too.
Yeah, it's like I tell my students in my vehicle dynamics class, how do you win a race? By having the shortest average lap time. And how you do that? By making sure your vehicle stays out there running. So
staying operational is the exact way that you need to keep going.
yeah, so we'll see. Maybe they can pull this out yet and get a good run here. But of course, you get 2 runs here.
Oh yeah.
And this is your first one.
And
so,
work out bugs now rather than use the next run.
Yeah, we're scoring the best run out of this competition as opposed to taking an average, so that works out well. Looking at the NASA competition, they were supposed to start their award ceremony about 15 minutes ago, and they haven't started yet. We ran into this problem last year. They were trying to judge everything, and the points was so tight that we were an hour late in getting the award ceremony going. Only to find out later at the end of it that they had to wind up giving a tie to Iowa State and the University of Alabama. So we'll see if history doesn't repeat. Well, it can't repeat itself because we're not there.
Yeah,
But we'll see whether or not how the results come out of that, and we'll report that as it comes available to us. Okay. So tell me a little bit more about the club. Where do you typically do your testing of your robot at?
Testing we typically do in a cargo container that we've got set up.
A cargo container.
Oh yeah. We've got it set up in a cargo container that holds the entire bottom of the cargo container is designed as a test pit arena.
Okay, what do you use for material in it?
We use actually crushed limestone.
Okay.
As well.
So it's the same material that we have here.
Exact same material.
It's cheap. It's available.
Yes, sir.
It's easy to work with.
Yes, sir.
Yeah. And it behaves very much like the lunar material that NASA has, and what we have here. We got material in front of you here. We have regular sand and soil.
We've tested in that before.
Yeah, we've tested in sand as well. I always we get down the floor, and oftentimes our teams will say, "Hey, let's go test in the beach," and I always sit there saying, "No."
Yeah, because they tested in a sand volleyball pit.
Well, that's not quite as bad, but the sand does tend to stick to things. But beach sand by the ocean is terrible because it has all that salt in it.
It sticks to everything.
Makes everything sticky, and then you got to clean it all, wash it all off, because if you don't, then the regolith sticks in your robot and you can't get it out. Yeah. And last time we were down in Florida, where we stayed in a place on the beach, we all of a sudden found out that we couldn't test in the beach anyway because it was a $300 fine for digging in the beach sand because of turtles. Turtles were laying eggs in that region, and so we couldn't test at all on there. But that's okay. It worked out anyway for us.
Yeah, that's better.
Yeah. So because then we didn't have to wash off the robot when we got to the competition.
Yes, sir.
So for those watching, as we're sitting here waiting for the robot to go, you're noticing this very unique thing here in front of me. This is one of the trophies we'll be giving away to the winning teams. Here it was designed by one of our own team members, Mason Eck. What we have here is we have this glass orb, and it's laser etched into that is the duplicate of the moon. And then he has fiber optics in here coming down to the base, and they can change in color as it's doing right now, going from blue to white. The verticals here are out of aluminum. They've been water jetted out, and then the rest of the pieces are 3D printed. They'll be mounted on a beautiful wood base with a plaque on it, and that'll be the award we'll be giving away to the top 3 teams here at the competition.
That's
So,
amazing.
yeah.
If you don't mind me asking about that
Yeah.
laser etching, so is that laser etching actually inside the orb, or is it on the outside at one side?
That is a good question. I do not know. I'll have to ask Mason. He actually ordered those orbs from Amazon, and believe it or not, they were only about $10 a piece.
I do believe it.
Yeah.
Laser etching can be fun.
Yes, it really can. And it's really nice. And the nice thing about it, you can move this thing around a little bit, get in the position where you want it. And though we had one of Jim Christensen, who's going to be our guest speaker Saturday at our banquet, moved all our moves into a proper position on there. Looks like the awards ceremony has started at NASA, so we're going to monitor this a little bit and keep track of what's going on. What's that? Okay,
Yeah.
it looks like they're ending the run here for Razorbots. Their computer went down. We're unable to recover. So, but they did get material in there. It does qualify them. So we'll see what they can get things sorted out and get a good second run. So,
Yes, sir. Well,
Jay,
thank you.
for being here. And,
Yes, sir.
Good luck on your next run.
Yes, sir. Thank you.
Thank you for being here at CoSMiC. We really appreciate
Yes,
it.
sir. Thank you for having
Okay.
us.
All right. Okay, I'm gonna keep close track here since we're gonna wait for the next team to come in, and I'm going to report on the NASA competition as not getting very much volume out of NASA, unfortunately. And I got my sound all the way up. Again, this is CoSMiC, the Collegiate Space Mining Challenge from Iowa State University in Ames, Iowa. Okay, they're getting ready. So Eric Reiners is up to RC Expert Lunar Operator.
And he is going to talk about the results of the RC efforts and who's the expert lunar operator. Now, before Matt does that, just raise hands. How many of you got the chance to run CAT RC either at UCF or at ASC? Nice, nice. Well, Matt, I'll turn it over to you.
Give you a little idea what that award is about. The Caterpillar is giving away. They have a remote control skid steer that is located in one part of the country, and the students have the opportunity to operate it from the University of Central Florida and from Kennedy Space Center, and they're giving away awards for the team or the students who had the quickest times of doing all of the tasks that needed to be done and without getting penalty.
So, sorry about the technical difficulties with the machine a little bit. So we only had a few teams come through, but I do want to have the top 3 teams come up and grab a prize. So each person from the top 3 teams can come have a pick. And so we'll start out with team number 1, got first place with 11 minutes and 22 seconds. Is We Yearn for the Mines. Jacob Evans, Zachary.
Okay, so the first place went to the team We Yearn for the Mines, made up of Jacob, Evan, and Zachary. I'm not sure what school they're from, but they had a total run time of 11 minutes and 22 seconds on their obstacle course.
All right, number 2. Just a little bit short.
Purdue, Anchor, Pranav, and Alexander had a time of 11:56.
Good job. All right, and in third place.
And third place,
UNH Lunacats.
University of New Hampshire Lunacats, Timmy, Riley, and Carter with a time of 12:26.
All right, it's the Lunacats out here. Let's go to fourth place for some prizes. So, all right, fourth place, the Shish Kebab of College of
Shiskabaj, College of DuPage, who did make it into that. We have some DuPage students here. Tommy, Dylan, and Dustin. Fifth place to Long, Josh, and Cindy of Team Swoops. And Adrian, Caden, and Sophia, the Slowpokes, also from the College of DuPage at 18:38 time. NASA awards.
Thanks so much. Hope you enjoyed running the RC system. Check us out. Go search Command for Dozy or Cat Command Station and see all about our product. Thank you so much. Thank you, Matt. Captain Advanced Rules and now.
Okay, now the Autonomy Awards. Next up on our competition is going to be the YSU Penguin Moon Miners.
Scored the highest level, not their total points, but gives you an idea of the levels of autonomy the teams have been able to achieve here at UCF and at KSC, because it's the sum of the two. And we had 12 teams total out of the 35 that were able to perform at some level of autonomy, really mixed level. And so, one more big celebration, because that's over 30% of the team.
Okay, over 30% of the teams at NASA were able to do some level of autonomy. Only one did travel and 3 dig and dump cycles. It'll be interesting to see who that one team was, because there surely will be the autonomy winner.
So before I get into 6th and 1st place.
Okay. Honorable mention on autonomy.
Not 6th and 1st, so if you go ahead and put it in.
College of DuPage, Colorado School of Mines, Texas A&M, University of Utah, University of Portland, and the United States Military Academy.
University of Utah, University of Portland, and the United States Military Academy. So congratulations to
all excellent teams.
Being able to achieve some level. Go to the next slide. So, yes.
Okay, autonomy 6th place at NASA is University of North Carolina, Charlotte. Okay, next team up to run here at CoSMiC is Youngstown State University. They're out of Ohio, the Penguin Moon Miners. They are a senior design team from that university, and they're in tech inspection right now.
Next slide.
Okay. 5th place, autonomy. 250.
Don't I wish?
Oh boy.
Yeah. Boy, there goes my, yeah. Wow, there went my bonus check for like a decade. Is University of Illinois, Chicago.
University of Illinois, Chicago took 5th place in autonomy. It's a $250 prize and a plaque. Another excellent team. Okay, and as you see, our pit crew in the box, Johnny and Denise are working the pit and get it ready to go for the next run. You can see a picture of our pit area. The team's working on the robots. Okay, very good.
Next slide. Fourth place, not $500,000, $500 is Michigan Tech.
Michigan Tech University took fourth place, $500. Third place in autonomy at the NASA Lunabotics Challenge.
Okay. And second place,
Second place,
$1,250.
$1,250. University of Alabama. This is exciting because now we have a new top dog on the autonomy prize. See some familiar faces there. University of Alabama has a great team, Astrobotics, great faculty advisor, Dr. Kenneth Ricks. We've come to know them quite well over the years in competing. They're an excellent team, and they always come with a very consistently good robot, and they're fun to compete against and get to know. And they've been very gracious hosts too, the years that they've run the robotic mining challenge at their campus in Tuscaloosa. Okay, so now we get to find a new autonomy challenge or champion.
And first place, $2,000 is
Purdue University. Congratulations, Purdue. It's exciting to see. We love to see these lead changes in the competition. That means the teams are learning, they're expanding on their capabilities, and we're seeing new technologies come into play. So excellent, excellent, excellent.
We gotta get software.
Okay, we have 4 teams yet to go today to get done between now and 7 o'clock. Hopefully we can get going through these pretty good now that we have mission control moved and our communication issues set. They're adjusting the camera at the request of the team. Activity in the pits area,
Thank you, everybody.
staying consistent. Okay, Caterpillar just concluded their autonomy awards in NASA.
Congratulations to all the teams who won autonomy awards. All right, next we are going to give the award for the efficient use of communications power.
Okay.
Efficient use of communications power essentially means the team.
Next award at NASA is efficient use of communications power.
Right, without having to communicate back to the students in the control room. And so the team, we have a certificate, and they will give you here today.
Going great. Why don't you
Um,
come here?
but
Yeah.
I believe we also.
I'm online, but I'd love to. Come here, sit down. As I'm watching the NASA awards, I also just visited here by Mr. Joel Johnson.
Hello.
Yes, we're excited to be here doing this and to have all your support with helping us make this possible.
Well, we just thank all the teams for being here, and we just thank your team and all your students for doing such a great job putting this together. So
Yeah.
it's been a lot of work, a lot of planning
It has
for
been
your group.
a
So
team effort all the way around between
Yes.
university administration, the
Yeah.
College of Engineering, CPM,
Yep.
EH&S.
Yep. So
You've been
it's
fantastic to work with, and
the conference is it's exciting to see it happening. The competition's going.
Yeah.
Sounds like things have gone well today. Smooth competition so far.
well, as smooth as can be expected. There's
Okay.
always technical glitches. We had
Okay.
to move mission control from over there to over there because
Okay.
somebody ran over one of our ether cords and cut it.
Oh.
So
Okay. Okay.
we got that resolved. We're rolling again,
Good.
and we expect good things out of the rest of the competition.
Well, we're just excited that all these schools have had a chance to come see Iowa State, be a part of this experience, and thank you to you and your team for all the great work you're doing. So
You're welcome.
hopefully everyone's having a great experience and enjoying their time on
They
campus
have
at
it
Iowa
so
State.
far. I pointed several teams down to Hickory Park and
Fantastic.
over to West Side Deli.
Good.
And a lot of compliments on the campus. A lot of the
Good.
students love the Iowa State
Well, and a
campus.
chance to engage with with the Innovation Center, and a
Yeah.
chance just to see the creativity of your team of putting all this together and building the arena, and
Yeah.
just all the great planning that your group has
So
done.
they're really excited. So maybe
Good.
we can expand this in the future years.
We'll have to take a look and see what the opportunities are in the future. So,
All right.
yeah.
Well, again, Joel, thank you so
Thank
much.
you. We appreciate it. We appreciate all you've
Okay.
done. And thank you to all the student leaders. We appreciate all that you've done in support of
Yeah.
having this event today. So thank you.
Okay. Thanks.
All right. Good luck to all the teams.
Take care.
All right. Appreciate it.
Okay. University of Alabama just took third place in communication efficiency. That's to be expected. Autonomy systems usually do the best in the communications efficiency. So we'll see how this comes out. They get a certificate. So for all of you out there watching, hoping to see more robotic action, we apologize that we aren't able to move things through quickly, but this is our first time doing this, so it takes a little bit of work, sort out some of the technical issues, and the teams themselves have come here. Some of them haven't had as much time testing as others, so they're working through their technical issues. We're making sure to give everybody as much a chance to run as possible on this.
Robotic Construction Awards, second place.
Oh, robotic
awarded to
construction.
The University of Utah.
Okay, I was wrong. That's the non-efficient communications, but construction, this is the big award. So Alabama took third, but Utah took second. They were a good team last year, and they ran neck and neck with us as well on this. So this is exciting. Hey, guys. Construction award at NASA, which is one of the big awards. Alabama third, Utah second. They have still the name grand prize or first place yet on construction. So we'll see here. Yeah, we took first place last year.
Okay, the top prize.
Top prize construction.
Robotic Construction Award, first place is awarded to the University of Illinois in Chicago.
University of Illinois, Chicago. Now, I got a chance to watch their second run, and one of our teams here, I won't say this right now, I think actually collected more material than they did. So it'll be fun to make comparisons later and see how it turned out. All right. Well, congratulations, University of Illinois at Chicago, for being the top prize winner on the construction award. That's the mining award at NASA. As we watch this, it's very exciting news because we're seeing new winners for the first time. at this competition compared to years past. It's been heavily dominated by University of Alabama and Iowa State University. It's nice to see other teams get a chance to shine at these competitions. Very important that other teams get a chance to see success and are encouraged to continue to work hard on this.
There's lots of dimensions to this competition, and we just awarded all the individual categories, so congratulations to all teams.
Hello.
I'm Anthony.
Anthony, nice to meet you. Have a seat. Okay. So you guys are getting ready to load up in here, and
We are.
great. I've been monitoring the NASA awards.
Okay, how's that going?
Surprising. The top winner in the construction category, the mining, University of Illinois at Chicago.
Really?
Alabama was third.
Underrated, huh?
Yeah, and University of Utah was
I heard
second.
they were doing good, yep.
Yeah, they were doing good. So very excited to see that. I watched the University of Illinois Chicago's run, and I saw how much material, which was impressive. But I have to say, the New Mexico Tech team here that deposited their material did a very good job
Yes.
and had a very large. So it's going to be fun to compare what we get here to what they get there.
Of course.
And hopefully you guys can do a great job too.
I'm planning
Looking
on
forward
it.
to it. Good.
Worked very hard for this.
Okay.
To this group here, that the Artemis Award for the 2025 Lunabotics
Okay, they're announcing the grand prize winner.
is awarded to the University of Utah.
University of Utah is the grand prize winner. Congratulations to Utah. They are a fantastic team. We loved competing against them last year. This is good. Alabama is no longer the top dog competitor. They can get the monkey off their back, and now everybody's going to be shooting for Utah.
Nice.
So that's nice. That's
Good for them.
excellent. Congratulations to the University of Utah team. This is exciting to see. A lot of fun. Wish we could be there, but we're having a lot of fun here, and we'll enjoy what we get to generate here. And I'd like to think we have some fantastic awards that we'll be giving away as well. You can see right in front of here one of the trophies we'll be giving away.
Okay, very cool.
And I'll go ahead and minimize this and minimize the sound now that we know who the winners are. Very exciting news out of Florida with the Lunabotics mining competition. Now we'll focus more here in Ames, Iowa, and the CoSMiC competition. And looks like we have some activity going on in the box, as we like to call it. Here it comes. That is a cool little robot.
Thank you very much.
Very compact.
We idealized that for we were planning on going up and on the Artemis rocket, so
Yeah.
yes, very
Yeah.
low profile.
What are your dimensions on that robot?
I believe we are only 11 inches tall, and the length is about, I want to say 76 inches long.
Okay. 76? That are you sure? Because that's about 6 feet. That's outside the size box.
Okay.
Maybe 46?
I was thinking of the weight, sorry.
Oh, the weight. Yeah, what's the weight on the
78 pounds.
78 pounds.
78 pounds.
Okay. That's pretty light.
Yeah, it is extremely light. We prioritize that. Energy consumption, obviously, we're graded
Yep.
on weight as well.
And very interesting bucket on that too. It's not as wide as some of the others that we've seen running in the competition. Why is that?
We're really limited in our resources.
Uh-huh.
We're a small scale university
Yeah.
from Ohio in Youngstown, and
Mhm.
we had a local company build the bucket for us based on previous dimensions of a previous design.
Uh-huh.
Everything is new for this year. We're a senior design group, and we're the first YSU team to be competing in any Lunabotics competition. So we're extremely excited just to be here. Yeah.
Okay. I'm taking a second to listen what the key organizer, Rich John Bulk, and they're closing out the ceremony with Eric Reiner. Oh, I know what he's going to do here. I got to turn this down. It's going to get very loud. They have each team do their key chant at the competition, and it gets quite raucous.
Cool.
Yeah. Okay, so we got the robot set up. So tell me more about the design of your robot.
So I was thinking about it. The frame is actually 26 inches long.
Okay.
Sorry for there earlier.
Yeah, that's all right.
The frame is completely made out of 80/20 aluminum, like a Rector set. It's lightweight. It's very easy to be in terms of adaptability and functionality for a limited amount of resources. We are pretty much designing everything hand tools. We didn't really have any water jets or any aluminum cutting blades or anything like that.
Yeah.
So very compact and very efficient for what we had.
So your aluminum pieces, Rector style, where did you get those from?
We ordered them from Amazon. So,
Amazon?
Yeah,
Okay.
limited budget as well.
Oh yeah. So how much money do you have invested in building this
So
robot?
we started with $4,500.
Wow.
And luckily we are able to kind of fend for some extra additional funds. There is about $7,200 into the robot,
Okay.
but not all of that was funded. It's out of our own budget.
Oh my.
We're in a little bit of debt, but
Yeah.
had to do what we had to do to be able to get here.
Now, is this a student club or a senior design group?
It is a senior design group, yes.
Okay.
Yeah.
So is your team all seniors?
So we are all seniors. We do have one sophomore.
Okay.
And she's in software development, and she's been doing a very good job. Her name is Iamide.
Okay. Are they all 1 degree?
We are all electrical engineers, believe it or
Oh.
not. We have no mechanicals. We don't have a software engineer major at our university. It is either mechanical or electrical.
Okay.
Yes.
Very, very interesting.
Mhm.
Yeah, usually you see a lot of these teams based mechanical engineers trying to do electrical engineer work.
Yes.
What's it like being an electrical engineer trying to do mechanical engineer work?
It's interesting. It takes a lot of trial and error. I'll tell you
Yeah.
that. A lot of late nights staying up and figuring things out. But
Sure.
I feel like what we had to work with, we did an extremely good job. Proud of
Probably
ourselves.
A lot of what I like to call TLAR engineering. That's an acronym, stands for that looks about right. Then you go out and test it and find out, no, it wasn't quite right. We're going to
Yep.
make some adjustments and figure out the next one.
Yep.
So very good. So it looks like we're done on the NASA competition, so I can turn that off. But exciting news. University of Utah is the grand prize winner at the NASA Lunabotics competition for 2025. The University of Illinois at Chicago is the construction prize winner. That is the mining award, top prize there. I've had a chance to watch U of I at Sea competition runs, and I think we're going to be very competitive here as well. So this is very exciting.
It is very
good.
exciting.
See how we can do here and see what CoSMiC can do on its inaugural run here in Ames, Iowa. And so we're looking forward to that. So your team's just in the middle of setup, and hopefully there's no communication issues, and we'll see how well we do here once we get rolling.
Yeah, I think we'll be good, knock on wood.
Okay. So how many members in your team again?
We originally had 7, but the 7th member had some issues within his senior year.
Yeah.
So it is just 6 of us
Just
on
6
the
of
team.
you.
Yes, and like I said,
Yeah.
we're all electricals.
Yeah, very good. Well, fascinating to watch. This is a very unique design in its configuration and size, because normally we don't see robots this small. But from a standpoint of mining efficiency, it's going to be fun if you can get the close to equivalent material as what New Mexico Tech did.
Yes,
That'll
sir,
be
100%.
quite amazing.
It would be amazing.
Quite amazing.
Yes.
So, but it's not just the total amount of material that you collect. It's also comes down to weight,
Of course.
which you got a nice advantage there,
Mhm.
and the technical points that come along with that. So we'll see how this all plays out. So we see a lot of variation in light on that one screen. I think it's a simple case of something going on with the lights, what they're doing.
Gotcha.
or somebody's moving back and forth in front of a camera that's seeing light. Because some of these cameras have auto adjustment for light, so if it's dark or if it's light, they open up or close their apertures, and that makes the camera go dark or light depending on what's happening. So it's interesting. All of these cameras you're seeing closed circuit here. One of our club members, Mary Greeley Hospital here in Ames, had to upgrade all of their security systems.
Really?
And he purchased all of their old security cameras for $100.
Wow, that's impressive.
And it's like 45 cameras. Wow. So he donated a few of those to the club that we could use for this, so we could set up our closed circuit TV.
Nice.
So I guess in an offhanded way, my thanks to Mary Greeley Medical Center for selling to us at a very good price the cameras that we're using. And we're very excited to have this as a resource for putting this together and being able to show you all the different operations. And I see we got a camera out of place there because we're looking at the top corner of the arena. So you people in the box, if you can hear me, we got a camera out of position in one corner. If you could get that fixed, I'd appreciate that. See, they can hear me on that. Somebody will say something to them, I'm sure. Hey, Carter, come here, if you could. We got a camera out of position in the arena. This is Carter Dougherty, one of our club members, so you might let them know that it's out of position. If you could run over there and tell them. Oh, I think they're getting, nope, he just bunt. Okay. We'll see. But nonetheless, hey, Carter, go over there and check with them, make sure they know. Okay, yeah, they got it moved. All right, I'm going to move this. Move my clipboard.
Okay.
Award over here to the other side of the computer.
It is very nice.
Yeah, Mason Eck designed that for us, one of our club members. And what's that?
They fixed it.
Okay, yeah, they got it all fixed. Great. Okay, so we're back to that. This little orb here actually has a laser etching of the moon.
Really?
Yeah, that's the moon in there. You see that little hazy circle in there. He water jetted the aluminum plates here in the Ag Engineering building. And he has fiber optics set up here, and then 3D printed the white plastic parts you see here. And then we have a beautiful wood base that these goes on with the plaque on it. So the first, second, and third prize winners in the competition will be getting one of these awards.
It's a very impressive building and campus you guys have here.
Well, thank you. We're proud of it. I like to call this a best kept secret in the middle of a cornfield.
Yeah.
What we have here at Iowa State. Just some interesting facts for those who are watching online. We have one of the largest mechanical engineering programs by enrollment here in the nation at Iowa State University. One of the largest, top 5 by size college of engineering with close to 10,000 students in engineering. So that means 1 in 4 students on the ISU campus, actually better than that, close to 1 in 3 is an engineering major.
Wow, impressive.
Yeah, and the rest are either science, farm, or liberal arts studies. We have a whole lot of animal science going on here,
Cool.
and farm science and that, because it's all about agriculture in Iowa, and we're very pleased with that. But engineering supports a great deal of that as well.
Nice.
We have over 1,200 manufacturers in the state of Iowa, a lot of them supporting the ag business. And we wind up with doing a lot of our senior design projects in mechanical engineering senior design with those companies.
Very cool.
So our people in the box, our pit workers are getting the pit all prepared for your robot, making sure that the material isn't too compacted and too clumpy, trying to smooth that up as best as possible. So you got an equivalent terrain to work on. And so it'll be fun to see. Now, you notice too, we're using a rake and a pitchfork. It's not an Iowa thing. It's that if you use a shovel and try to dig down into this material, you're just not going to get very far. It
Yes.
gets very dense the
Yep.
further down you go. And the easiest way to get down there and loosen it up is actually using a pitchfork. So
Gotcha.
works pretty well. In Iowa, a pitchfork is typically used for one of two things. One is moving hay, and the other one I'm not going to mention. So
Nice.
it usually involves fertilizer.
Yes.
Okay. Well, I'm live on that screen, but hey, our computer here has stalled.
Oh.
We're-
Okay.
We're yeah.
Nope, I think we're good now. We're good.
Oh, it's going again. It unlocked itself. I think we're good again. Okay, so we are moving. Yep, we got it. And the Penguin Moon Miner is on the move. So what's your strategy here?
Strategy is just to, we can also use our bucket as a somewhat of a plow. So if we get in a situation where we have a buildup of regolith, we would be able to push it into the berm. But kind of just go back and forth. Today we won't be testing our autonomy, but tomorrow we plan on doing that, at least at the very end.
Oh,
Get some
that
additional
was
points.
very interesting motion on that robot. With most skid steers, you see them kind of pivoting that, but it really kind of swung the tail around.
Yep.
That is fascinating.
Very heavy in the back end, so that allows for that.
Okay. And that's actually ideal too for pushing material. Okay, and we'll see. So the bucket itself, are you able to raise and lower that? Or
We are. We do have a stepper motor that allows us to raise and lower the bucket, yes.
Okay.
And then we have two 45 kilogram servo motors attached to the bucket. Have had some issues with those,
Yeah.
I'll admit, but hopefully we're good today.
Yeah. Get a nice little rake in the material there and kind of scrape that forward.
We do have an onboard camera, so.
Yeah. You can see that up there on the mast, so they're able to watch that real time as they're mining.
Yes.
I noticed one of the things going on here, and it's always a challenge, is that terrain. You know, just when you
is.
think you got your bucket set at the right depth and you move,
Mm-hmm.
and then you wind up hitting a hump or you hit a gully, and the next thing you know, you're not engaged at all. You're engaged too deep,
Mm-hmm.
and then things become a real challenge. And there now, all of a sudden, we thought we had it right. We got too deep. I noticed it rotated in on you a little bit there.
Yes.
Yeah. But hey, it looks like you got a good bite there.
Mm-hmm.
Good amount of material. Sometimes we stumble onto things. We find that a better strategy, we kind of stumble into it, and it becomes our way of operating the robot through testing.
Yes.
And that's why it's so important in engineering to do the testing along with the analysis. So, okay, so we have two sorties into the berm box. For those who are just joining us, a little while ago we got to hear from NASA, the winner of the construction award, which is what we're doing here as well. But in Florida, the winner of the construction award at the NASA Lunabotics Challenge was the University of Illinois at Chicago. And the overall grand prize winner at the Lunabotics Challenge was the University of Utah. So my congratulations to both those teams. These are first-time winners of those awards at the competition. So it's very exciting to see new teams making success at the competition. And we hope to see them again next year at the competition. We hope to be there as well. This is CoSMiC, the Collegiate Space Mining Challenge at Iowa State University in Ames, Iowa, sponsored by the Cardinal Space Mining Club of Iowa State University. So this is Youngstown State Penguin Moon Miners in the Lunar Arena that we have here, which we have nicknamed the Box. And they are digging up crushed lime rock. Oh, wow, got a good scrape there. Very nice. We're only 5 minutes into the run and they're already getting some good material deposited. That seems to be a very efficient motion going back and forth like this on the robot. Is that's the way you usually intend to drive this thing?
We did. We had a few different design criteria that we wanted to meet. Like I said, we wanted to stay low profile, keep the center of mass pretty much down low and towards the back, as we kind of have like a rear wheel design. It allows us to be able to push back onto the back wheels quite a bit, so you don't out torque the servo motors.
Yep.
And
you almost look like you have enough room there for a third wheel between each of the two.
Yeah.
That'd give quite a bit more traction. I'm going to turn this on for our people in the arena or in the stepatorium.
Our primary goal for this year is to pretty much just build a foundation for future teams because, like I said, this is our first time competing.
Yeah, well, it looks like you got a very good start. This is a very successful system for a first year.
Thank you.
And what we found too is oftentimes the simplest designs are the best. So one of the big things I'm often teaching my students before you get started on design is first take stock in what technologies you have available to you as far as tooling and what you have availability for parts and that. And that will never steer you wrong because then you'll most likely have the most efficient design that you can create from a cost and a functional standpoint, because then you'll focus on a design that works within the limitations that you have rather than struggling with design because now all of a sudden you design something you can't build.
Gotcha.
Yeah. Of course, our other big challenge in engineering is, and this happens all the time, you get a group of engineers together and they're brainstorming and trying to figure out, okay, what are we going to do? And then somebody comes along and says, hey, wouldn't it be cool if?
Just
yeah. And that's where the trouble usually starts.
Yeah.
Because was it something we really needed to do, or is it just something we want to do because we're bored and we want to do something exciting? And it usually does not end well for us as engineers. So I'm always coaching my students constantly on that. Stay focused on the goals, stay focused on what it is that you're trying to do specifically, and you'll do well. And it looks like you're doing pretty well here. I mean, we've now had at least 7 sorties into the berm box, dropping fair amounts of material. And given the size and the weight of this robot, this is a very efficient operation, very impressive. I like the pattern these wheels make in the regolith.
Thank you.
It's very interesting.
That is something we'll have future teams look at to make more efficient. We didn't have too much time to really look into the wheels. We were given them from last year's team. That was the only thing
Oh,
we had provided to us. So,
okay.
like I said, did the best with what we had.
Well, I'd have to say they're operating quite nicely. So, yeah, I mean, you haven't gotten anywhere near close to stuck yet. They don't dig in too fast. That's the biggest challenge on these too. If you have very tall grousers versus very small grousers like what you have here,
Yes.
there is an optimal height for getting traction. Hey, there is a very good scoop of material coming in on this little penguin miner, and let's see how that next dump goes here. Now the bucket does rotate. Can it be picked up as well as far as height?
Yeah, like
or-
I said, we have a linear actuator connected to a stepper motor that allows us to move up and down. It's just we are limited by the low profile of the robot.
Okay.
I've seen other teams have like kind of a system where they're able to elevate it significantly higher than their robot's frame.
Yeah.
Something to consider for future teams.
Yeah. It looks like to me that your drivers have come up with a strategy on how to push material and get a very good bucket load out of it.
I'm extremely proud of him. He hasn't had too much exposure to testing. Like I said, we had a 7th member that had to be cut, and we were planning for him to be the operator. But very proud of our team member Bryce.
Well, we're only a third of way through your time, and look how much material we have already. I'm a little concerned about are we going to have enough material left in the arena by the time you get done here?
I hope that's the main issue.
And out of such a little robot to boot. So. What's kind of fascinating about this is your team and your little robot are making this look very routine.
Yes. Kind of encourages me for tomorrow being able to test the autonomous mode.
Yeah. Yeah.
Maybe a good strategy here after you get a few more loads is to be able to smooth out the berm collection here at the bottom of the bucket.
Yeah. Create a ramp for yourself to drive up on. And,
Exactly.
Yeah.
Because we are limited by the amount of height we can get up the bucket.
Well, we'll see if they can figure that out. It looks like another good load. Getting right there to the back of the Now, one of the challenges, of course, is the time delay between what you see and what's actually happening, and getting the robot in just the right location as you're doing your digging and you're moving, because a lot can happen in 2.5 seconds when you're on the move.
I'm not sure how much it is affected by the Ethernet that we have provided, but we did a very good job of optimizing the camera delay, and I believe we almost got it to pretty much nothing.
Wow.
We were testing that out earlier in the pit,
Okay.
so I'm not too sure how much delay he is dealing with.
Yeah. Looks like he's going to take another. Oh, is he going to
You
try to
go for
move
the
that
rock.
rock? Oh,
It'd be impressive if we can get it there.
yeah. Sometimes the best strategy on these rocks is if you can roll it using your bucket and roll it, if you have enough power and the actuators to get it to roll. And this one's just round enough. We watched one New Mexico Tech roll a rock out of the way.
Mm-hmm.
Then they actually picked it up later and deposited it
In the
into
berm.
the berm. Yeah. Got to be very careful he doesn't get his bottom hung up on there. He won't be able to back out of those ruts that he's digging. How much ground clearance do you have underneath that?
I'd only say about half a foot, if that.
6 inches?
I would say so.
Kind of looks less than that to me first glance, but
I'd say about 4 or 5 inches.
4 or 5 inches, yeah. What sort of motors are you using in this robot?
So we have SparkMax motor drivers that are controlling the wheels.
Okay.
And we have those hooked up to our motors and our gearboxes. And we have 100 to 1 torque rating on the gears.
Okay.
And like I said, for the servo motors, the rotational actuator, we have 45 kilogram servo motors.
Uh-huh.
And our stepper motor is actually $3. Yes.
Wow. The motors you're using, are they Neo motors?
They are Neo motors, yes.
You know, which is the same company that offers the SparkMax motor controllers.
Yep.
Yeah. A lot of the components that get used in this competition are actually from companies that supply parts for First Robotics. Were you ever involved in First Robotics?
We were not.
Okay. We have a number of our club members that were involved in First Robotics. That's why they get to know these parts very well.
Mm-hmm.
We've done a lot of work this semester in senior design. I had 3 different teams working on Cardinal Space Mining sponsored club projects. One was working on a orbital gearbox using strain wave technology gear drive through a double reduction, making a 200 to 1 plus reduction gearbox.
Wow.
All 3D printed.
That's impressive.
Yeah, but it doesn't have the torque capacity yet that we want, so you need to do some more development on it. But very successful in creating a design that's plausible and could be seen in the future. I had another team taking Milwaukee Fuel cordless drill, brushless cordless drill. 2 semesters ago, we did a team project or a club senior design project to take the drill apart and hack it and turn it into a robotic drive motor. But in the end, when we got it done, they did a very nice job at it. We still found that the speed ratio wasn't quite optimal, but it was still a little too fast, even though we had it in low speed for the
Yeah.
drill, just too fast for the robot. So this year, for the spring, we brought the project back, and I challenged the team to add a another ratio onto the drill motor unit, and they could do it any way they chose to do it. They found a P6R gearbox with 4-to-1 ratio from Bainbots,
Okay.
just the perfect size. Adapted a hex drive shaft into it, and found that they could take a bunch of material out of the nose of the cordless drill, and they wound up adding an additional drive onto the motor gearbox assembly by adding only 1 centimeter of additional length to it.
That's impressive.
Yeah, and less than a kilogram in weight increase on the system, and gave it the ideal speed range. So we might be seeing if we can use that, and it runs off a SparkMax controller.
Cool.
And the beauty of it is that these Milwaukee fuel drills, they have embedded encoders in them. So once you understand how to rig those wires up directly to the SparkMax controller, you can operate as a stepper motor. You can operate it based on speed control. You can operate it based on number of turns.
Cool.
It really was amazing. So we'll see what that does. Total cost to make the conversion was about $300. So not necessarily cheap, you know.
But that's not very expensive.
But a very tough, very durable design, and it'd be interesting to see. We're going to probably share that with other teams to say, here's something you can do, because it's always a challenge to get a hold of these first robotics parts. Because whenever first box season comes around, everybody's sold out. Yeah.
Grab some real quick.
And now you're waiting for parts, or you got to learn to buy off season, plan ahead as to what you're going to use. And well, now this is interesting. Oh, it's fighting the rock there, but we're now still 9 minutes left in the run, and he's getting himself fighting with that rock. But we got a fair amount of material in the berm area. This robot is making things look very routine, and that's not a criticism. That is a very good thing, because that's what you want. Oh, he's going to go after the rock again. See if we can move it. One of the things teams kind of decide is, are we far enough into this run where we have a very good chance of placing and being successful? Do we want to go for broke, take a risk, get a rock or something like that in there? If it were me, I'd be saying, you know what, leave the rock alone.
That's what I would do too. I think he did himself in by moving it right in the middle.
Yeah. Well, he's able to maneuver around it easy enough though too. I got good confidence he'll figure that out, and with a little bit of work, maybe he can smooth things out a little bit more in there and make it a little easier to move around. Either way, already at this point, a very successful run.
Thank you.
Fun to watch. And a beautifully simple design. Guys, be congratulated on that.
Thank you.
I do love the maneuverability of this in the arena. Oh, now he's trying to bite a lot more material. I was a little concerned he might be stuck there for a moment, but he's not. Now, for those not familiar with Youngstown State University, what part of Ohio are you in?
Northeast Ohio.
Northeast Ohio?
Yes. Smack right dab in the middle of Cleveland and Pittsburgh.
Okay. Uh-oh. Can't even get the bucket rotated up. I wonder if the servos have gotten tired. Because he's not seeming to control the attitude of the bucket at this point. Have you had any problems with that in the past?
Like I said, we've been testing out quite a multitude of servo motors. We're hoping that these would be the best option for us, but we do have replacements, so maybe it was just the matter of trying to move the rock,
Yeah.
out torque them.
Yep. And that can happen very easily on these things. You go to try to work a motor system, you keep current in it for too long, and next thing you know, you overheat. If it has thermal protection, it trips, and you got to wait for it to cool down to reset, or worse yet, if you get the windings too hot and you melt the insulation on it, they short out, and now you have a dead motor. You got spare parts?
We do. We have 4 extra motors, so I
Oh,
think it'll be good
excellent.
for tomorrow.
Good deal. Well, it'd be fun to hear from you, the debriefing off of this run, and what your mission control team learned out of what they're doing. I'll come follow up with you guys tomorrow and
Thank you.
learn more about this. It's been fun to watch. It's exciting to have you here, and this being your first time through on a competition, doing this, very impressive.
Thank you so much.
As you know, we've been at this a while, since 2009.
Exactly.
You should have seen our first designs. They were really kind of embarrassing, but we thought they were good ideas at the time. Our first 2 designs were kind of named after Wally robot. They were called Artie 1, Artie 2, and we thought we want to collect a lot of material quickly of this material, so snowblower is a very efficient at moving a lot of material. So we thought, well, that should work pretty well.
Yep.
The first year, we managed to burn out a motor and burn out a speed controller and jam the thing up. And after a whole lot of work, we finally got run in. But what we discovered is we had, for dust, we had the hopper that the blower was blowing the material into. We had it sealed, so we wouldn't have dust flying all over the place. Well, all that managed to do, the impeller, because we're working in a atmosphere, and it moves not only material, but it moves air, and it pressurized the hopper.
Gotcha.
So all the regolith that got up in there, and because the chute was an open bottom chute, all the regolith blew out, and the only thing we collected was a few rocks.
That's unfortunate.
So yeah, it was, but it was a lesson learned. So the next year we decided, okay, the chute going into the hopper has got to be closed. The hopper itself has got to have vents on it so it doesn't pressurize. And then we got to make sure that the auger itself that's picking up material has enough clearance that we don't jam any rocks in it. Well, we still managed to jam rocks, so we wound up doing a whole lot of changes at the Kennedy Space Center and put rubber blades on the auger rather than steel blades, and that solved that problem. Gotcha. We got into the arena and we started digging, and we could see that we're picking up a lot of material, but as the robot's running down the arena collecting lots of material, we're watching about a third of it blow right out the vent holes. It looked like a steam locomotive going down the track with all the 2 plumes of regolith shooting right out of the top.
Interesting.
And then the sad part about it is we got done collecting material and we turned around to go back to deposit material, and one of our bogies dropped off the front of our track and we were marooned. And back then you only got 1 run.
Yeah.
And when we offloaded our material, we saw we had enough material in the hopper that we would have placed probably in the top 5, but because we didn't get it back, yeah, so it was just luck. That year, the winning team, Laurentian University, used the bucket ladder, and after watching that, we decided, okay, bucket ladder all the way.
Most optimized.
Yeah. So and so we came back with RD3. That year, we collected 72 kilograms of material in mining. It was very successful. We won the mining portion of the competition, but we lost by a half point to, you guessed it, University of Alabama, who had autonomy going. We had some autonomy going too, but they took the grand prize and we took second on the grand prize. But it was a fun year.
That's good.
we learned a lot out of it, and our designs have progressed along that quite a bit over the years as a result. But the main feature of our Iowa State systems are the track drive that we use. Vermeer is one of our sponsors we had through the years, and we learned a lot about track design from them. And okay, he's got a minute left, and he's still just going to go after that rock. There's a matter of pride, I think, here going on here. Yeah. Stubborn will.
We did originally have an auger and hopper design.
Yeah.
But we moved away from it and just kept the bucket.
Yeah.
Out of simplicity and
Yeah.
mainly weight.
Yeah.
That was the main issue.
The auger design that you had, did you get a chance to test that in any sort of regolith like this?
We did not get to test it. All we got as far as is pouring a bucket of sand into it and seeing how that would operate. But obviously, I tested. I felt the sand. It's not too dense in terms of the material inside, but I feel like in some circumstances, the auger would get backed up.
Yeah. Well, he's got 10 seconds left. He needs to get himself back and make that last deposit. And nope, he's going to play with a rock instead. All right. Well, very good run for Youngstown State University Penguin Moon Miners.
Thank you so much. Thank you, Jeff.
Yeah, you're welcome. Very good. All right. And looks like next up will be Virginia Tech Astrobotics. Look forward to hearing back from you how the run went.
Thank you
okay,
again.
Take care. And thank you for being here at CoSMiC. Okay, so we got a little work to do to reset the pit. The guys in the box will get that set up, and we'll be back in about 10 minutes once they have a chance to evaluate this berm. In the berm box, we got a nice amount of material for the size of robot here deposited. It's going to be fun to see what that volume looks like once the counting is done. This is Jim Heisey at CoSMiC at Iowa State University in Ames, Iowa. We'll be back in about 10 minutes. Pull the
robots
mic.
coming in?
Okay. 20-minute setup time? Okay. Okay.
That makes sense.
All right. Well, I'm going to go ahead and leave this mic off for the Stepatorium since there's very little people in here watching. Don't need to burn that thing up. In fact, I should check to see how the battery's doing on that.
Does that one broadcast to in here?
Yeah, that one's just for in here for
Gotcha.
people.
Yep, Virginia Tech.
Yeah, we're down to under half battery on this. So it needs to be plugged in and charged. Want to just... Okay, and this is the mic that broadcasts
All right.
on the web, so let's see if I want to change my picture to something. Oh, here's a fun one from Vietnam War. How much you throwing at the enemy? Well, everything in the kitchen sink.
Wow.
So that's off the Enterprise, USS Enterprise. So he's got his extended range fuel tank. He's got, now this one is a Rockeye.
Rockeye?
Yeah, it's a cluster bomb.
Gotcha.
It's for tearing up airstrips or taking out troop emplacements.
I think we don't use those anymore.
No, they're outlawed.
Yeah.
And these are your World War II general purpose bombs. This single engine, and it was called the SPAD in Vietnam. It's a Douglas A1 Sky Raider.
Gotcha.
They had a wonderful loiter time, 4 20-millimeter cannons. They could carry as much bomb load as a World War II B-17 on one engine. So they were
That's
quite
a lot of
remarkable
improvement.
Yeah.
That's like the kind of the top end of where they got kind of capped out with the propellers, right?
Yeah, well,
Perhaps?
yeah. Well, that's a 3,000 horsepower engine up top
Yeah.
there.
Just looking at the pilot compared to the size of the
Yeah.
engine versus the other planes.
Here's another fun one. This is B-25 nose art. The ink squirts.
Ink squirts.
So there was some very creative nose art in World War II.
Yeah.
And all of these crew up here and the pilot and all that. Yeah, I thought that was
Yeah.
pretty funny.
Yeah, that is.
Yeah, and then last one here that I have on this selection of stuff that we have going on. And this is a colorized picture of a British Spitfire from World War II. And seriousness of that pilot. But
that looks nice.
Yeah.
Did a really good job with the colorization.
Yep. Brings reality into, but you can see the quality of the paint on some of that and how things were painted onto the aircraft. You know, it's a war machine, so nothing was ever done to too much elegance.
I just noticed that your cursor's an F-117.
Yes.
I hadn't noticed that. That's fantastic.
I am a bona fide wingnut. I love airplanes.
That's fantastic.
So I'll go back to my text in here. And okay.
Just don't turn it on. We can't find the charger for it, but just don't
Okay.
turn it on until.
Yeah, well, if I get a bunch of people sitting here, I'll turn it on. Otherwise, I'll leave it off. We'll just go with this mic.
Have there been many people in here?
It varies.
Gotcha.
Yeah. If they've done their run, they're going to head out. Now, this is a very interesting track design that you've got on here. Tell me about this.
So the track design, we've used the track design several years in a row now,
Yeah.
but it's not been the same design.
Mhm.
We've been trying to improve it over time. Actually, just this year, and I'm not certain about last year, but this year for sure, we've had a senior design team working separately to develop a new track design, which will hopefully come in next year. And that one's based on 3D printed, replaceable modular tracks.
Yeah. Who's your advisor?
So our advisor is Dr. Kevin Chimpall.
Yeah, I know him well. Yeah.
Oh, yeah?
Is he here this week? No.
No, he's not. I think he's with the group in Florida.
Oh, you have a group in Florida
Yep,
too?
we have a group here and a group in Florida.
Really?
Yep, the Florida group just finished up. Well, earlier on the broadcast, we heard that the UCF or KSC.
Yeah, I was
finished up.
reading off the award.
We didn't make
winners
it to
at KSC.
KSC. We were knocked out at UCF. Was
Okay.
that exactly how it should have been? That's a little bit up for debate, to
I
be
was,
honest.
but I was
that's nothing
excited to
new.
see the
Yeah,
winners. The other thing,
it's really nice to see him.
yes, it's nice to see anybody but Alabama taking in the top prizes because they've dominated for far too long, and I wanted to see other teams get the opportunity to compete and win, and for all the teams to sense, we can just knuckle down and do things right, we can be there too, and we've seen that. Now the other thing I'm really excited about here, you got a chance to see New Mexico Tech's run here.
I did not.
Oh,
I
they
don't
they deposited a lot of material.
Oh yeah.
Yeah, they had a huge pile
Okay.
in the berm area. I got a chance to see University of Chicago or University of Illinois Chicago their last run.
Gotcha.
And our run here was more material than they deposited. They had a good run
Oh, at the KSC.
at KSC.
Gotcha.
And they won the construction award.
Oh, nice. Oh, wait.
For
So that means that
Yep.
the new thing here is probably better than theirs.
Well, not necessarily. Well,
Not
it could
necessarily,
be.
but could be.
Could be.
Could
be. And if we can have this competition come out collecting more material than they did at NASA, and we've got 5 of the top 6 competitors from last year here at this competition, then that's just really nice to have that opportunity here in this competition, that we could have that same level of success, especially first time out of the box doing this. So really quite exciting that we can do that. So
from a competitor's point of view, it's gone very, very well.
Yeah. So tell me more about your robot, size, weight, its collection systems, more about the design.
So our robot weighs about 70 kilograms, 150 pounds.
Yeah.
Our collection system is a front-loading bucket that then dumps to an internal container in the back.
Okay.
And that internal container expels the regolith using a conveyor belt.
Okay, so it has a live bottom in it, so to speak.
Yeah. The bottom kind of moves around inside.
Well, it just is a belt that moves everything out.
Yep.
And a few years back, I was talking with our club, telling them that we should do the same thing. We should come up with a live bottom, because that way we know for sure, because before we were using dumping hoppers, and you have to get that way up at a 50-degree angle to get the material out.
Yep.
And then there's the whole issue of CG shift and everything. It's a little more weight with a live bottom, but the one thing you can be guaranteed of is when you want the material out of there, it's going out of there.
Yep.
And as long as you don't make it go too fast, you're not going to sail it over the receiver.
Exactly.
And that's happened to a few teams in the past
Yeah.
too, where we've seen that happen. So
last year we had linear actuators doing a whole dumping bucket.
Yeah.
Like you would a dump truck, like you were just saying.
Yeah.
This year we're changing it up.
Well, give my regards to your advisor, Dr. Shimpaw, because I always enjoy spending hours sitting down talking with him at the competition.
Yeah.
So it's too bad he couldn't be here, but we're certainly excited having you guys here to partake in our little best kept secret in the middle of a cornfield. So let's see more about your robot. What sort of motors are you using in this robot?
So I think the primary motors are Krakens.
Yep.
They're being driven by SparkMax ESCs that also they have internal encoders. I believe,
Okay.
So
Yep.
that we can very easily get the position data back to our controller, and we can work based on
Okay.
that
What sort of
information.
gearbox do you have the Krakens hooked up to?
So I believe it's a 3, a 2, and a 2, so it's a 12-to-1 overall.
Okay. 3, 2, and 2. Yeah, 12-to-1 overall.
I'm pretty sure what it is.
Any chain drives in there past the gearbox?
No, we don't have any chain drives or anything in there.
That's pretty fast drive.
Yeah, it is pretty fast, but we control it. We control it.
Okay. So you're not running the motor at full speed in here when you're driving it?
No, I don't think so. I think we
Yeah.
would take off pretty fast when we do that.
Those are
but-
pretty power hungry motors, those Krakens.
Yep, they are.
What are they rated at?
I don't know off the top of my head right now, but I do remember us from it's a very similar bot that we sent to UCF in Florida.
Yeah.
And we were very, very high on the power draw because of that.
Yeah, they're very current hungry, and yeah, I've been evaluating a lot of different motor systems have been used through the years, and the Falcon 500s and especially the Krakens, I think, are a step beyond really what ideally you would want to use in these situations. So we've been doing a lot of work this year on alternative drive systems to try to figure out what is optimal.
I think last year we used Neos
Yeah.
But I was just hearing from another team this year that they used the Falcons, and the Falcons were burning out.
Interesting.
So I don't know exactly what they're using the Falcons for, but I think it's a
Well,
very
here's what can happen. They can burn up in one of two ways. And first and foremost, if you don't have enough reduction on the motor such that you try to run it and the torque load on the motor is more than it can generate at the voltage that you're running at, you can stall it and burn it out
yeah,
that
that's
way.
true.
And then the other way is you do have the optimal gear, but you wind up being too aggressive with the way you're running it, and wind up running it past its peak power point, because you can either overheat a motor by running it at stall for too long, and that usually takes just seconds or minutes depending on the motor design,
Yeah.
or you can spend too much time beyond its peak power point, because once you get past peak power, now the motor's running really inefficient, so it's generating more heat than it can cool, and you'll burn it up that way. It just doesn't happen as fast, but you'll eventually
Yeah.
burn up the motor. And so that's the big thing here. And of course, with the Krakens, the way they have it designed, it's designed so it could possibly mate with the Vex Pro planetary gearboxes, but those gearboxes are so small that they don't stand a ghost of a chance surviving under a Falcon 500 or a Kraken. And those are nice light gearboxes. They're kind of expensive, so you wind up usually using a Bainbots gearbox or something from Robot Shop or something like that. It winds up being a much bigger, heavier gearbox just to put up with the power of the motor. And ideally on something like this, your track drive system, where did you get that from?
Say that one more time.
Your track system, where is that from?
So the track system, I remember last year, I think we sourced it from a specific company. But I think that last year we also had a senior design team working on tracks.
Yeah.
So I think that we may have partnered with them to get this year's tracks. Although it may have been the same as last year's. I was not directly involved with that, and so I don't know off the top of my head.
Now, is this part of senior design class, or are you a club?
So we're a club separately, but we sometimes have some sub projects that get shunted off, like usually research for like future years onto a senior design project.
Yeah, that's what we do here at Iowa State as well. We have about 40 to 50 members in the club, and this year, for instance, we had 3 kind of R&D projects. Well, actually 2 R&D projects, 1 outreach project in senior design. We had a project on an orbital drive, a project on a drill motor drive, and then our 3rd project was finishing up our work on our Wally robot, which I hope you guys get to see tomorrow. So we have an operational Wally.
Wally, like the compactor.
Yes,
Oh, yeah,
yes,
fun.
the Pixar Wally. Yeah, he's going to be our outreach ambassador.
Oh, that's cool.
To schools. We had one back in 2012, took him with us along to the Kennedy Space Center, and the reaction at the Kennedy Space Center was phenomenal, especially from the kids. We even have a fun video. If I can figure out how to play it tomorrow, I'll get that done. But back in 2012, NASA Edge, NASA's STEM education show that they run, was broadcasting at the competition. And we crashed their broadcast with the robot, and they wound up interviewing Wally. And it was hilarious what we did. And but what was fun is anybody went, well, where's Aaron? That was the student who built Wally. And all I had to tell him was, just stop and listen. If you hear a bunch of kids screaming, that's where Aaron's at. So now Aaron Hill, it was his robot, so he took Wally with him, and we missed having Wally. So I decided we need to make a Wally, and looks like we're going. So okay, we got a run going here, Max. We don't have movement yet, but something tells me that's going to be going here pretty soon, as they get fully connected. So
all right.
I have to say, though, that is a very nice looking robot. The paint trim on it, the fit and finish looks excellent.
Actually, we actually had all of the parts. Once we manufactured them, we were actually able to partner with a local company in Virginia to get them anodized.
So
it's not just painted.
It's anodized. Oh, even cooler.
Yeah, we went with a red and black paint scheme to we thought that fit where our robot this year is Reaper.
Yeah.
This one specifically, since we do have the 2, This one
Yeah.
is Grim.
The Grim.
It was the first one.
Oh, Grim and Reaper.
Yeah, Grim,
Oh,
Grim and
wow,
Reaper.
yeah, that's
But
beautiful.
Reaper, it's like regolith, excavating, pathing, autonomous. I
Regular
don't remember.
excavation, autonomous pathing, excavation robot. Yeah,
I have it written down
something like
somewhere.
that.
It was a
something.
acronym. We came
Oh,
up with Reaper and
that's
we're like, we
beautiful.
could figure something
That's
out.
the fun thing about engineering. We come up with all sorts of
Yeah,
acronyms for
yeah.
things like a few years ago, we decided that our robot's name would be named after the Roman god of blacksmiths, Hermes. And
Hephaestus?
no, well, Festus. No,
Well,
it was a
Hermes.
Greek god.
Hermes. Greek god is Hermes. Hermes is Greek god of like messaging.
Messaging, that's it. Yeah. So it was a Greek god of messaging. Yeah, that the reason I say Roman god of blacksmiths because
Vulcan.
they wanted to name it after that, and the club didn't choose that. They chose Hermes. But
Yeah.
one of the club members came up to me and said, "Heisey, I bet you can't make an acronym out of Hermes." And no sooner he said that, and I said, "High efficiency regolith mining excavation
Hey.
system."
That's perfect. That's perfect.
Yeah, it's perfect. And we used that name for several years, and then we went to Mars and for Martian autonomous robotic system, and well, we still don't have any motion out of Reaper here.
Yeah.
Yeah, but you know, communications issues can often be the bane here of what we have going on.
Yep.
Can't get all the systems to hook up and communicate. So hopefully we'll see some movement here in a little bit. Otherwise, it's going to be a long 30 minutes.
Yeah, we'll see what's happening in a little bit.
Yeah, so we chose different names that went along with the Mars robot, and one of the more memorable ones was Mars Pavonis that we used, and that was the name we chose for the robot the year after we had stayed in Cape Canaveral for the competition. We had Mars 1. Trying to remember. Oh, that was. Well, I can't remember the name of it, but it had a lot to do with navigation. I think it was Marinaris, Mars Marinaris, and then Mars Pavonis is what we named after Mount Pavonis Mons. And Pavonis is a Greek word for peacock, because the year before we had stayed in Cape Canaveral and at a B&B there. And it was next to a state park, and the state park was infested with wild peacocks. And there was peacocks all over the neighborhood, and so the students, I told them, find a geographical feature on Mars, and they found Pavonis Mons, which was named after peacocks, and I thought that just
it just works,
just fits.
It just fits.
And we had all sorts of misadventures with the peacocks. And for anybody who's familiar with peacocks, they're a most obnoxious bird. But then after the Mars systems. Mars Atlas was our last one that we had. Then our current robot name is Lance, and that stands for Lunar Autonomous Navigation, Construction, Excavation System. And yeah. Okay, so we're going to scrub this run, and they'll get another chance for their first run. Or not. Yeah, okay.
Ooh.
Oh.
I might be up late tonight.
Yes, you are. Well, good luck with that. So we'll scrub this run. But Max, I'm sorry that
it was good to meet you.
But it's good to meet you. We're very thankful to have you here as part of the competition.
Thank you.
Taking part of that. And again, give my regards to your advisor, Dr. Shimpa. It's too bad he couldn't be here, but sounds like he had a good time down in Florida.
Thank you.
Once again.
Yep.
And we
Well,
look
it's good to meet
forward
you.
to seeing you run tomorrow.
Look forward to seeing you tomorrow.
Okay. Well, shoot. Had another missed run, but that's the way these competitions go. You're not always guaranteed success. You get in there and you wind up with a glitch with electrical connection or a bit of software. Or even just plugging a wire into the computer and not getting it to run. So these are the heartaches of the competition. And when you're successful, it's wonderful. When you're not successful, well, you're going to be up late working on some few things, because that's what we engineers do. We got to solve the problem, and it's up to us. There's no hoping. It's all about doing the work and the analysis. So My hats off to Virginia Tech for being here, and I wish them best of luck. The best part about this is, unlike the NASA competition, which takes the average of 2 runs, we take the best run that the teams do. So they still have a very good chance of being competitive if they can get all their problems fixed and be ready to run for tomorrow or Friday or Saturday whenever their next run is going to be. So it looks like we'll be getting Creed up next. That is the team from, get that looked up here, from San Diego State University is going to get ready to run here next. And we just might be able to get done close to on time. We were intended to be done here by 7 o'clock, and we'll see how this works out. We got contingency time tomorrow. So once we get Creed through here, we may shuffle the UND Lunabotics team to tomorrow, and maybe get a good night's sleep for a change. Pits are open until 11 o'clock, and the teams will be down there working on them, and then we shut things down, and they'll open back up at 6 in the morning, and then we'll be here ready to run the next runs at 9 a.m. on Friday. So we hope for those of you who've been watching online, that you'll join us again tomorrow to see more of these runs, and we hope to have better success, more activity going than we have today. But again, as mentioned, this is our first time doing this, and this is a 100% student run. Yes. Yes, I have that here. So perfect. Thank you. Stay tuned. We will have San Diego State Creed team in the arena, in the box here pretty soon, because we don't have to spend any time redoing the surface in there, since unfortunately Virginia Tech Astrobotics wasn't able to move or disturb any material. So we're pretty much have the arena ready to go, and we'll get the team in here and be ready to go in a little bit. Again, my thanks to all our sponsors who are helping us make this reality. Seek Sensor Intelligence, Caterpillar, Danfoss, Mechdyne, Collins Aerospace, the Iowa Space Grant Consortium, and the College of Engineering at Iowa State University. So we appreciate all of them for their support, for our effort in putting this space competition together, and we look forward to more runs. Going to make their next attempt at a run in here, and we're going to do it this time, right?
Yes, sir. This is the
Okay.
real thing.
Yeah. Well, I don't know if you heard the results from the NASA competition down in Florida.
I think I did. It was Utah, right?
Yeah, Utah won the grand prize. The University of Illinois Chicago won the construction prize. That's the mining award.
Okay.
Yeah.
Gotcha.
Now, I watched their last run. I don't know if that was their best run or not, but I have to say that our run from New Mexico Tech looked every bit better than the University of Illinois Chicago's run did down at NASA. So
Definitely says something.
yeah, well, that'll be interesting. I would like to think that on our first time out here, we could have an equally good competition to what was run down at NASA, since we're doing a lot of the same things that they're doing. And we have a lot of very good teams here, including yours, here competing, and so that we could get some comparable results out of this. And I know our administration at ISU is very excited about this, what we're doing here. We're very excited about it, to have the opportunity to put it, and very pleased to have you here. So being here as a part of the competition. And
our team is very excited to be here.
Excellent, good. And we're hoping you're enjoying the hospitality here in Iowa, called Iowa Nice.
Yeah.
And where'd you go to eat last night, by chance, out of curiosity?
We went to this Japanese restaurant, I think down the street. It's called Ichiban.
Ichiban, yes, yes. That actually is run by a former student of mine. He's a
Oh, no
mechanical
way.
engineering graduate. Yeah,
Oh,
Ichiban.
that's awesome.
Yeah,
some
I'm
legacy
sure
there.
it was excellent.
Yeah, it was very good.
So what'd you have down there?
I had a chicken teriyaki bento box
Oh.
and a sushi deluxe plate.
Sushi, yes. Everybody's got to have sushi when they go to a restaurant, a
Yeah.
Japanese restaurant. We also have Fuji Steakhouse, which is excellent too. You'll have to try that out.
Fuji Steakhouse.
Fuji Steakhouse, yes.
Sure, remember that.
Yeah, and but before you go, you got to try Hickory Park as well.
Hickory Park.
Yes.
Is that like a barbecue?
Barbecue and ice cream shop.
Whoa.
So make sure to save a little room for ice cream because they have the best ice cream desserts that
Alright.
you'll find. Yeah.
Hickory and
Hickory Park.
Fuji Steakhouse.
Fuji
Okay.
Steakhouse. But we got a lot of excellence. Downtown on Main Street, we got Cornbread.
Cornbread.
Yeah,
Okay.
another barbecue place. They have excellent brisket and burnt hens.
Ooh.
Yeah.
Brisket
Yeah,
sounds
and
really
they have a
good.
killer mac and cheese down there too.
Oh.
Yeah, you're not going to get out of here with losing weight. That's I can guarantee you
bet,
that. Yeah, you know, you're in the middle of the heartland. We eat very well out here, as you can tell. I don't mean to be a rolling commercial for Ames, Iowa eateries, but we do enjoy our restaurants that we have around here in town. Also, there's a great little sandwich shop over here.
The deli, right?
The deli.
Yeah.
Did you go there today?
I didn't go myself. A couple of my friends went though.
Yeah,
earlier today.
yeah. They have the juiciest sandwiches you'll ever
Really?
have. Oh yeah, they're messy, but they are so good.
Those are the best. Though.
Oh yeah, yeah. I had a Reuben today over there.
Oh.
I've been dreaming about going over to their sandwich shop. I decided today that the club can order their pizzas and have the pizzas. I'm gonna go have me a West Side Deli sandwich, and
there
I
you go.
enjoyed every bite of it.
Yeah.
So wonderful stuff. So tell me about the team again, for those that haven't heard us talk earlier.
Yeah,
So-
sure. So we're a senior design team at San Diego State University. We're comprised of 2 mechanical engineering teams, each 5 mechanical engineer
Okay.
students, and then 1 electrical computer engineering team,
Yeah.
also 5 students, so 15 team members total.
Okay. And it was done all part of a capstone.
All part
design
of the capstone project. We started back in August, so it's been about a 9-month journey.
Yeah. So tell me a little bit about the robot too, for those that haven't heard earlier.
Yeah, sure. So, kind of like how we did in our last talk, I can break it down into 2
Yeah,
different.
yeah. We're
subteams.
just repeating the same thing. So
Yeah.
this is part of what you get to do when you're doing MC. When
Mm-hmm.
you come to a run, yes, you might have a lot of the same people online, but you're going to have a lot of people who haven't seen it yet.
New people.
So you repeat it, and so that the people who weren't here the first time can get the benefit of the information that we'd said the first time around.
Right.
It's not like a class where you got to take notes, and if you weren't there, too damn bad.
Mm-hmm.
But no, in this case, we want people to have a chance to know more about you and your team and the robot that you're bringing. And so
Yeah.
describe a little bit size, weight, what its main features are.
Yeah, so we're like just under the competition dimensions. We just did our inspections, but we are weighing at 151 pounds right now.
Okay, so pretty sizable robot. I think
Yeah.
the max is like 176 pounds you can go up to.
Mhm.
So you're getting up there. But the good side of that, though, is you have weight to work with in order to move material. You get too light, you can't push those rocks that we
Yeah.
have in there
Yeah, you
unless you
definitely need that.
load yourself up with a lot of regolith. And so you do have some weight. And
It
then you
also
better.
helps with balancing too.
Yes, and then you have to pray your motors are strong enough to be pushing that rock if you're going to be pushing it. So,
Absolutely.
yeah.
So, I guess with the excavation system, it
Yeah.
uses this bucket ladder mechanism on a conveyor belt.
Okay.
It's driven by 1 Falcon motor.
Okay.
And it has 1 degree of freedom. It slides on a linear slide rail.
What
so-
range of motion does it have? How high and how low can it go?
Oh,
See, I probably asked a little technically difficult question, didn't I? Because you probably weren't on that team.
yeah, I was on the drivetrain, but I want to say
Yeah.
around 5-6 inches.
Yeah, that
of
sounds pretty normal.
vertical
Yeah.
movement.
Yeah.
So, yeah. And then with our deposition system, we went with an active, what did I call it before? An active slide.
Yeah,
tray.
you got a
Um,
flat belt in the bottom of the hopper, so to speak, or an
Yeah,
active tray.
so
Yeah.
we got a conveyor belt in our hopper. It's angled.
I
so
called
that-
it a live bottom.
a live bottom. There
Yeah,
you go. There you
yeah.
go. A live
Yeah.
bottom.
Some of these big road hauling trailers that you see that haul material, they call those belt systems in the bottom of their big trailers live bottoms.
Live bottoms.
Yeah.
Gotcha. Yeah, I did hear that term.
It's a trucker term.
There There you go.
10-4, good buddy. Okay, so what's your capacity then? How much regolith can you hold in the robot when you got her loaded up?
I believe it was around 150 pounds
Okay.
when we tested on the beach with
Well,
Sam.
come on, it's got to be kilograms here. We're doing everything metric here
Okay,
because
so
it's NASA.
that's like 70, around 70, 75
Yeah.
kilograms.
Yeah,
Yeah.
it could be. Yeah,
Okay.
2.2 pounds per kilogram, right?
2.2 pounds per kilogram.
Yeah.
Correct. Yeah. So that would be around 70-ish.
Yeah, yeah.
Okay.
Yeah, and I always have fun. So much in engineering that we do days is caught between the English system of pounds and inches and feet and
So many conversions.
and then metric, which is meters and newtons and kilograms. And I have a class I teach in vehicle dynamics, and yeah, the students struggle between, do we use kilograms mass or do we use newtons? And you know, and then they get lost between the ratios. Well, if it's pounds, what is it in kilograms or what is it in newtons? And yeah, they struggle with that. Then I ask them the very simple question: well, how many newtons in a kilogram? Do you know that one? Yeah, see, I'm sorry to put you on a pop quiz, but it's always a fun little thing to do. What's the acceleration of gravity in metric?
Meters per second squared.
Well, neither, but what is the value? What's the number?
Oh, gravity?
Yeah, gravity, acceleration of gravity,
9.81.
9.81.
Yeah.
So how many newtons in a kilogram? Anna knows the answer already. She's grinning over there. I know that.
I'm stumped.
You're stumped. 9.81.
Oh.
What's the
okay.
definition of a newton? The force required to create 1 kilogram mass to go 1 meter per second squared.
Kilogram meter.
And if the acceleration of
yeah.
gravity is 9.81 meters per second squared, then it's 9.81 newtons per kilogram mass.
Okay.
Yeah, or kilograms force, I should say. Kilograms force, kilograms mass. We get confused, but it's like pounds mass versus pounds force. That gets confusing too in the English system. All these things that we have to put up with as engineers that just drive us nuts. But it develops our character, you know, so to speak, because we have to put up with all these crazy things. So back to your robot. Sorry for that little trip down
No, it's
quiz
always
lane.
fun learning those little details.
Yeah. We have to make sure we get our units right so our satellite gets to Mars as intended.
Right.
As the old legend goes.
Mm-hmm.
Do you know they actually found that satellite? It did not miss Mars.
Oh.
Yeah, it hit it squarely. It was intended, for those who don't know the story, NASA had an intern working on a satellite project they were going to send to Mars, and they sent it up there and they lost it. They thought, gee, maybe it missed Mars altogether. And it turned out he made a error in unit conversion. And years later, they sent the Martian reconnaissance orbiter to track things so that they could send their robots, the Spirit and Opportunity, Perseverance and Curiosity on there. And while it was orbiting Mars, they found their orbiter that they had lost. It actually had gone in too shallow, and when it got around the backside of Mars, it impacted the planet's surface.
Wow.
So they didn't miss Mars. They just didn't get it inserted into orbit. They hit it squarely.
Yeah, they were a little bit too accurate there. Well.
Yeah, maybe a little too accurate. So, you know, it's not much of a consolation prize for the poor engineer who messed up that calculation, but
right.
That's the way things go sometimes. So here we are. We got the Creed robot in the arena.
Yeah.
Those massive drive wheels. And it looks like we got movement. That's a very good sign. So we've got operation.
We're hoping those big wheels will help us with that traction. Same with those cleats. So.
See if you guys can get as much material. Now, you did a practice run earlier, not a competition run. And so it'll be interesting to see here if you guys can get as much material collected as New Mexico Tech did. They had a very impressive run, a very nice operating robot. That thing moved very well. Of course, they were using a bucket and not a hopper, so it'll be interesting to see if you guys can load this thing up to the max and come in and get that material dumped off and
Yeah.
give us a pile of material like you showed me this morning on your pictures in the volleyball sand court that you tested in the day before.
Yeah, that's the goal.
That was impressive. And if you can do that, holy cow, we might have a real barn burner of a competition going on
Yeah.
here. So we'll see how it turns out. But anything can happen in here, as you well know.
Absolutely.
You know, just because you did that at the park and you had a good practice run here does not guarantee success in the competition run. So, and we've learned that all too well too in the years that we've competed here. We've had years of heartbreak and years of missing it by that much,
Oh, I bet.
and you know, and in 2012 when we won the mining competition, but we wound up taking second place to Alabama, it was by a half point. Yeah.
That's a punch in the
And
gut.
then, yeah, well, then last year we wound up tying with Alabama at the competition for the grand prize. So we've always been there neck and neck. But I was very excited to hear the results for those who haven't heard it earlier, what I said. And okay, they're testing the robot. It's moving well.
Mhm.
Yeah. Okay, so this is the last run for today, and it looks like they're going. So we got the timer going. This is exciting. So we have Creed here from the South Dakota State University running. What do you think their strategies are going to be? I see him just nudged a rock there already and did it quite nicely.
Yeah.
So it looks like he's lining himself up. Oh,
So-
this is good.
We are going to be starting with our autonomous routine. It's time-based, so essentially you'll see in a moment, but it'll move up while digging and then move backwards
Okay.
to deposit back into
And it's time-based, you said. So
It is time-based.
Oh, that's cool because I always talk about time of flight, and boy, that's a pretty fast motion there too.
Yeah. And then it stops, and then it should deposit right there.
Okay, and yep, there they go. All right, and then
And then I believe that completes our autonomous routine.
okay,
So our goal is to try to get everything in between the rocks first.
Yeah.
Before trying to navigate around them and
yeah.
possibly push
Now,
them.
one of the magic things I always preach here to our team about mining is understanding your takt time, as they call it. It's a German term, T-A-K-T. And it has to do with the time interval between your buckets and the time interval between the volume of material that you're sweeping as you go down the mining. Because what you want to do is get every bit of material that you can as you're moving. And so sometimes the fastest motion is not necessarily the best. And you definitely don't want to go too slow because you would like to maximize the capacity in each bucket. And it looks like you just dumped a little material out of the back of the robot. Do you have the belt progressing as you mine in order to?
Slightly. So we do that just to try to even out the top.
Yeah.
While picking up the sand, or
Yeah.
sorry.
Yeah, this thing,
limestone.
oh my goodness.
Yeah.
Yeah. Oh, that is impressive. That's just a very easy offload on that, and that is a very nice pile.
Yeah, and because of the high deposition angle,
Yeah.
you can make quite a high mound with it.
Yes, yes. That is an advantage to size sometimes, you know, to get that exit out as high as you can
Right.
on there. Your robot reminds me very much of a design that University of Australia had. They came to the competition one year and they had a very similar robot. And but what was funny about it is the person who operated the robot drove it very aggressively, and it was very tough. And it offloaded about as equally as fast as yours does there too. And he would come riding up to the deposit bin in the arena and would slam right into it. And then immediately turn the conveyor on, and all this material regurgitated right out of the back of the robot into the receiver and through the screen, just like what your robot's doing here. and they had quite the good success, but they didn't wind up winning the competition that year because the robot was too heavy. It was right at about 80 kilograms.
Oh.
And then they had some communication issues with it because that was the year that we won the Joe Cosmo Award, the grand prize in mining, and the autonomy award. We didn't win the autonomy that year. It was the next year we won autonomy, but we placed quite well. So we won mining, we won Joe Cosmo because we did very well in a number of categories. We had collected in 15-minute run a total of 115 kilograms in that run. But I think you guys are going to do far more than that here, the way things are looking. This is a very impressive digging robot.
Yeah.
Okay, and he's going to back it up for the next run. Oh, wow. I don't think we have enough berm size area for the amount of material you're going to be collecting here. So
Yeah, about 5 minutes in now.
5 minutes, yeah. I mean, just like I was talking with Youngstown State University, their little moon miner robot was making this look very routine. And it appears you are as well. I hope we have enough depth in the arena for what you're doing because you're getting significantly down there.
Yeah, and we're trying to go as slow as possible to maximize how much each bucket's scooping up.
I think you're doing a good job. I think we're going to wind up close to China here before we're done.
Oh, man.
So this is very impressive. Very exciting to see.
Yeah, it seems like it's performing pretty similarly to how we were testing it in the volleyball court.
Well, you seem to be very calm here, sitting here watching this, knowing how well it's running. You should be hooting and hollering and jumping for joy here. With
No, believe me, I'm super stoked for this.
super pumped. I am too. This is exciting to see. Does your robot have a name? What's that?
Go Aztecs.
Go Aztecs. Okay.
I don't think we named the rover itself, but
Yeah, we usually pick a name for ours every year.
Yeah.
Yeah, this year it's Lance. I don't know what
Lance,
name
I
it'll
did
be
see
next
that.
year.
Mhm.
Yeah,
That's the swan.
the swan. Our two swans that we had. Now we haven't had them out in the lake lately because we've had some issues of people injuring the swans. So
Oh,
we pulled
no.
it. But Lancelot and Elaine.
Lancelot.
And even though I feel sorry for Elaine because it's actually two male swans. If we put a male and a female out there, they generally don't stay put. But if you put two males out there, they'll stay in the pond where they're in. And we don't like our swans wandering off.
Right.
And I don't know if you noticed, we've had certainly a lot of geese wandering around here. So watch
I
where you
have seen
step
that.
on the sidewalks. It's been
Yep.
a mess over here. We have several goose families that have set up residence here in the middle of campus.
I did see that.
Yeah, and they can be quite testy sometimes.
Mhm.
The families really look cute, but the mom and dad can get quite ornery.
They tend to not run away
Yeah.
when you approach them. I
Yeah,
noticed
that's
that.
they're too used to people. That's
Yeah.
the big problem. So, they used to be an endangered species. I'm kind of thinking, I think geese should Canadian geese should become a food crop here in Iowa because we certainly have enough of them now.
Yeah.
And the way they move around, we've had bird flu issues and that.
Right.
I tend to want to blame the geese, but I know it's not their fault. They're just doing the best they can with raising a family and doing the things that geese do.
Yeah.
But, this is impressive. You're getting right down there. So, and the
Mhm.
robot has no issue with moving through that regolith. That's
Yeah, those big wheels are really helping us out. Right
yeah.
here.
So your drive system in there, as we talked earlier, you have a chain drive in there, and you're using Falcon 500 motors.
Yes, sir.
And what's your drive ratio on the gearboxes themselves? Out of curiosity, I asked too technical of a question, didn't I?
No, I knew this. I know on the excavation system it's 27-to-1.
27 to 1 gear ratio. Do you have a chain drive in there too, then, or?
Yeah. Yes, there's a chain in there as
Yeah.
well.
What's the ratio on your chain drive? Is it like 2 to 1, 3 to 1?
On
See,
the
again, I'm
excavation
asking
system.
too, yeah, on the excavation,
Oh,
I'm
man.
asking too technical a question once again. I'm sorry, I'm a mechanical engineer. I live and breathe ratios and gears and stuff like that. It's what I do. I play constantly around being a design engineer with looking at motor specs and trying to come up with the optimum drive design. I drive my club nuts because I'm always asking them about what's the next best motor to run. We got to get away from this first robotic stuff that we've been using because it just was always annoying because it's not that it's bad equipment, it's good equipment, but it's just that when first robotics competition year comes around, you can't find anything. It's all sold out. So, you know, and I'm sure you guys run into the same sort of issue with wanting to use Falcon 500s, knowing the right time to buy the motor when they're still available.
Right.
So how many club members do you have that were involved with First Robotics? Any?
Two.
Two?
Yeah, one of which was has been consistently involved for the past 9 years.
9 years of being, you had mentioned that earlier, being a coach for or advisor for a high school team.
Yeah.
Yeah. Yeah, we have a very good nationally competitive high school team here in Ames, Iowa, called what are they called? Oh, you remember what the Ames High School First Robotics team is? The Ames High School First Robotics team. What's their team? It starts with an N. Neutrino. I got it. It's Team Neutrino. And one of their alumni went on. He's now been featured in. You're familiar with BattleBots on Science Channel?
Oh yeah.
He and another member who is a former Cardinal Space Mining alum are Team Tantrum. If you've ever watched any of that. Team Tantrum was the championship team from last year.
Oh wow.
With their bot. And I had a chance to talk to them and I asked them how that experience has been. They said it's been good, but it's a lot of work. And I said, so yeah, I would imagine you're making some good money being on TV. And they said, nah, every dollar we earn goes back into the robot. So, because they're constantly repairing it because, let's face it, BattleBots is very hard on the robot.
Right.
Yeah. But they had some very good success. And it's a very fun robot that they built, which matches the personality of these two people that we had in our club, Alex and Aaron. So.
That's awesome.
Well, this is very cool. We still got 18 minutes to go, and look at the size of pile we've got in that berm area.
Yeah, looking to fill in the rest of the side in the back over there.
Yeah. I think you're going to run out of space. I don't know if we have enough roof height in the arena for what you're going to do here.
I think we're going to try to make a ramp to get to that back side.
That's what it looks like.
Okay.
Yeah. I kind of talked to your team earlier about doing the ramp, and it seems that I should keep my mouth shut. My team won't have a chance here, but that's all right. We weren't competing anyway. We're just happy to have everybody here and do that. So very cool. Very cool. Oh, look at the load in the buckets there. He's really picking up some serious material.
Yeah, they're forming little hills above the buckets.
Yeah. You do like to see that when you can get that done.
That kind of went into our design process as well, because we found that having them mounted onto the belt on closer to the top of the bucket allowed for that hill to be formed. So that kind of maximizes.
Oh, there's another good one. Yeah.
Mm-hmm.
Yeah. What angle is your bucket ladder mounted at, out of curiosity?
The
angle of repose that the bucket ladder has, because it's not vertical, it's at an angle.
It is at an angle.
Is it 15 degrees, 20?
I think 15 degrees.
15 degrees. Yeah. We played around with that too, looking at, because our first bucket ladder robot, RD3, it was vertical.
Fully vertical?
Yeah, fully vertical. And we had to run it at a very high speed to get everything into the hopper, and we still couldn't. And we wound up, we had a mining efficiency of about 30%.
So the intent was for it to go fast enough that the buckets on the top would throw it into the back.
Throw it into the thing. But the angle on our buckets wasn't allowing us to throw all the material out. So 70% of what we collected went right out the bottom of the robot. And but that was okay because we still wound up collecting enough material to win the mining award. We got 72 kilograms on our best run. And
there you go.
the funny part about that, you know, is the regolith that they have down in NASA does have rocks in it. And that year our scoops were made out of polycarbonate. So they flexed. They flexed. And as we'd catch rocks in there, we started seeing these little contrails coming off the surface of the arena and flying all over the inside of the tent and onto the, and then we started hearing some snapping sounds, and we realized that we were catching rocks and launching them like bullets all over the arena. And I was really very concerned about that. We hit the other robot, we hit the ceiling of the arena, we almost hit a judge in there. And I came up after the run and asked the chief judge in the arena, Dr. Mesker. I asked him, Phil, what are we going to do? I'm concerned about operational safety of a robot. It's throwing rocks like bullets. And he said, I'll take care of that. And he turned around and yelled at all the people in the arena that were working there. He said, people, don't stand in front of this robot when it's mining. And turned to me and said, okay, problem's taken care of.
Oh, there you go.
So
well, at least the bucket system didn't break.
No, it was but here again, because it was out of plastic, they would flex and get energy in them, and as soon as the rock got through close to the surface,
launched them.
Oh yeah, just launched them. And so the next year we used aluminum buckets, and it didn't have that problem anymore.
Yeah.
So no more plastic buckets. So we're getting quite a few of our club members here watching your robot run. They're getting quite impressed with what you're collecting here. Having to deal with that rock. We're a little past halfway, and we only got about a third of the berm area left to cover. But this is a good thing. This is the sort of thing that is very impressive mound of material that we got going here.
Yeah, looks like we do got a little bit more space in that back section.
Yeah,
so.
Looks like he's lining himself up, but figuring out how much room he's got to run without rocks sitting there.
Right.
Yeah.
See what's going on.
I don't know what they're doing. Hauling some wood into the conference room there. That's my club member, so always have to be concerned about what are they up to. Looks like they're going to do a little finagling on arena setup. Well, okay, so we got a lull here. Looks like your mission crew are having a council as to what they're going to do. Hopefully it isn't a case of communications has dropped out. We certainly had a lot of those sort of problems today with communications dropping.
Right.
But really? You must be getting hungry.
I am a little bit hungry.
Okay. Well, that is a good run. That is a very good run, even with 12 minutes and 29 seconds left to go. Well, congratulations.
Thank you, sir.
Colin, that was a very impressive run by Team Creed and their robot. Even though that's the first time I've seen a team want to end their run early. We're good enough. We're just going to go home and relax tonight.
I wasn't expecting
working
that myself,
good.
but...
Yeah, that's good. That's very good. Very impressive robot and very efficient. So hopefully next year we'll both be down in Florida and we can show their other teams the sort of things that we can do.
Yes, sir. Yeah.
It's looking good. Okay. Excellent.
All right.
All right, well, I'll let you catch up with your team. Let me know what the report is from Mission Control, would you?
Will do.
All right, very good. Thanks, Colin.
Thanks for having
And
me.
thank you for being here as part of the competition. We really appreciate it.
Thanks for hosting the team.
Yep. Okay, well, there we go. That's the last run for the night. So we'll be signing off soon, a little early. That's good. It's 5 minutes to 7, but we intended to go till 7 o'clock, so we're doing fine. And we're done for the day. So we'll see you tomorrow at 9 a.m. is the plan. And looking forward to seeing the runs tomorrow. So thank you for being here with us tonight. This is Jim Heisey, faculty advisor for Cardinal Space Mining Club. On behalf of the club, I want to thank you for being here, and thank you to Iowa State University for letting us use the facilities here to run this competition, the Collegiate Space Mining Challenge at Iowa State University. Good night.